Yeah. Okay. Okay. So yeah. So thank you everyone for coming. Welcome to the 7th edition of the workshop on benchmarking multi-target tracking. Where this year we will be focusing on how far synthetic data can take us. So I would like to take a moment to acknowledge the Juneteenth federal holiday, which celebrates the emancipation of African Americans from slavery. I would also like to thank my colleagues that helped organize this challenge. We have Mateo, Alyosha, and Rita around, and also some of them that couldn't join, or Chun, Patrick, Simone, and Laura. Okay. I would like to quickly motivate a little bit the workshop. I would like to start by quoting Richard Sutton on his famous blog post, the Bitter Lesson, where he says that the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. So I think here computation can be understood as either model size, hardware, or amounts of data. And here in this workshop, we'll focus on the data side. So I think in recent years, we have seen several examples of this, such as the big success of large CNNs, and more recently, with the introduction of transformers into vision, I think that this trend is only getting more obvious. Or basically, we see that scaling large models with large amounts of data is leading to great success. So the kind of summary here is that we know that our models are data hungry, and they are just getting more and more hungry for more data. So in the context of tracking, let's maybe have a brief overview where our data sets stand. So we can start with the Kitty dataset. That was maybe one of the first modern efforts to collect a large dataset in the context of autonomous driving and among other tasks. It focused on multi-object tracking, and it had these 24 sequences for training, focusing mostly on not so crowded scenarios. 2 years later, we had the first edition of our mod challenge, MOT15. That was then the year after consolidated into the MOTSynth, which was maybe which became like a standard benchmark with 7 training sequences and 7 test sequences, focusing on diverse pedestrian tracking scenarios, mostly crowded. So a few years later, we saw how maybe the community started focusing on more complex tracking tasks, such as joint human pose estimation and tracking. In 2019, we saw another example of this with mods being introduced, in which we focused on not only tracking with bounding boxes, but also tracking with segmentation masks. Year after, we had the MOT20 dataset introduced at our edition of the BMTT workshop, in which we focused on heavily crowded scenarios, so even more complex tracking. We also saw several efforts, I'm not listing all of them, of autonomous driving datasets that were now on a much larger scale. And lastly, last year at this edition of the workshop, we saw the first, we introduced the STEP datasets for video panoptic segmentation, in which now we are not only interested in tracking bounding boxes for pedestrians, but also getting instance masks as well as semantic segmentation. So essentially tracking every pixel in the image. So this is a much more complex task. So kind of the general pattern that we see here is that we see that as time goes by, we are focusing on more and more complex tracking tasks. And the question here is whether manually annotated datasets can keep up with the complexity of the tasks we are trying to tackle. Because for instance, we know that for video annotation, it's quite hard. We know we want to have temporally coherent, for instance, segmentation masks and bounding boxes, and it's quite hard to obtain this with manual annotations. And for some tasks, such as for instance 3D human pose, it's even almost impossible to do this manually. So with this in mind, at ICCP 2021, we presented the MOTSynth dataset, which is a large-scale dataset that we obtained synthetically with over 700 sequences, and it's the largest scale up to date for tracking, segmentation, and human pose estimation. We also have depth maps and information such as occlusion information that would be very hard to obtain manually, and of course with temporally coherent segmentations. So I think for us people working on tracking, this seemed like something quite cool, because now being used to these maybe smaller data sets, now for once we had this large data set that in principle should finish this data bottleneck that we were having with real data sets. But of course, the question here is whether methods that would be trained on this synthetic data set would generalize well to real data. So the long answer to this question is that we consider two settings. So we first considered MOTSynth as a kind of pre-training data set that then we would use, would use models trained on that, would fine-tune them on real data. So if we compare pre-training on MOTSynth versus COCO, which is the more standard pre-training, we see that MOTSynth, when models pre-trained on MOTSynth, when tested on real data, would perform better. Without fine-tuning though, so just completely getting rid of real data and just testing directly models trained on MOTSynth or real data, we got quite good performance, but we saw that for some tasks we had up to a 20% worse performance than models trained on real data. So the short answer is yes, models trained on MOTSynth generalize quite well, but there's still a domain gap. With this motivation in mind, we decided to organize a challenge for this workshop, in which basically we aim to gather the tracking community and ask how we can close this domain gap. So the rules were relatively simple. Only MOTSynth annotations can be used for training. So models need to be trained on synthetic data, and then they will be tested on real data. And we did allow MOT17 training images to be used, but no annotations can be used. So this was to allow domain adaptation techniques to be applicable, but no real annotations were allowed. So we had over 20 competitors taking part in the challenge, but in the end we also asked participants to provide code and a technical report, and we had 5 final solutions that were valid. So of course this is a limited sample size, so we cannot draw many conclusions from that, but there were some patterns though. We saw that essentially all methods participating in the challenge focus on the tracking by detection paradigm. So basically they first apply detector for every frame in the image, and then focused on linking those detections into trajectories. We saw that the most methods essentially focused on improving the object detector. So this seemed to be the more important part of the pipeline. And we saw that the top 3 competitors all focused on domain adaptation or semi/self-supervised learning. So they all exploited the real images in MOT17 without the annotations. Also, another pattern here is that in terms of data association, so linking boxes into trajectories, we saw that most people focused on relatively simple schemes that were just not even using appearance, but just motion cues such as Kalman filters. Anyway, I don't want to anticipate more of this because we will have in 1 hour, more or less, we will have the winners of the challenge explaining their solutions. So stay tuned for that. And yeah, and apart from this, we'll have a set of really nice speakers, starting with Tadas now. And yeah, and we'll have the speakers, and at the end of the day, we will basically gather all speakers and have a roundtable discussion where we'll try to draw some conclusions over all the things we learned today. So this is it from my side. And now I would like to introduce our first speaker, Tadas. If you're here, could you please share your screen? Oh, just a second. Sorry about this.
Can you hear me okay? Can you see my screen okay?
Can you speak again, please?
Can you hear me okay?
Yeah. Okay. So I would like to quickly introduce our speaker. So Tadas is currently leads the human synthetics team at Microsoft Cambridge. His primary research interests lie in the automatic understanding of human behavior, computer vision, and synthetic data generation. In particular, he's interested in the application of such technologies to virtual presence. He received his PhD and bachelor's degree in computer science from Cambridge University and completed his postdoc at CMU. So we are very happy to have Tadas here. And yeah, whenever you're ready, you can start.
Great. Thanks for the introduction, Matteo. And hello, everyone. It's nice to join you at CVPR and at this workshop. So today I'll be talking about our work on synthetic data generation for the purpose of generating training data to tackle various tasks related with face understanding. And so some of you might know that synthetic data has been used successfully in already used successfully in various products in industry. So some of you might know that the skeleton tracking in HoloLens in Kinect, in the original Kinect, was done using synthetic data. Few you might know that hand tracking in HoloLens 2 was also trained using synthetic data. So there's already quite a wide array of applications for body tracking, for hand tracking, trained on synthetic data out there in the industry. So we were thinking, can we do the same thing for faces? Can we train reliable models that analyze faces using synthetic data alone? And turns out that you can. And I'll be talking about our synthetic pipeline today, and we'll highlight a couple of applications that will show off what can be done using synthetic data in this space. So here's some examples of faces rendered from our synthetic pipeline. So we can generate a diverse array of individuals with different clothing, hairstyles, different facial appearance, and alongside that, create great annotations that would be really difficult or sometimes impossible for humans to do. And I hope you'll agree that our faces are quite realistic. And turns out that this level of realism is sufficient to train deep learning networks to perform various face analysis tasks. So hopefully, because you're attending this workshop, you don't need too much motivation for synthetic data, but it's still worth sort of a quick reminder. So why are we interested in synthetic data? And maybe before that, sort of by synthetic data in our work, I specifically refer to using computer graphics to generate imagery rather than sort of the more recent and quite popular approaches using GANs or other ways of sort of neural net-based image generation techniques. So I refer to more classical visual effect style computer graphics. So why do we want to create synthetic data? Well, we have control over the data we want to generate. We can create unusual combinations of appearances that might be really difficult to capture in real life, unusual scenarios or environments. And very importantly, we can create ground truth annotations that would be impossible for humans to create, either because it's just too expensive for humans to annotate. Maybe humans are just too inconsistent at annotating particular things. For example, each pixel of a hair strand would be really difficult for humans to annotate consistently in for large data sets. And it unlocks a lot of really cool applications when we're not limited by type of ground truth available with each image. So it becomes, our imagination is the only limit there. So what makes good synthetic data? So we like to think of it as sort of look at it through three axes for that. First of all is realism. We want our synthetic data to be realistic. So hopefully that's not a too controversial a statement. We want our data to be diverse because that's going to let it generalize to a broad set of individuals. And we also want the richness of label. And by that, I mean ability to extract semantic information from synthetic data. And this is especially important because when there's different types of synthetic data we can generate, we can render scans of people, which will be high in realism and maybe high in diversity, but will not have the same richness of label if we compare to us using a parametric model of a human body, where we know each location of each feature on the face, which would not be available in a scan. So, and maybe something similar, we don't get the same richness of label if we generate synthetic data using GANs. You might get really high realism and diversity, but not richness of label. So we want to be in this sort of corner here where we hit all the edges of the axis, but of course, often in real life, you need to make trade-offs. So just briefly about why we care about realism. Well, it allows us to spend less time worrying about domain mismatch or domain adaptation if our synthetic data is highly realistic. So we can spend time more tweaking what is in our data rather than the realism of it. Why do we care about diversity? Because we want models to work on everyone, not just on a subset of people. And you know, we're probably never going to reach a point where we can generate the full diversity of human appearance. And I think it would be quite a boring world if we did get to that point, because every year there's new fashions, both for hair and clothing, that it's going to be difficult to match. So we're always going to be chasing that end tail of human realism. But we can get really, really far by sort of capturing a broad set of realism, even if we don't get like the entirety of it. And richness of labels. So why do we want rich labels? You know, from at one edge, we can have bounding boxes and that's it. At the other, we can have per pixel annotations of normals, depth, and semantic categories. And the richer the label, the more exciting applications we can build on top of it. And I'll sort of, at the end of the talk, I'll show some of the benefits of that in our work as well. So we talked about the importance of realism, richness of label, and diversity of our generated data. How do we get that? Well, in our work, we treat, as I already mentioned, synthetics as visual effects, except that in our case, we don't just need to get a single scene right. So visual effects can create synthetic data that is indistinguishable from real data. A lot of films, you wouldn't know that visual effects are being used sometimes when they are. They're just so good. But our job is to do a similar task, but at scale and with much larger diversity in appearance than is done in the movie industry. So it's a slightly different challenge there. So how do we build that? Well, we need to have a parametric model of the thing that we're building. So in our case, faces. So that really underpins everything we do. We need to have a pose or expression library for that parametric model so that we can sample different expressions on that face in different poses. We need to have a wardrobe, clothes, hairstyles, makeup. And finally, and probably least importantly, is we have to have a renderer and the system to sort of generate that ground truth. And that sometimes can be different interchangeable ones. Okay, so with sort of having described what makes good synthetic data, let's walk through how we build our face synthetic data. So we start, and I'll sort of go into depth into each of these steps, but as an overview, we start with a template face to which we add an identity, so change in geometry to generate a different person. We add an expression and pose. We add texture and displacement maps. We add hair, clothes, and place that face in an environment. And that's enough to render an image of a face. And of course, we can generate ground truth annotations alongside it. Briefly talking about our parametric face model. So we use a fairly simple 3D morphable model style linear basis model. So nothing very unique about our parametric face model. Maybe worth mentioning is that we have articulated eyes and teeth and tongue in the model as well. And it's created from around 500 scans, a reasonably diverse set of individuals. And our expression basis is constructed manually by an artist to try capturing the broad range of expressivity a human face can display. As I also mentioned, the importance of a pose library in synthetic data. So we create our sort of pose and expression library, and I use the terms pose and expression slightly interchangeably in our work, mainly because our expressions are just blend shapes with a couple of bones for pose. So suppose plays not such an important role. So we have a multi-camera rig in our lab that allows us to capture people making faces in it. So we have over 100 subjects' performances in that rig, and we can use markerless motion capture to construct expression data. So here's an example of that. So here's myself being captured in our multi-camera rig at different viewpoints. You can see that I'm just wearing a skull cap. There's no markers annotated on my face. And what we can do is we can run a dense face landmark detector on my captures, and then just fit our parametric face model to those dense landmarks. And that way reconstructing my expressions. And then we can replay the same expressions in our synthetic data. So this allows us to create an expression library at scale. So now you may be asking, where does the dense landmark detector come from? Don't you use synthetic data to train that? And yes, we do. So this is sort of an example of a virtuous cycle that we observe with synthetic data in our work. Sometimes we create a first iteration of our pipeline using worse quality expressive data, then bootstrap a landmark detector, and now we can use it on on more complex data, and we can sort of complete this loop a couple of times until we get DNN models that work well on diverse set of expressions. So we probably don't want to just render blue faces in our system. So we have a texture that we apply to faces, and we use just exemplar-based models. So we just sample from 200 textures in our manually constructed texture library from real people, from real scans. So no DNNs here. We apply a displacement map to create a bit more detail in the face. So we have two displacement maps. One is for coarse level detail, one more fine-grained level detail to model things like pores. And then we can render a face that starts looking quite realistic. Now, we also need to add hairstyles to our faces. So we have a big library of strand-based hair. So, and by strand-based, I mean sort of each hair strand is modeled explicitly. So a hair groom artist will have created these really highly realistic hairstyles manually, and it's quite an involved process to do, but you get really, really high quality hair then. And we have a library of head hair, eyebrows, eyelashes, and facial hair that we can then randomly sample to add to our heads. We can sample color and density of the hair. We can add gray hairs as well. So it allows us to create a lot of diversity in our hairstyles. We then clothe our digital heads. We have a library of upper body clothing and a library of headwear and glasses. So this allows us to sort of really create quite a diverse set of digital. We have a diverse set of digital assets that we can then apply to our heads. And here's an example of that in action. So it's the same 3D head of a person just being dressed in our library of accessories and clothing items. And in addition to having different geometries, each of our clothing items also has procedural textures. So it allows us to, even if the geometry is the same, we can sample different looking clothing items by varying things like the size of the stripes or hue of the scarf or hue of your jacket. So it allows us to sort of create more diversity. Then you can sort of see that I keep referring back to this diversity of data, because we believe that's really, really important to generate synthetic data that's as diverse as possible, because it just lets your models generalize much better. So here's an example of placing sort of, once we assemble our digital heads, we can place them in an environment. We use high dynamic range imagery to act both as the background environment and as source of illumination for our data. And because illumination is hugely important, it's the same face can look hugely different, or any object really can look hugely different under different illuminations. So it's important to have quite large diversity of those as well. And so now I talked about sort of all the assets that come into our digital human pipeline. And one thing that is sort of like as an aside that I want to mention is how synthetic data can act as multiplier of data. So say we create a new, we capture a new sequence of expressions. We can replay that same sequence on different individuals. So we just, the cost we incurred was creating a new expression sequence, but we can replay it on thousands of different looking individuals. So it's sort of our data that we captured multiplies by allowing it to, by us being able to replay it on very different individuals. And it goes not only for pose captures, but say we create a new hairstyle, we can put that new hairstyle on different shaped heads. We can add same clothing on different shaped heads with different expressions. So it allows us to go really far with creating only a couple of assets that will be replayed on a broad range of identities. And of course, there's sometimes complexity of how you combine different shaped heads with different shaped clothing, and there's like the element of proceduralism there, but I think it's a huge, huge advantage of synthetic data. Okay, so we can generate the synthetic data. We can generate ground truth annotations to go with it. Things like normals, depth, landmarks. So in this talk, I'll focus specifically on what we can do with facial landmarks. So for that task, sort of wanted to see, can we use this data? Can we use this for solving real world problems? And for that, we generated a data set of 100,000 images of faces. with landmark annotations, and then trained a dense landmark detector network. So, and let me sort of go into a bit detail on that. So we train off-the-shelf ResNet to predict 703 landmarks on the face. So something that would be really, really difficult for humans to annotate. And we just train, just as I mentioned, an off-the-shelf ResNet to perform that task. And it turns out it generalizes quite well to real data. And I'll show you some results in a couple of slides comparing to state-of-the-art work. One really important thing is that when we generate synthetic data, we generate it from a perfect camera. We don't have sensor noise. We don't have lens noise in it. So what we do is we perform fairly aggressive training time augmentation to introduce that noise, to introduce gamma correction, shot noise, contrast variations, various warping effects, distortions, and that is really, really important to train good models that generalize on real data if you train only on synthetic data. And in all the examples I'll show you, we never mix real and synthetic data. We use synthetic data alone. It just saves so much effort when you can just do that. One other thing that's worth mentioning about our models is, in addition to predicting the location of landmarks, we also predict the uncertainty of the landmark. So there's nothing fancy happening there. We just use Gaussian negative log likelihood loss. And you can see that, let me play that again. Green landmarks are shown, the ones that the network thinks that are reliable, and the red ones are the ones which it thinks are unreliable, and it just estimates, probably mostly through the mean shape of the face, where those landmarks should be, the ones that are unreliable. Okay, so we also are able to train a sparse landmark prediction network because a lot of academia is using that, and we want to compare our models to the standard academic setups just to see how well we compare to them, and if we use the same standard data sets, because there's no really, very, very few data sets out there that are annotated for dense landmarks. So and one aside, and I think an important one, is how do we evaluate models trained on synthetic data on real data? Because typically there's not only a domain gap in appearance, but there's also going to be a domain gap in...
Hey, Tadas, 1 second. We had a little bit of a technical difficulty. Please pause for 1 second. Tadas, can you speak for a second?
Yep. Can you hear me okay? Hello?
Okay, 1 sec. Okay, I think we're good. Can you please speak one more time?
Hello? Can you hear me okay? Hello?
Yeah, we're good.
Great. So one challenge with evaluating on real data when you use synthetic data is that the annotation semantics might differ. For example, if you ask a person to annotate 2D landmarks of a face, they'll annotate the outline of the jaw, for as an example, even though that's not where the projected 3D location of the jaw would be. It would actually be sort of X-rayed through the face. However, it's not an incorrect annotation. It's just an image space annotation that humans would provide. And it depends on your application, which annotation you want. But training synthetic models on one type of annotation and evaluating on a different one your model error will be dominated by those inconsistencies rather than the model actually failing. So we need a way to cope with that. And for that, we actually train a separate network that does translation. So that will translate from the convention of synthetic data to the convention of real data. We never train it on any images. We just train it from a network that maps from landmarks to landmarks. So say from 68 synthetic landmarks, synthetic style landmarks to 68 real style landmarks. And this allows us to evaluate models trained on synthetic data on real data on a fair footing. The first thing we did was, take an off-the-shelf ResNet, train it on real data, and train it on synthetic, and then evaluate it on a standard set of benchmarks on 300W dataset. And we found that we perform significantly better when compared to models trained on real data. So this is just taking an off-the-shelf ResNet. It's not what state of the art is in the face landmark communities. So we wanted to check how well we compare to state of the art methods for the task. Well, turns out we're quite competitive with them as well. So there's a couple of methods that perform better than us, but they keep in mind that they are evaluating within dataset. They train on the same dataset and evaluate on the same dataset, and there's always going to be biases in dataset types of annotations, types of images captured there. And they're also really tuned for the task of landmark detection, whereas we just use an off-the-shelf network. And we still, with synthetic data, we're still able to be very competitive with those approaches. One quick question is we might think okay, how many, because we can generate an infinite number of synthetic images, how many should we generate? How much is enough? We found that after about 50,000, 100,000 images, we start getting very limited returns on the compute required to generate that data. And due to lack of time, I'm not going to go into too much detail here. We also care very much about the fairness of our models, and we evaluate on fairly diverse, maybe the MUG data set is slightly less diverse in terms of lighting and pose variation, but it's quite diverse in types of identity. And we really want to make sure that our models generalize well to everyone, every type of individual. And finally, like as a teaser of some of the other work that we've been doing in this space is this is what you can do if you have really reliable, dense annotations of dense predictions of facial landmarks. So what we can do is perform dense landmark prediction and fit our parametric face model to them to reconstruct the expression and identity of the person. And this is being done in real time. There's a paper on arXiv that we recently released from our team on this. And the only input signal it's using for reconstructing facial expressions and identity is the landmark location. So it's not using any photometric losses, photo consistency losses. So it's just using the landmark information. And we can get really high quality state-of-the-art reconstructions of the face using landmark information alone. Okay, and so this concludes my talk, and thank you for your attention, and please visit our project website for more information. I'm open to questions.
Thank you very much. Wait, let's give him a round of applause so he can hear now.
So do we have any questions in the audience? Yeah, you maybe want to go.
Yeah, come here. So, hi Tadas, I'm Matteo. As a synthetic data user, I believe that synthetic data are of course useful and they can replace real data, but you didn't show failure cases. What are the failure cases of your synthetic data? Do you have some, or it works smoothly, like 100%?
Yeah. Excellent question. So yeah, and apologies, didn't go into that. Often they are related to domain gap, but not in terms of appearance, more in the types of content. For example, we don't have tongue expressions in our synthetic data. We don't have someone sticking their tongue out. So in the real data, we try running on an image with a tongue sticking out. There's going to be sort of some failure there. We don't have mugs in front of faces in our data. That's going to lead to some confusion from the network. So it's going to be one really nice thing at least I find from using synthetic data. Quite often, failures are fairly obvious. Not always, but reasonably often is sort of, okay, we don't work well if a person's touching their face. Well, we don't really have any images of people touching their faces. So that's the way we tackle it. We just add that data.
Yeah, perfect. Thank you. Maybe one more question. Yeah. Okay.
What's the next step?
Yeah. So Gil from dataset is asking, what's the next step in your opinion?
It depends. There's so many different directions in which that we can answer that question. The most obvious ones are, just expanding libraries of our assets and diversity and sort of keep adding these incremental improvements to our pipelines. The other ones sort of, let's do the same thing for full bodies, for interactions of people with objects, for interactions of people with people, and apply it much more broadly in industry and academia, because that so far there's so many possibilities of synthetic data, but it's not used as much as widely yet. And I suppose, well, that's why we have these workshops to advertise the benefits of synthetic data.
Perfect. Thanks a lot. Maybe let's thank the speaker once again. Okay, and now let's move to the next talk by Gil Ebas. So Gil is the CTO and co-founder of DataGen. He's based in Tel Aviv, and he received his Bachelor of Science and Master's from the Technion. Gil's thesis research was focused on 3D computer vision and was published at CEPR. So Gil, we're very happy to have you. And yeah, whenever you're ready.
Thanks. Okay, perfect. Hi, everyone. It's a pleasure to be here. I'm Gil, the CTO of DataGen. I'm one of the co-founders of the company. Today, I'm going to talk a little bit about synthetic data generation around humans. We do very, very similar things to what Microsoft has shown, but we, of course, work with all of the companies that you guys see here, providing them with synthetic data for helping them solve the real-world challenges. So it's a pleasure to be here. And Tadas just gave an amazing talk, which is a perfect way to kind of kick off this conference. And it segues very nicely into what we do. So just to kind of take a step back, we're at CVPR. All of us are working on a ton of different things, but all around understanding the world, really being able to extract structured information from unstructured data, from visual data. And it's really impacting a wide range of industries. So we have people here that are focusing on robotics, focusing on human tracking, on understanding people, and really in a wide range of applications. And we as DataGen, our goal is to take this amazing work that Tadas and his team have shown off just now, and really bring it to a production level and provide it to all of the companies kind of in the world that are focusing on synthetic data, and allowing them to really focus on the research, focus on creating amazing computer vision models, and less on the very heavy engineering side that has to do with synthetic data. So of course, data is messy, and really synthetic data, as we just saw, shows a way to scale up the data in a very fast, a very seamless way, have much more control over the data, and be able to really answer the needs that your network has. So understand where the failure case is and quickly iterate, quickly turn around new data sets. And so what computer vision engineers really want, right, is unlimited access to data that has both granular control, meaning we want to define exactly what is in our data. We want to define the hair color because we just found that it doesn't work well on redheads, for example. We want to define kind of the specific pose of the head because we understand that when people look too much to the side, our network breaks down. We want to understand the age, gender, ethnicity so that we can deal with biases. And so this granular control is extremely important. The second big thing is really we don't want to deal with biases and PII. PII is personally identifiable information, and capturing images of faces is something that the big companies are trying to do less and less of. Just holding this data is quite complicated. But also with respect to how we look at the evolution of computer vision going forward, we want to rely less and less on data that's gathered from real people, that has privacy information attached to it. And then zero bias, meaning not that we don't want to insert biases, right? Like we want to allow you to control the high-level distributions of the data. So there are no inherent biases baked into the data. What we see when we gather data from the real world, no matter how much effort we put into it, there's always going to be biases due to demographics, due to the lighting situations that the data was captured in, due to the time of year that the data was captured. And so in order to get something that represents an extremely wide domain, we need to be able to fully control this data. And of course, this is possible with synthetics. Annotations, of course, needless to say, with synthetics, we get perfectly annotated data, and data that is not just perfectly annotated, but richly annotated, meaning we can pretty much request whatever annotations we need and get very nicely annotated data at scale. And the annotations don't cost extra, right? It's one of the benefits. And we want it to be domain specific. And this is actually a very interesting point, which is maybe a little bit of a unique point relative to the previous talk. Microsoft did an amazing job, and they focused mostly on solving AR problems for their HoloLens device. We are working with a ton of companies in a wide range of domains, and we provide domain-specific synthetic data, and we're going to show you what that means. Okay, so just a little bit on kind of what it looks like. What are these synthetics? What is this ground truth? You get fully annotated synthetic data at scale. This is like one of the faces with the modalities kind of drawn on top. And this is a very powerful thing. If you can control the data point level annotations, the data point level features, you can pretty much use your imagination to create whatever data is needed. And we also have these full domains, and we're going to show you a sneak peek now and then dive into the data-centric approach and how to actually use the synthetic data in an effective way. But just to show off a little bit of kind of what this looks like, we have 4 different domains that we currently support, and we're constantly expanding it. We have a completely generic, agnostic, domain-agnostic infrastructure, of course, to add more and more domains. And the idea is that we have people that are dynamic, driving in a car, in a smart office, writing on a board, home security, coming to the home with a package and delivering that package, and also doing fitness exercises at home. And we work with big companies in many different domains and of course provide them with this synthetic data. So I'll show you guys a sneak peek and then we'll dive into kind of how to leverage the synthetic data. So these are 10-second sequences. Every frame is fully annotated, of course, and we are able to do this at scale. So we have the ability to generate humans at scale, we have the ability to generate motion at scale, and we have the ability to render things at scale. So you don't have to deal with any of the engineering aspects. Really, you can use your imagination and generate data to solve your problems. Cool. Okay. So let's talk about how to leverage this data, right, to solve real-world practical applications. And so Andrew Ng, beginning of 2021, kicked off the year with data-centric AI, this name for something that we all kind of understood existed, but he gave it a name and he kind of pushed it forward, where describing data-centric AI as the practice of systematically engineering the data used to build AI systems. And I think that this is a very powerful way to look at data. On a conceptual level, right? These neural networks are kind of these black boxes that weigh, let's say, 30 megabytes, 300 megabytes. But for most edge case or edge device neural networks, they're relatively small. We as DataGen sometimes create 250 gigabytes of data, for example. And conceptually, the way that I look at it is these networks are really compressing the data and extracting from it the minimum information kind of needed to create this transformation function, right, from an input image to whatever output we're training it on. And of course, this is guided by our loss functions. But at a conceptual level, it's a compression and extraction mechanism that we can then later leverage to inference very quickly and create these transformations in real time. And so when looking at it from this lens, right, as the data is actually the knowledge and the network is really just compressing and extracting, it gives kind of a new perspective on the power of data and what we can actually do with it. What knowledge do we actually want to imprint in our neural networks? And so if we look at the kind of standard methodology, right, that we had up to now, we would acquire data, we would train models, we would perform some evaluation on a test set and deploy it in production. And so we would iterate many, many times. Because it was so hard to gather data, we would iterate many times on the hyperparameters, on the layers of the network, on the architecture, etc. And this is very model-centric. This is what we call the model-centric approach. The flip side of that is the data-centric approach. If we can have full access to data instantly at scale with control, we can then suddenly iterate on the data itself and create better and better data, and data that actually solves the problems that our network is having. So for instance, if networks don't work well on people with glasses, instead of doing hyperparameter tuning to improve the generalization, we would want to iterate on the data and add people with glasses to the data itself. It sounds trivial when I kind of frame it like that, but it's a very non-trivial kind of approach because it was so hard to gather the data. So what do these iterations look like, right? What is the practical way that we actually do these iterations? So there are three high-level ways to iterate on the data. One way is to calibrate the data. So calibration means, we're trying to, of course, represent reality. We're trying to represent some target visual domain. And so calibrating the data is getting our data to be closer to that target visual domain. There are some things that we know ahead of time, like let's say the distribution of people with glasses and not glasses. There's some things that you need to iterate on, test, and slowly improve. And so things that we want to improve here with calibration could be, getting more finely tuned camera parameters, lighting that better represents the domain, and more advanced methods can include also domain adaptation and various neural network-based methods. Jonathan, who gave a talk in SynthML conference yesterday, talked a little bit about DataGen's effort around domain adaptation using StyleGAN. And so that's a really good kind of way to look at calibration. Variance is the second kind of way that we can iterate on the data. We can say, okay, we don't know exactly what the calibration step is. We don't have a clear signal. So let's add additional variance. And like Tadas mentioned before, with synthetic data, it is recommended to use heavier augmentations and to add more variance than you would see in the real world. And so adding camera variance, adding variance with the accessories, adding variance with lighting, these things are all very, very powerful and can be done with quick iterations using synthetic data. And then the third is really augmentations. Augmentations are around, what do we want the network not to look at? So if we do random augmentation of brightness, for example, with the same kind of, even on the same data point, just to illustrate a point, we're telling the network to not look at the signal of the brightness when trying to transform between the image and the output. We're telling the network actually what not to look at when we use augmentations. And so when we randomize the brightness or randomize blurring or add salt and pepper, for example, we're telling the network not to be dependent on these visual signals when making a decision. And so these are three different steps that we can do when we want to iterate on the data as part of this iterative process. Now, one way to do this iterative process, right, we're talking about this data-centric AI, is what we call the iterative supervision process. And this is what's done with standard data. This is not for synthetic data specifically. And the idea is that we acquire data, we train with that data, evaluate it, and then we want to, of course, do self-annotation. So we run the model on training data. We do some kind of we do some kind of manual cleaning of the annotations, okay? And then we reiterate and retrain with that same data. And this is one way to bootstrap models. And it's what we call kind of an iterative supervision process, where we're just iterating on the annotations themselves. This doesn't need synthetic data, of course. And it takes into mind that you would have kind of errors within the annotation, the original annotation, or you would annotate only part of the data. The iterative data process, which is powered by synthetic data, in contrast, allows us to do data generation, train a model, evaluate that model, and understand where there are gaps, okay? Where are there gaps in the model? And we're going to talk about how we do this in practice. The last part is showing you guys 2 different projects that we implemented and showing you kind of the technical details. But we're first talking high level here. We want to understand where the gaps are. And then we want to expand our test set. So we want to add additional tests to then validate that we're solving these gaps. And also we want to generate new data based on these gaps to improve the model in these specific points. So it's kind of like understanding that we're not going to get the perfect network on the first iteration. And the approach is to quickly and seamlessly iterate on the data itself until we reach high performance. So smart directed iterations, okay? And then especially when data collection is challenging or labels are expensive, this is a very powerful approach. And if you have access to synthetic data, of course, it's kind of trivial. And the idea is really that we want the right data, not just more data. And this is an important kind of topic, because everyone talks about just scaling up data. But what is the data that we actually need? So we're going to talk now about a few different implementations, and then I'm going to leave some time for questions as well. So we did very similar to TADAS. We also did landmark detection on the face, and we showed off the data iteration approach. Our goal with this is not just to show that the data works, it's to show the methodology and how we see, kind of in a broader sense, the ability to use synthetic data for whatever task you're using. If it's tracking humans, or if it's doing head pose or eye gaze estimation or expression analysis, or whatever task you're dealing with, it's the same type of methodology. And so just to kind of quickly describe what we did, we started off with a very naive iteration on purpose, also just creating a first synthetic data set. We're testing on the 300W common data set, and we're of course using NME or normalized mean error as our metric. And so we started off first iteration, just create a head data set, and let's see what we get. We get a certain NME around 17, not great, let's iterate. And so we added stronger lighting, for instance, because we saw that specifically in failure cases that have stronger lighting, our network failed. This already created a nice boost in performance. We iterated again. We saw that heads that had strong head pose failed substantially. And so we added more variance with head pose. We also fine-tuned the FOV. We did again and again iterations to iteratively improve the performance. And this is like the main takeaway. At the end of the day, we also did tests seeing the different amounts of synthetic data versus real data and what the performance is. And we see very nice kind of graph here, where the idea is that with a very small amount of real data, you get a nice boost in performance. And we didn't even use that much synthetic data. The idea here is really just to show the methodology off. So with 100 kind of real data points, you get the equivalent of like 500 real data points. It's something of that order of magnitude as we go forward. And so in these iterations, let's talk a little bit about the gap analysis that we did. So for instance, the first kind of iteration that we did, we wanted to calibrate the camera position, etc. And so you see here on the top left, for example, in blue, the real data points, and in green, the synthetic data points. And so in the, you can see actually the points of the eyes and the chin. So what you make out here, this is the left eye, right eye, and chin. And this is in the real data set. And this is our initial naive synthetic data set. Okay? And so after this iteration, we said, okay, let's move the camera. Let's quickly iterate on this. And so this is the iteration afterwards. We pretty much changed the distribution of the head pose, and we better fit the validation set that we were using. Here on the bottom, we can see the original head scale. So we took a bounding box of the head, real and synthetic before, and we saw that the real data was larger than the synthetic data. So we pretty much moved the camera and we made it closer, and we better fit the data. And this is a very easy thing to do. And of course, you need to do it with the validation set, not with your test set. But at a high level, it provides very nice performance boosts in a very, very simple way. The second is really clustering, really understanding where the failure cases are happening. And there are various ways to do this. One powerful thing is because we're using synthetic data, we can do failure case analysis both on real data and on synthetic data, so synthetic test data. And because we have a lot of different annotations, we can then leverage it in various ways to understand, to cluster together where the failure cases are. This is one that just stood out to us. Like, we didn't do anything special to find like a hand covering the face being one of the big failure cases. But pretty much we're able to quickly and seamlessly iterate and cluster together failure cases in order to fill the gaps. And the third is also something that Tadas touched on, which is label gap analysis, where many times when trying to combine real and synthetic data together, we see that the real data was annotated in one way, which is totally fine as long as it's consistent. And the synthetic data is annotated in another way because we have full 3D ground truth, and because different synthetic data pipelines are developed in different ways, but this is totally fine as long as it's consistent. And so there are different ways to deal with this. One is to create a network for mapping between the two. This is what's called label adaptation, and we actually use this in our benchmark as well. But there are various ways to deal with this. So these are different ways to look at performance gap analysis and different things that we do given the performance gap analysis. Now we're going to show off kind of another implementation. So this was recently done by our algorithm team. We have a few in the audience. So we have here Ellie and Paul. Here, raise your hand, say hi. Yeah, right there. So we have a very cool kind of short paper that we just created around this, which is showing how to leverage synthetic data for hands-on wheel detection. So a little bit of motivation. There are many people that are killed every year in road accidents. We of course don't want that to happen, and so and they're many times due to preventable distractions. And so the idea is to solve hands-on wheel using synthetic data. We want to show synthetic data off in a real-world application. Of course, also there's like the 5-star safety rating, and all of the cars are going to need this capability in the next few years. So we're seeing multiple big companies work with us and use our data for this and many other safety-related topics. Okay, so the computer vision challenge is just classifying if each of the hands are on the wheel in every frame, and we want to reach good performance with little to no real data. So we use the DMD dataset, which is 650,000 labeled frames. This is real data. And we also have the hands-up synthetic dataset. We just made a small dataset, train, validation. It's the idea is to show off the methodology. Of course, we could create a data set of 800,000 images and not 8,000 images, but it would have provided the same kind of concept. So we didn't see a big need to scale this up. We used a very simple architecture. Like Tadas mentioned before, we want to keep the architectures as simple as possible, use the state of the art, the current state of the art, and add whatever kind of heads are needed in order to make it work. So we used a lightweight mobile net, 2 multi-layer fully connected heads, and we did frame-wise classification, so no temporal stuff here. And the synthetic data generation, we set kind of the camera up, we set the lighting, we had randomized car types, we had randomized demographics with an equal distribution between different demographics, and we had many different synthetic behaviors. So on the order of magnitude of hundreds of synthetic variations of behaviors. I'll show you guys what it looks like on the inside. So this is with the key points being visualized. One sec, I'll go full screen. So this is with the key points being visualized. Here are key points on the steering wheel and key points in the hand. And so in order to understand what the class is, we pretty much made sure that all of the key points of the hand were at a certain distance, or the furthest key point from the steering wheel was at a certain distance from the steering wheel. And this is a very cool and easy way to get annotations that we didn't even explicitly annotate in the synthetic data. Because you have access to a lot of 3D information, you can then be creative and be like, okay, how do I get the annotation that I need in order to solve my problem? Cool. So we iterated on this. I'll show you in a second some of the outcomes. We iterated on this. One additional thing is around the gaps, the gap analysis. So when doing this experiment, we created the first initial naive version. We found 4 different types of failure cases, or 4 things leading to failure cases. One is just occlusions, where hands were covering the other hand, where both were off the wheel, and we understood that we didn't have enough data of 2 hands off of the wheel. So it was actually very relatively easy to add. We had the opposite side, so like when you're like driving in a weird opposite side. I mean, I don't drive like that, but I don't know. I guess there are some people that do. And when they're fast moving, very strong blur, that also led to failure cases. And so we generated a new batch of data for blurring. Of course, we use simple augmentations. For the both off of the wheel and opposite side, we generated new motions and we're able to integrate them into the data. An example would be, when we generated hands off the wheel, we tested before and after, and we had like a performance boost that was quite significant with like recall from 7.7 to 8.5, and precision stayed relatively the same. The idea is that, by understanding where the gaps come from, we can actually solve them and then really create a very structured way to create production level computer vision capabilities. So cool results. First of all, the iterative data approach kind of works. We did see improvements with each iteration. We did a small scale pure synthetic version, and we reached, this is this green line over here. This is pure synthetic. And we reached like initial viable results. We didn't reach the ideal results, also because we didn't scale up the synthetic. We had a very relatively small amount of synthetic data, but we already reached good results. We also have on this red line using 600,000 real examples. And then we see kind of how we get quite close to this with combining synthetic and real data. What we did here is we pre-trained with synthetic data. We used a small amount of real data, and we saw kind of what the results were. The next step would be to use much larger scale synthetic data, because we should probably show off 600,000 synthetic data points versus 600,000 real data points. So we're gonna get to that. But the cool thing is, like, really with 300 real data points and 10,000 synthetic data points, we're already able to reach very nice results. And so this is quite a kind of nice proof of concept that we did internally. And we're gonna be iterating on this, so you guys can definitely check it out The paper is online. So a little bit on DataGen. We were founded in 2018. Now we have a team of around 100 people fully working on synthetic data. We work with a ton of amazing companies from a wide range of industries, including in the in-cabin industry for the cars, including fitness, including office spaces, like all of the different video conferencing applications that we use. And the idea is that we're really focused around working on human-centric computer vision applications. So that's a little bit on us. What we kind of offer, we do a lot of things around humans. So we have this head generator, very similar to what Microsoft showed off, but you guys can actually control the distributions of the data, which is great. It's going to be expanded to full body by the end of this year. And we also have humans in context, which are fully dynamic humans moving in environments. For larger customers, you can request your own unique environments. And you also get a very nice pool of environments out of the box. For academic folks, we're more than happy to collaborate, just reach out, and happy to see what we can do. And we also have a large suite of data tools. So we have a nice GitHub repo that we give you guys. You can quickly and easily integrate the data. There are examples of how to use the data in training scenarios, how to test with the data, how to visualize all of the different modalities and extract new modalities. So it's quite cool. And we're constantly, of course, improving this and expanding it. Thank you. That's my talk. Thank you guys very much. And of course, if you have questions, let me know. I'm going to do one final plug. I also have a podcast. So anyone that wants to come and listen, feel free to check out Unboxing AI. There I talk with like top computer vision folks from all over the industry about kind of the next level things that they're working on. And it's very, very cool. So yeah, any questions, happy to answer. Thank you. Thank you, thank you. Yes?
I have one question. In the future of the cycle of improving training data to match all the data cases, how do you assure that you don't overfit? Because that is notoriously, if you keep doing that cycle, at some point you completely overfit. How do you prevent that from happening?
Yeah, so it's a very, very good question. One thing is also leveraging a validation set, right? You don't really want to touch your test set, of course, but you want to see like where you're failing in your validation set. And so that's one kind of important distinction that I should have mentioned more clearly. But the second thing is, when doing real world computer vision, like for practical applications, my assumption is that there is no, like the test set tries to represent the real world, but of course there is a certain gap between the test set and the real world domain. And so we see this a lot, like where applications that are deployed to production, even though they have good performance on test set, there are still edge cases that make it fail, and there are still challenges that make it fail. So one thing is always just to keep in mind that the test set is never perfect, and we need to be constantly expanding it pretty much. And so one thing in the iterative kind of cycle is also adding new tests. And so similar to software engineering, where given a failure case in software, we add a new unit test to validate that problem won't happen again. We should be constantly expanding the test sets with computer vision applications as well. And so ideally, even though in academia for good reason, the test set is usually fixed, for practical applications, we see a very strong future of constantly expanding the test sets. Yeah.
How do you see the data scaling to other domains? How easy it is to scale?
Yeah, that's the biggest challenge with synthetic data. So with real data, all you need is a camera and a lot of man hours and a lot of effort, but expanding to new domains, like you want, I don't know, a new aquarium, computer vision to see your fish, right? So if you want to expand to that domain, it's not too bad. With synthetic data, you need kind of to do effort to expand domains. What we did in DataGen, which is kind of unique, is we created an infrastructure for creating new domains quite easily. And the main kind of, like I step back, the main kind of thought process we had was to separate between content and capabilities, where content is, for instance, the motion that's generated, the objects in the scene itself, right? That's just content. And we know we have different pipelines for generating this. And the capabilities themselves, which include rendering and swapping between the people and creating different, like putting accessories on and making people with different expressions and all of that, those are all just capabilities. And so by separating the two, we can easily just create new content, similar to Netflix, where they create all the time new content, and generate new synthetic data that's in new domains. So this is kind of what we're doing, but of course we're constantly adding new capabilities, and there are a lot of capabilities that we want to add. Yeah.
Yeah, very nice presentation, thank you.
Thank you.
Question about motion blur.
Mm-hmm.
I see often difference between real data and synthetic data is that synthetic data always misses motion blur, right? In the case where you have arms on the wheel. So adding just a blur augmentation on synthetic data, does it help kind of detect motion blur, or you have to use the motion blur within the synthetic data?
So it's a great point. What we did in our hands-on wheel was just a quick kind of fix. So like just adding blurring is a quick fix. But like we said before, adding augmentations is telling the network what not to use when trying to infer. And ideally, if we wanted to invest a little bit more effort, we would add blur into the data itself. And there are actually ways to add it into simulation. So it's actually not too hard. But currently, this is one of those capabilities that we're going to be adding into the platform. It doesn't yet exist there. But at the high level, we can either leverage in post-processing the optical flow to then try to generate motion blur that's more relevant, or we can add it into the simulation, into the core capabilities of the simulation, which is one of those things that we're going to be adding. But it's a very good point. And I think that there is good reason to leverage motion blur when trying to see if the hands are on the wheel or off the wheel, right? So ideally, this should definitely be added into the core capabilities. Another question? Yeah, sure.
Just a fun one. Of course, there are very, the use cases that you show, very serious ones, but have you seen your customers using that for some fun use cases? If you can speak about those.
So there are some cool use cases. So usually they're very focused on, like, I hope that the academia can do the fun stuff. These guys are usually focused on creating practical applications. But some cool ones are like this was used for paralyzed people to be able to control a computer screen, and so that's like a nice one. This was also used to make sure that people have masks in various places. We had some cool ones also in cabin. You can do a lot of things beyond just hands on wheel. So yeah, there were a bunch of unique use cases. Yeah.
Quick one. Are you obviously talk about computer vision? Are you simulating other sensors too? For example, if it's patients are displaying markers, are you?
Yeah, it's interesting. So IMU is like we haven't simulated the sensor errors in IMU, for example. Although it is very much possible, I think, maybe to do even in post-processing, because you have the full 3D information. But one thing I can say is, going forward, looking far in the future, right? All of the unstructured data is kind of what we're specializing in. So with very similar methods, we could do audio, we could do different things in 3D, LiDAR is possible. But right now, we're really focusing on visual data. One cool modality or type of simulation that we've done is infrared. And so we've put a lot of effort also into infrared. Okay, guys, thanks very much. And feel free to add me on LinkedIn. Yeah. Thank you. Sure. Thank you very much.
We don't have a 7 to 10 minute break.
But how do I do this actually? Because now, Alyosha? Oh, sure, sure. Okay, so for these those attending virtually, we will now have the award ceremony, and I will let you see it from here, and then we'll continue with the talks. Okay, I think we'll start in a couple of minutes. He's joining virtually. Oh, yeah. A little bit confused, actually. Oh, no, this is the one. This is the one that's going to be virtual. No, this is the one in person. This is the one given.
Are they? Well, I don't have their names anywhere else. I should still say their names, right?
Sure. Yeah. Actually, let me. So this is the overall winner. This is the overall.
Well, my day, you made my day. I was able to give you some, provide you some value.
So this is
So they have essentially
overall.
And you can build, you can export.
Then they'll give a brief virtual talk.
Yes. So after you, he will present you in person, and then we have the virtual talk. Yeah.
And do you want me to introduce, give them both at the same time, or I don't know how you want to interview this. Announce this one, let them speak, and then announce this one, and let them speak. Or do you want?
I think that would be better, probably. Yes.
How long is the call?
It's 15 minutes, 10 minutes per person. Thanks all by the way for coming in such a rush.
Sorry, Michael.
No. Okay. So yes. So I will put this here so that they can also see it, the ones that are not here.
I'm working on getting we do some of this
Okay. Okay, we're gonna start in a couple of minutes. So if you're staying, can you please take a seat?
Should I start?
I think so.
Yeah. Hey, everybody. Hey, I'm James. I got roped into this at the last second, or last minute, literally, because of some snafu at the Atlanta airport, my home city. I drove here, so don't worry about that. I'm James. I'm a principal scientist at Argo AI, and we sponsored this multi-object tracking challenge. And so because of that, I guess we get to say a few minutes about Argo, which I'm happy to do because I am enthusiastic about Argo. Michael Schoenberger was supposed to be presenting, but couldn't make it. So yeah, Argo is a self-driving car company. We have about 2,000 employees and about 10 offices across 2 continents. We're partnered with Ford and Volkswagen and are developing products for Lyft and Walmart to operate ride share and product delivery across the US and Europe. And a cool milestone that we just hit a couple of weeks ago was actual driverless operations in 2 cities, Miami and Austin. So that is a big landmark to pull the safety driver out from behind our test vehicles. They've been operating for a while now, collecting a lot of data. And one of the great things about Argo, why I'm there, is that we are able to share that data with the research community. So I lead the Argoverse project. We're going to present more about that at the workshop on autonomous driving later, actually, at 1:45. But we just published the Argoverse 2 data set this spring, which is really 4 data sets. The data set, sensor data set like New Scenes or Waymo Open, which are also great data sets. Another motion forecasting data set where you're trying to predict what an agent will do in the next few seconds. An unlabeled LiDAR data set, so that's something new, just enormous 20,000 scenarios without annotations, but suitable for things like semi-supervised learning or self-supervised learning. And as far as we know, the first map change data set, a data set where the AV has stumbled upon some change in the real world, a new bike lane, repainted lanes, a new crosswalk, and suddenly the HD maps that these vehicles use are out of date, and the vehicle needs to be able to say that, hey, you know, the map is not totally trustworthy right here. But anyway, I could talk about that all day. Again, we'll talk about that at other workshops. We are serious about computer vision, of course, at Argo, and we are hiring. That's the whole point of sponsoring this probably. We have an exhibition booth. I encourage you to stop by it because we have another really cool thing, which is an Argo LiDAR. So we make our own LiDAR internally. We've used Velodyne LiDARs in the past, and our public datasets use them. But our newest thing is this Argo LiDAR, which is extraordinarily dense and extraordinarily long range. And we actually have one physically here operating, so you can go and check it out. And I think that is a serious advantage for Argo to have this device. Okay, well, that's enough about Argo. What this is really about is presenting the award winners for this multi-object tracking challenge. And there are 2 award winners. And the first one here in person to receive it for the most promising direction award is for their work, Bag of Tricks for Domain Adaptive Multi-Object Tracking. I love the Bag of Tricks title, by the way. Is Ming Seok Su, Zhangwan Ryu, and Kwangjen Yoon. I understand that you have a brief presentation to give about that. Maybe I shouldn't step out of the way just yet. Oh, yeah, okay.
To the Zoom sessions? Yeah, perfect. Okay, good to go.
Okay. Hello everyone, I'm Jungwon Liu, working as a research scientist at SI Analytics. I'll introduce backup tricks for domain adaptive multi-object tracking. Yeah, the presentation will proceed in the following order. This year's BMTT challenge consists of 2 tracks. Among them, the MOTSynth to MOT17 track is an unsupervised domain adaptive multi-object tracking task that trains static dataset and evaluate them on real dataset. The data consists of the synthetic dataset MOTSynth as the source data and the MOT17 test set as the target data. To evaluate performance, HOTA is used to measure detection and tracking quality. MOTSynth is a very large-scale data set for pedestrian detection and tracking, including information such as bounding box, pulse, segmentation mask, and depth map. And when I saw the experimental result, I thought that high performance could be achieved by training only the synthetic data without domain adaptation, unlike the existing synthetic data set. This is an overview of our method. It consists of 3 main steps. In step 1, baseline training and store labeling are performed. In step 2, we combine and fine-tune the store label target and source data set using a proposed method called cross-domain mixed sampling. And in step 3, based on the fine-tuned model, we obtain the final model using iterative pseudo-labeling and weighted average on the target data. Here, the target data is MOT17 train set. First, we train YOLOX and ByteTrack as a labeled source data set and use it as a baseline. The reason for using YOLOX is that it has been mainly used in recent state-of-the-art methods. And augmentation methods such as mosaic, mix-up, and scale jittering and EMA model update were applied. So we judge it as a reasonable baseline for domain adaptive object detection. Additionally, not using error nodes performed better in our experiments. ByteTrack achieved high performance with a low score detection box. So we use this simple and effective method as our baseline. Then we train using only the MOTSynth dataset and store label the MOT17 train set. In step 2, the first fine-tuning is performed using the pseudo-labeled MOT17 train set and MOTSynth dataset obtained in step 1. So DOCS and DSP are cross-domain augmentation method used for domain adaptive semantic segmentation, such as GTA5 to cityscape. Similar to this approach, we propose cross-domain mixed sampling augmentation method. Mosaic augmentation and mix-up augmentation were widely used data augmentation methods for object detection because they can trace various objects. So we perform domain adaptation through a simple and effective method of merging the source and target data sets through mosaic augmentation and mix-up augmentation. In step 3, we borrow the model soup method. Model soup is a domain generalization method that achieves state-of-the-art in ImageNet A and ImageNet R by simply combining the weights of fine-tuned models with various hyperparameter settings of the same pre-trained weight, and choosing if they are outperform the weights before combining. Therefore, we used model soup to improve the domain generalization performance. Additionally, to improve the domain generalization performance, various weights for each augmentation were selected and the weight average using a method called greedy soup included in the model soup. Augmentation types are found experimentally in the smallest set of split one, and a total of 7 types of augmentation combination were selected. Additionally, we did not use the EMA model update for fine-tuning because it gives better performance experimentally. Iterative pseudo-labeling is a method widely used in unsupervised domain adaptation. In general, as the step increases, the ratio of the pseudo-label increases. However, there are limitations in the pseudo-label because there are many label noises. So we use the combination of model soup and iterative pseudo-labeling to improve performance. Our proposed method achieved 63.2 HOTA on the MOTS17 test set, and the first place MOTSynth to MOTS17 track with meaningful performance. This is comparable to the current state-of-the-art method of supervised multi-object tracking. Here is a video result comparing our method with supervised trained byte track on the MOTS17 dataset. We found 2 major limitations with synthetic data. The first problem was the pedestrian reflected on the glass were also detected. As for the second problem, there was a problem that human-shaped characters were also detected. But in most general cases, it usually works well. Thank you for listening to my presentation.
Actually work. So I'm wondering, how do you select the model for pseudo-label generation? So you select model based on the faster detection performance or the faster tracking performance?
We focus detection performance.
Oh. The question about calculation type is compared to baseline, how much performance you get applying all the facts of tricks. And second is which tricks you think are the most helpful in using?
Do you mean baseline performance? Our method?
So the first question is how much performance boost you get applying all your tricks compared to baseline, where you only train on synthetic data. The second one is out of all the tricks, which one you think is the most powerful?
I think our baseline performance is 58 HOTA, and we apply cross-domain sampling. Then we achieve around about 60 HOTA.
What's the later part? Like which trick is helpful ones for you?
I think store labeling in more 17 train set.
Maybe I have a question. So you mostly focused on object detection. Did
Yeah.
you consider also focusing more on the data association part, like perhaps using appearance somehow, or more tracking specific?
Great question. But as you know, MOTSynth dataset is very large scale dataset, so we need a long time to train. So we have not enough time. So we focused on improving object detection performance, then just apply tracking by track. Yeah.
Okay, thank you. I think then we move to the next speaker. That's fine.
Great, nice work. So the next award winner I'll be handing out virtually. You didn't do that last time over there, maybe. The overall award winner for the challenge goes to SD Tracker, synthetic data-based multi-object tracking. This was by Yingde Guan, Xingying Feng, Huiying Cheng, Hu Du, Ting Li, and Min Wang.
Can you hear?
Yes, just a second. Okay. Okay, I think you can start now.
Okay. Hi, this is Yingda Guan from Systems Research. I'm going to introduce our work, SD Tracker, synthetic database multi-object tracking. Next, I will introduce our work in following order. First is the motivation, then the method and experiments in the detection and the tracking part, and finally a conclusion. First of all, why we need the synthetic data? It is necessary in many scenarios. For example, in crowd-scenes, labeling is expensive and time-consuming. Data of special scenes is scarce. Data collecting may violate privacy policies and so on. Then let's consider how to use synthetic data more effectively. When real data is not available, based on the idea of domain generalization, the source domain needs to be augmented as large as possible to cover the target domain. When real data is available, domain adaptation can be used to bridge domain gap. Also, self or semi-supervised learning is a practical method to improve the generalization abilities over the target domain. Next, I will describe our detection method in detail. When we have no access to real data, we start with domain generalization, which is implemented in 2 steps. In the first step, domain randomization ensures that the neural network can see sufficiently diverse data. Second, we further enforce pyramid consistency loss across different stylized images from the same sample to learn domain invariant features. In domain randomization, the key is diversity. We map the synthetic image to multiple auxiliary real domains from ImageNet when training. when we do style augmentation, it is important to generate out-of-domain data efficiently. At the same time, we must pay attention to data safety, so we choose cycle GAN, whose cycle loss can suppress noise and distorted semantic information from source image. After backbone and feature pyramid network, in ROI head, classification and regression loss of the styled image are also involved in backpropagation to improve the network's ability to detect out-of-domain data. In addition to the vanilla ROI head, we add a consistency head. Consistency loss help model to learn invariance with data from different domain. It is proven that using the mean of different level feature as target can help the network to fit more easily without affecting the optimization of the detection branch. It is worth mentioning that the consistency head is applied only during the training process and doesn't increase the inference time. When real data is available to further improve the generalization of the model to the target domain, we use the model trained on synthetic data to generate a pseudo-label for the unlabeled MOT17 train set. The threshold needs to be determined carefully to ensure the final performance. We apply proximal policy optimization, which is noted as PPO2 algorithm to search for thresholds that maximize MAP. In PPO2, we initialize a set of mean and variance, get some thresholds by sampling, then we train the model with the pseudo-labels filtered by these thresholds and update the mean and variance according to the MAP. After several rounds, we get the final threshold to retrain the model. We search for each sequence separately due to the different confidence distribution. To simplify the search process, the threshold is fixed for the whole schedule. The bottom line is a visualization of our pseudo-labels. During training, we also adopt other tricks for general optimization. We use multi-scale train, test time augmentation, long schedule, and with pre-trained by BYOL. For small objects, we use large resolution and small anchors. We use WBF for ensemble. To maximize the effect of ensemble, we use different network structures and algorithms. For example, CNN and SWIM, anchor-based and anchor-free. To further enhance the diversity of the data, we use multi-types of data augmentation, include weather, blur, noise, and digital as shown in figure. The final results of detection are shown in the table. From the results of model 0 and model 2, the effectiveness of domain generalization can be demonstrated. Comparing the experimental results in the third and fourth rows, we can find that semi-supervised learning can improve the performance significantly. Due to the time and computing resource constraints, the detailed ablation experiments are not completed, which will be left for future work. The red bottom is a visualization of our model. Next is the tracking section, which is based on backtrack with some upgrades. Due to the mismatch of the annotation formats between MOT-synthetic and MOT-17, the model trained by detection framework can only predict clip box, but the ground truth of the test set is full box. Clipped bounding boxes affect the accuracy of the tracker. So we use full box estimation to complete the clip box. The method is shown in this function where YT and YB are top and bottom web coordinates of a bounding box. The data to fit this function are extracted from one of our model's prediction on a random frame. We also raise the confidence score for near border detections so they can participate in the first round of the bad-trick association, confirm a newborn track. For dynamic sense, we apply the NSA camera filter and the ECC camera motion compensation. For static sense, we implement a trajectory estimation method to merge the tracks belong to the same ID. For lost track, we estimate a trajectory first by velocities, then we find the closest box by box center distance. If this distance is lower than a fixed threshold and the corresponding track satisfy the certain similarity constraint, for example, box area and lost time, these tracks are set to the same ID. After that, another interpolation is applied to fill in the lost frames. This merging enables our submission to have a very high IDF1 score, which reaches 77.2. Here is the visualization. For better interpolation, we extend the track buffer from 30 up to 90 for slow-moving scenes. We operate the Gaussian smooth interpolation to generate a smooth trajectory and remove very short tracks, which is less than 10 frames. The final results of tracking is shown in table. We use grid search to find the optimal hyperparameters on MOT17 training. As we can see from the experimental results, dynamic and static scenes require different approaches. Model ensemble, full box estimation, and interpolation increase performance on both static and dynamic scenes. Motion compensation boosts the dynamic scenes results by a large margin. The proposed track merge technique can notably help static scenes. Finally, we conclude our work. The proposed approach designs a domain randomization module to generate diverse out-of-domain images from a single source domain. A consistency-based strategy is used to get models to learn environmental representation across different domains. Proximal policy optimization additionally enables to obtain high-quality pseudo-labels when using MOT17 training set. SD track also makes several upgrades to the popular beta track, increasing its robustness when using detectors training with synthetic data. The method achieves hold time 61.4 without labeled real data. That's all. Thank you for listening.
Thank you for your talk. Do we have any questions?
Question related to errors that's specific to synthetic data. Last team mentioned that there are errors such as detecting reflections that's very specific to using synthetic data. Do you guys observe similar errors that on your model?
Were you able to hear the question?
I can't hear clearly. Can you
Maybe
send
you
the question to the chat and I will reply?
Hey, thanks for the presentation. So my question is more about errors you see specific to the synthetic domain. Last team mentioned that they observe detection on reflection from glasses. That's kind of very specific to using synthetic data to train their model. I'm just wondering if you guys observe something similar on your model.
Yes. Static person on bicycle and reflection, our model can detect.
Okay, thank you for your answer. Maybe one last question. Is there anyone in the audience? Yeah, okay.
Hi, thank you for your talk. I have a question. Did you monitor also the performance on MOTSynth or just on MOT17? Because I'm interested to see if the unsupervision on MOT17 impacts how the unsupervision impacts the synthetic part. So yeah, my question is, did you monitor the performance on the synthetic part, on the synthetic data?
You mean the hotel use only synthetic data?
So your metrics are obtained on MOT17, right? Because you were interested to see how well you were performing on real data. But did you also have metrics obtained on, let's say, in the MOTSynth test set?
We can achieve 58.3 HOTA when we only use synthetic data.
Okay, thank you.
Okay, thank you for the talk. Let's thank the speaker once again. Okay, so now we have the lunch break, and we'll be back at 1 p.m. With more talks from Professor Jitendra Malik and Gulvarol and Kate Sanko. So yeah, and at the end of the day, we'll have the roundtable discussion. So yeah, I really recommend you to come back after lunch. Thank you. Okay, I think we're gonna start. Yeah. Okay. So now next we'll have the talk from Professor Jitendra Malik. Jitendra Malik is currently the Arthur J. Chick Professor in the Department of Electrical Engineering and Computer Sciences at UC Berkeley. In 2018 and 19, he served as Research Director and Site Lead of Facebook AI Research in Menlo Park. I think everyone is familiar with Professor Malik's research. His group has worked on many different topics in computer vision, computational modeling of human vision, computer graphics, and the analysis of biological images. Several well-known concepts and algorithms arouse in this research, such as anisotropic diffusion, normalized cuts, high dynamic range imaging, shape contacts, and RCNN. He has mentored more than 70 PhD students and postdoctoral fellows. He will be talking about tracking people with 3D presentations. Whenever you're ready. Yeah, let me check something very quick. Okay, perfect. Yeah. Thank you very much.
Okay, what should I use the return? This one, right? Yeah, this should work. This. Okay. I think this should work. Okay. Hi, everybody, and it's okay if I take off my mask. I think we have a distance here. So, yeah, let's get to this. So this is joint work with Jatushan, who's there. George Pavlakos is also there. They are sitting in the third row. So if anything it gets very difficult, I'll ask them. And Anju, who's not here, but and myself. And this is a line of work which we have been doing at Berkeley for several years, which have to do with analysis of images of people. Okay, so so this is the theme of the work. So the theme of the work is to track humans. That's a very old and classic problem, but we want to do this with, so it's PH. So P is for prediction, H is for humans. But what is ALP? A is for appearance, location, and pose. So 3D appearance. 3D appearance means that the appearance of the triangles on every part of the body. So a triangle on the torso, what color is that? A triangle on the face, what color is that? That's what we mean by appearance. A texture map of the whole body. Location, what do we mean by location? XYZ. Okay. Traditional. Okay. Pose, what do we mean by pose? Pose means two aspects. There's a camera, but then there's the articulation of the human body. So this is the whole enchilada. So the goal is you're looking at a human, even though the human is in the 2D frame, we have lifted the human into 3D in terms of pose, appearance, and location. Okay. The And then you can see that we are doing this over time. Okay, it's a video, so you're doing this at every frame. And our claim is that this is the right way to do tracking. I mean, was not the way to do tracking some years ago, but I think we have now the kind of compute, the kind of models, the kind of data that we can hope to do the switch from 2D to 3D techniques. So if you look at the data, this is what the data look like. I mean, if you look at those of you who worked on MOT challenge, that's the kind of data we used to have, right? So the typical setting of how did tracking arise?
On Zoom, we're still seeing the cover slide.
What?
On Zoom, we're still seeing the cover slide.
Okay. Okay, maybe
it also doesn't look like presentation mode on Zoom.
So maybe you need to change something on the Zoom. Okay, just stand by.
Thank you.
Not sure actually. We did this already.
Yes, Zoom you have to share up here.
If you just share screen? Yeah, no, but the problem is that slides were not getting updated.
Okay, no. Okay, like this. So first you present. And then you share on the screen. Yeah. Should be this.
Yeah.
Looks good.
Okay, somebody said it looks good.
Yeah.
Good.
But then you cannot see. Does it still look good?
Yes, it does. Thank you.
Okay.
Okay.
Yep, it changed and we're seeing motion. Thank you.
Okay. Okay. Everybody in the room is happy. Okay. Everybody on Zoom land is happy. Somebody say yes. Okay. Good.
Yes.
Okay. So tracking tracking kind of arose once we started to have these cameras that we could put everywhere, and they were typically in settings like that. So a human was very few pixels, 20, 30 pixels. And in that setting, it only made sense to do 2D tracking. And that's what people did. And our thesis is that that made sense then, but it no longer makes sense now. Person tracking has been 2D, but why? And this is what the data look like. So this is just making the same point. Typically, it was like surveillance video. And there were people developing techniques for human reconstruction in 3D even 20 years ago. And that's sort of slightly hidden for you, but we'll make it more visible. But this is the data now, right? Look at the resolution of the videos we have now. Okay, these are the videos you see on television, on Netflix. I mean, so why should we stay with the techniques which made sense with the data of 20 years ago? We can do better. Okay. And this is what, and there were ideas for doing 3D reconstruction more than 20 years ago too. I mean, this is actually 24 years now. This paper by Chris Regler and myself, which we published at CBPR 1998, which was trying to do reconstructions of Muybridge sequences. It was very hard. We had to do it with 3 frames, and it basically just worked for the 2 sequences, right? It was not a robust technique. Okay, this is what we can do now. Okay, so this is work from our group. This is Anju Kanazawa's work on HMR, which is code you can download and use that for reconstruction, but also other groups have worked on this. So human 3D reconstruction from a single image is not like totally a solved problem, but it's within 10% of being a solved problem. Okay. And we can build on that. Okay, so now let's get into the technical reasons why 3D tracking might be better than 2D tracking. So in 2D tracking, think about occlusion. Okay. The person behind has disappeared, right? Okay, so this happens if you think in 2D, then the masks overlap and now you have trouble, right? In 3D tracking, suppose you are keeping track of the 3D position. This is what happens. No occlusion, right? In 3D space, two people can't occlude because they are in different parts of space. Their volumes cannot interpenetrate. Okay, so that's an obvious reason why. I mean, occlusion is no longer a challenge if you are reasoning in 3D. Occlusion kills off the pixel, but in 3D, everything is always present. So they don't overlap in 3D. Second point. Think of this person. So follow this guy, right? This, so focus on that player and keep following this guy. Okay, so this is what it looks like in the bounding box sense, right? So people do a lot of the tracking, 95.9% of the tracking is in terms of bounding boxes. So look at this fellow's bounding box, and his bounding box, and his bounding box. So it appears to be changing all the time. It's becoming big, it's smaller, shrinking, blah, blah, blah. Which means that your matching algorithm has to be robust to those changes, right? Okay, and then, so you have a combination of this change in appearance, because this bounding box is shrinking in size, and of course you have the occlusion phenomena. Okay, now the person is still the same. If you look at the person the right way, the person is still the same, right? I mean, if you refer them in the following sense, take the person's body, okay, and now consider the color of any part of the person's body. So this guy is wearing a t-shirt, so his arm is just skin color, so that's a certain color. On the body, it is constant. His skin is not changing from pink to yellow to green every frame. It's the same. The pixels are changing from pink to yellow to green every frame. The skin doesn't change. Look at his t-shirt, right? It's got white and black stripes. At a particular part of your body, like here or here, it's the same color throughout. Okay, the pixels change. The colors on the body do not change. I mean, they will change a little bit, like if you're wearing a flowing skirt and the skirt sort of billows about in the wind, yeah, but that's a small effect. The first order effect is that the appearance of any part of the body remains constant throughout this. I mean, people, of course, change clothes, but they don't do that in the middle of a tracking sequence. Okay. So 3D appearance is invariant to viewpoint and pose. Okay, so in summary, 3D location is more separable than 2D location, and 3D appearance is invariant to viewpoint and pose. So the beauty is, if we can lift to 3D, and that's a very big if. If we can lift to 3D, tracking should kind of become trivial, because tracking is about matching, right? So there will be some tracklet that's being built up, and then you are matching to the detections in the new frame. And if you have very, very good descriptors, which are pretty much the same on both sides, then matching is easy. It's just, okay, whatever is the closest, you match and you're done, right? But if you look in pixel space, they look very different. If we look in the 3D space, they are basically the same. So that's it. It's really a trivial idea. I think it's not an idea which would not have occurred to people, 20 years ago, 30 years ago. But what we can do now is we have the technology. We can do the lifts to 3D. And if you just apply that sensibly, the rest will follow. So let's just take you through that. Okay, so we have an input video where we detect people. I mean, detection also, we have a technology, use mask RCNN. It'll detect all the people for you. Okay, we extract features. I mean, okay, this is basically done by whatever is your machinery for doing the 3D lifting. And then we are going to do some spatio-temporal aggregation. And note that for each of these, I've shown this rectangle with 3 parts. And the 3 parts are essentially referring to appearance, pose, and location. So we are always going to produce appearance, pose, and location. And then the output is tracklet. So tracklet means one person over time. But that one person over time is 3 components: appearance, pose, and position. Okay, so what are the, 3D pose, 3D location, appearance, right? Those are pulled out. So by pose, I mean 3D pose, not in terms of joint angles, not in terms of 2D locations of the key points, I mean, which you could do with open pose, but we are actually meaning 3D pose here. 3D location is just like XYZ. Actually, we use a different encoding of Z. We use 1/Z, which is called nearness. And it turns out that the error characteristics are more naturally captured there. And appearance is going to be by a texture map. Okay, so how do we do appearance and pose recovery? So there is this HMR algorithm we published a few years ago with Anju Kanazawa is the first author, and that gives pose. And in recent years, it's been augmented that to give location as well. And what's the intuition there? Okay, a 10 pixel person versus a 100 pixel person. Okay, the person is the same size. So if the 100 pixel person must be 10 times closer. That's it. I mean, basic idea, which you just have to do a little bit of math, and that takes care of that. Appearance, because when you are running HMR, you are essentially extracting out the shape of the body and you have the correspondences. So what you can do is to train another head to that system, which says, what's the texture corresponding to triangle 35? And triangle 35 is the triangle on this region. And maybe triangle 47 is the triangle on the hand, and so on. So you can pull out the appearance of different parts of the body by the same process, which is trying to do this lifting to 3D pose. Okay, so that's the appearance. So it's showing you some kind of this is a texture map, and the different colors here are it's like a UV mapping, because you use a UV code for the different locations on the body, and this is the colors of each one. Okay, and then spatio-temporal. Okay, so now we use a transformer for this part. But basically, what you're doing is a Hungarian matching, right? The Hungarian algorithm is beloved by all people in the tracking literature. You have some it's bipartite matching, and we're going to do that bipartite matching based on some distance, and that distance is going to be based on difference in appearance, difference in pose, difference in location. Okay, so that in fact we can be even smarter. We don't have to match. Let's say take location. We don't have to match against the location in frame t-1 with the location in t. We can predict what the location should be in time t. We can predict what the pose will be at time t. We can predict what the appearance will be at time t, and then use that for matching. In the case of location, how should it go? Just linear extrapolation, which for a short range, everything that will work fine. Pose, we rely on our system. It's a trained prediction algorithm for predicting the pose. So we rely on that. And for appearance, what's the prediction? Well, it should be the same. I mean, the person hasn't gone and changed clothes in the last 1/30th of a second. So the appearance just remains the same. And then we do the Hungarian matching. Now we attach that frame to the tracklet. So the tracklet has become 1 frame bigger. Just continue. Okay. Okay, so pose prediction is based on a previously published algorithm. We have these papers, HMMR and PhD, which sort of developed the technology for how to predict pose from previous frames to the next frame. And there are later versions of this using transformers and so on. Okay, so that predicts the frame at T. So we'll do a detection in T+1 and try to match it against the prediction into T+1. And then once you're matched, then you continue. Okay. Location prediction is just linearized in 3D. We do it in 3D, not in 2D. I mean, typically a lot in the tracking literature, there's proper extension, but in 2D. But in fact, 3D is better because often people are moving in space. And so you should really be predicting the straight line behavior is in XYZ space, not in 2D space. So you just predict and then match. And appearance should just remain the same. So so that's the texture map, and the texture map in the next frame should be the same texture map. And how are we going to change it over time? Well, that's during tracking, we are tracking a person over time. So over time, more and more of the body of the person will become visible. So initially, you just see my front, but then as I move, you see my side, and then you see my back. So what's happening over time is more of the appearance of the person is being revealed, and it's being built up in the HMIR representation. And of course, there'll be parts which will be unknown, and in the matching, you must take care of that. Okay, so you're just adding up over time. Basically, more and more gets visible. If you see the same thing twice, you just average. Okay, association is just the Hungarian. Okay, so we now have these attributes: appearance, pose, and location. And from a tracklet, which generates a prediction for T+1, and we must match against the actual detection in T+1. And you're going to get some differences. They'll never be zero. And so what you need to do is to have some weights for these. And these weights are learned. So the learning problem is just these 5 numbers. Okay, it is not learning all the parameters of a neural network. We did do that for the 3D lifting function. That had to be trained on data sets of lots and lots of images of people. But the tracking behavior became easier because here we had to learn these parameters for the distance function, because by design in the 3D space, distances are much smaller. So I mean, since the topic of this workshop is about synthetic data and so on, synthetic data is still very useful because it can help us train these algorithms for pose recovery in unusual poses, or building motion models for how the pose will change over time or how location will change on time. We still need to do that. But the tracking part is much easier. It's the predicting human dynamics, which is where the action is, which is, I think, the fundamental scientific problem. Okay, and these are just more pictures. So you have pose, appearance, location over time, predicted into T+1, matched with what the detections were in T+1. This part is done with the Hungarian. And now we just get into results. And so we have some data sets on which we have compared, and the usual metrics, ID switches, MOTA, etc. And basically this algorithm just does better than every other algorithm. And I never like to spend time on these tables because they're always somewhat boring. The people who care most about them are the previous people who worked on those algorithms, but you can read them at leisure. I think the conceptual work is what I already showed you. And then these are examples where we are doing the tracking and tracking with competing approaches. And I'm sure this shows that our algorithm does better than other people's algorithm, but you expected that, right? And that's what all the demo videos of everybody shows. But yeah, I'll use this to, by the way, indicate a technique that we are using for visualization, which I think may be helpful to everybody. We can show the reconstruction overlaid on the whole body, but then the original pixels disappear. What's happened here? Oh, okay. But so what we do is we just put this head mask, okay? And what you should see is that the person, what's happening? Okay, so more examples of people being tracked. I think the interesting part is when people get occluded and then they get reappear and then they reappear with the same color. Okay, this is, I think, a standard sequence, and you'll see, focus on any person you like, and then they disappear, then they reappear with the same color. Because remember, in this 3D tracking, nobody ever disappears because they get occluded, but the tracklet continues, so that we just keep extending the tracklet and keep matching against detections. And at some point, there is a detection which matches, and now you've resumed normal business. So nobody ever dies, right? They're just, they eventually leave the frame, but when they are in the frame and they are occluded, the 3D identity is always there. There's actually a prediction. We can, in fact, reconstruct what they would look like. We know their pose, we know their appearance, we know their location. It's not out of sight, out of mind. Out of sight, but very much in mind. Okay. And I'll end here. And yeah, we'll make the code available and everybody is welcome to use everything. Yeah. Oh, yeah. Yeah, no, so we have the dynamics. I mean, it's essential. We have the dynamics. Now the question is whether you capture the dynamics in 2D or 3D. We have chosen to do it in 3D. Yeah. And in some ways even easier because there is more homogeneity in 3D. See, when I can walk at the same speed in different directions. In the image, it will look different, but in 3D, it's the same behavior. Now, humans, of course, learn that over time, so it's not, we're less bothered by it than we should be. But the natural dynamics of human behavior is in 3D, right? I mean, Newtonian physics is in 3D. Yeah. So and I think that's a question which will be debated forever. But I'm arguing here that in the past, the problem has been that if you don't have a robust way to lift to 3D, then you get screwed at that stage. And then even though your 3D algorithm is cleaner and more elegant, it just doesn't have good input. So you've lost in the first stage. But I'm arguing that our 3D technology now is good enough for humans that that makes I mean, the whole point of this is it makes tracking really simple, because the hard work is being done in lifting to 3D.
Thanks, for fantastic talk. Two questions very close. Do you think that camera calibration or real information about 3D can be useful now?
Yeah, I mean, more the better, right? I mean, if you know the XF, so that's better. Yeah.
Second question is about the prediction of the motion. Of course, if the frame rate is acting up, with just a linear prediction is good, but all the work about not Kalman prediction or Uber prediction, classical phase or whatever, that try to predict better the position and speed
so in a way, I mean, I subscribe to that, the Kalman filtering tradition. Now, the thing is that when we did predictions in 2D, there was a whole lot of noise which was added, which was like due to the bounding box changing or whatever, which still had to be captured in that system. See, I mean, one man's noise is another man's signal. Okay. So I've just converted it to signal, because if I model it correctly, it is signal. So a lot of the clever technology from 20 years ago, the particle filtering business, was necessitated because the image tracking, there was not that much continuity and there was so much. So all that had to be considered as just Gaussian noise. And here, all that is removed. So now even the more simple approaches work. Yeah. No, I mean, I think what is implied by the approach is that if you have a 3D lifting algorithm, then you can just take this machinery, but that may be a challenge, because not for every category do you have 3D models of the type that you can do the lifting. And humans are, because that's a category of great interest to us, so we have developed those models. Now, whether they'll be there for salamanders, I don't know. Yeah. So that's should be done. Yeah. Yeah. No, of course. I mean, this is just people, but it's not people in isolation. People should be with objects. Yeah. Sorry, at some point, I think we run out of time, but okay, let me answer there. Well, the modular clothing, I think that the body can be reconstructed quite well, but clothing, if it is not rigid, like loose skirts and so on, maybe like ballet dancers, they have skin tight clothing. But I think with loose clothing, it will be more of a challenge. But I mean, that's what I mean, that problem can also be solved. I think that this provides a very good starting point, right? Because you have isolated the pixels corresponding to a person and you have a rough idea of the pose. Fair enough, but okay, so I'll wave my hands. Okay. In the sense that, yeah, there is some change. As I said, the clothing, there's, the skirt can shake, lighting is there, but that's the part which I'm going to call noise. So I've certainly advanced a lot in terms of what is signal and what is noise. So, and there's some averaging going on in terms of the appearance. So the texture map is not fixed, but it drifts slowly to evolve with the lighting. Yeah. Okay, so right, so we are biased towards adults, but the difference, so there is an answer to this which we haven't fully implemented. The answer is that actually when you recognize a person, we can actually know whether they are an adult or a child. Humans can, from the pixels, because of the issue of the anthropometry, right? We know that like a child's head is much bigger relative to the body. We are able to recognize from the appearance of a human whether they are a 5-year-old or an adult, and that technology should essentially help make this problem solvable. We haven't done that yet. Our method will basically, for children, we make mistakes. Okay, thank you.
Yes.
Oh,
no, it's for the Zoom before. Or after. Oh, yeah, exactly. It's the... Sure. Yeah. Also, mute yourself.
Video even?
Yeah, maybe I quickly introduce you. Okay, so we're having now our next talk by Gul Barol. So Gul is an assistant professor in the Imagine team at called the Paris Tech. Yeah. So previously she was a postdoctoral researcher at the University of Oxford, working with Andrew Zizerman. She obtained her PhD from the Willow team of INRIA Paris at the École Normale Supérieure. Her thesis was co-advised by Ivan Laptev and Cordelia Schmidt, and received her the PhD award from Elise and Afif. In her PhD, she spent time at MPI, Adobe, and Google. Prior to that, she received her bachelor's and master's from Bogazici University. Her research is focused on computer vision, specifically video representation learning, human motion analysis, and sign languages. So yeah, we'll take it yours.
Thank you. Well, thanks for the invitation and the introduction. Let's see, I'm a bit shorter than Jitendra, so let me adjust that. So I hope it's fine on the Zoom side as well. So yeah, I have some background in synthetic data generation, which I believe is the connection to this workshop. But today I'll be talking about 3D human motion synthesis, which is another source of synthetic data. So I'll make some connections. But let me start by actually a bit of advertisement about our lab. And there are actually a few people in the back sitting from this beautiful group, and it's called Imagine. We are growing, we're about 30 people. And if you want to meet some of us, about 15 people are already at CVPR, so go talk to them. And if you want to come visit to beautiful Paris, please contact any of us. So yeah, so diving into the topic of this workshop. So why synthetic videos of people? Good old motivation is that it's very cumbersome, even expensive or infeasible to annotate a large scale data for training. But actually there's a new kind of increasingly important motivation is that there's the privacy concern, especially when you have people, their faces, their bodies, and GDPR like restrictions on the data usage. So synthetic data is becoming more and more important, not just because of annotation issues. And there are certain ways of doing that. A typical pipeline is which I was involved in during my PhD is using graphical rendering engines. So you have some assets on the left, and your goal is to render some RGB image given the 3D assets. And then you have for free a lot of other things, ground truth, pixel level or 3D level that allows you to train neural networks. So in this talk, I'll be mainly focusing on the motion capture resource that allows generating synthetic data, because there's the clothing, camera, and body shape that are arguably easier to augment, but the motion is typically from a motion capture that comes from some recording in the screen studio that's limited, that has certain number of hours, that depends on how many actors you hired and how long you recorded them. But ideally, we want this to be infinite or be able to control the generation to be able to scale up the synthetic data generation. I think my computer is a bit slow, so bear with me. Okay, so that's the key issue with synthetic human rendering. How to obtain, like, scale up the number of data we can have and the motions and the poses and the variety in a way we can also control, not just randomly generate things, but in a controllable way. So yeah, the space of human motions is super rich and complex. They can move in all sorts of directions, and they're articulated. Yeah, I encourage you to check out the arts and even GAN generated arts by Scott Eaton. I think he's recently moved to Facebook. I'm not sure. Anyways, anyway, so my goal in this work is to combine match semantics and motions together a bit to be able to synthesize sequence of human poses in a controllable way, in a realistic way, and then in an infinite way and diverse setup where we can sample from a distribution, for example. And there are certain different ways to do that. For example, you can imagine here, there's the concept, the action kicking as input, and the output, we want to generate a short sequence of 3D human poses, which we call action condition motion synthesis. The other way around has been studied much more. It's just given the right, the 3D action recognition. And then you can also imagine typing preform text, a person is kicking, and do the same. So that would be text condition synthesis. But you can also type as detailed as you want. So if a person raises the right leg and performs a slow side kick. So this could go infinitely many hierarchical levels. And why do we want to do this? Again, motion capture is limited and we want to have infinite data, but there are other motivations, of course, to have an interpretable motion space, which can be useful for other tasks. But today, yeah, I'll make the connection to synthetic humans. So because that was what I've been working on in my PhD, to generate the pixels themselves without worrying about the motion capture aspect. And yeah, the nice thing is that it comes with the ground truth. Not sure if the video will play. So you have for free the pixel level ground truth, especially for depth estimation. It's not something people can annotate manually. Maybe you can have Kinect, but for segmentation or optical flow, this kind of tasks, it's very advantageous. So people have used this kind of data for different tasks, but mainly for low-level tasks such as body part estimation, pose estimation, optical flow. But what about if you want to do action recognition by training on this kind of data? So nobody has attached a label, a semantic meaning to these videos. So we asked this question to ourselves for quite a long time. And eventually, one solution was to run motion estimation, actually HMMR, what Jitendra showed earlier. We run it on action recognition datasets. Okay, if you run it on YouTube videos, maybe it doesn't turn out as nice as in the papers, but it still captures the semantics, even if it's noisy. So these are some examples from Kinetics dataset, which is already quite challenging, and it does a reasonable job of capturing. Like if it's stretching arm, it at least has the arms around, maybe it's moving a bit jittery. So what we did is to extract motions in an automatic way and attach the labels to them so that we could train action recognition on synthetic data, apply it on real data. Although these data sets are relatively simpler, so even on Kinetics, we took a subset, for example. Right, so at the time, the goal was more like train on frontal view, test on side view. So that was another advantage of being able to generate 3D synthetic data from 3D, so you can rotate them around. I'm not going to show this work so much, except this plot, where the conclusion is that so the x-axis is the number of sequences per action, so the amount of data, and the y-axis is the performance. Real is the red curve, which is training only real, and synthetic plus real also always better. But this curve doesn't saturate at all. Even if you have 200 motions per category, we can even go further and it will benefit from that. And we tried a few things like adding Gaussian noise or cutting, pasting motions to increase the diversity. It was very basic and it always helped. So the question was, can we generate human motion so that we go a bit further right on this x-axis? And when we look at the literature, it's a bit disappointing. So people have been looking at future motion prediction for a long time, also for human motion synthesis from scratch also, but it was mainly walking, running, or any unconstrained synthesis. So we wanted to be able to control by saying, give me a motion from this action category. And when you look at that, there are some recent works that generate conditions on music, text, and action. So that at the time there was a 2020 paper with some promising results, but what not sufficiently good. So we thought we will just improve that. So I'll be talking about these two works basically on action condition and text condition motion synthesis. Both works done by Matisse, and he's actually sitting in the back. So if you have any detailed questions, that's a perfect moment to catch him. So the first work, we call it ACTOR, action condition human motion synthesis with transformers. So this is a joint work with Michael from MPI. So the goal is, as I said, given an action category to generate this short sequence in 3D. How do we do that? Again, going back to the motion estimation methods from RGB videos, We apply it on action recognition data sets. We get the paired data, although they're very noisy, the motions. So they look like this, for example, on a ground truth. So this, a bit jittery, but good enough. And the scene is also quite simplistic. So it gives a data set for throw and motion, the corresponding motion. So we do this over 3 data sets, around 10, so 13, 12 actions, or the maximum was 40 actions. So it's not large scale at all, but it's a start. And I'm not going to go into the detail, but it's basically a VAE, variation autoencoder, that has both for the encoder and the decoder a transformer. The main new thing here was actually to make it a VAE by adding this mu and sigma token, so distribution parameters of the Gaussian, that summarizes the entire sequence into a single representation that made actually very smooth and realistic results. And then there are several losses to make the output a simple representation, so that we have the parametric representation as output. Yeah, the key difference from previous work is that it's not autoregressive. Also at the decoder, we generate the whole entire motion from a single shot, a single vector, the Z that we sample from mu and sigma. And the action gets in as there's a learnable token, also one for each action that allows us to condition. Let's see some results. I think that's enough for the architecture. So here's some example for pickup, high knees running, punching and lean lifting, left stretching. So although I have some text for them, they are actually some symbolic action categories. So there are 40 of them, 1, 2, 3, 4. So the model has no notion of text. Spinal stretching, front raising. For those on Zoom, these, if they're not playing fine on your end, they're on my webpage. And then we were also investigating whether every time we sample a random one, are they different enough? And the nice thing is that there is some, for example, for kicking, we need to move the leg. So there's not much diversity you can do there, except the angle maybe, and is it the left leg or the right leg? But the degrees of freedom is more on the other, so the hands can move other ways. It doesn't matter for the action. So this is the irrelevant body parts can move, then create the diversity. So yeah, another boring table I'm not going to show, but it basically just to say that the metrics, the evaluation, as always for generative models, is a challenge that we're constantly discussing about. It's not perfect, so we'll rely on human studies also, but it allows us still to do some automatic quantitative ablations. And one of this is one of the main takeaways of our playing with the architecture showed that this non-autoregressive was the key to make it state-of-the-art, because the autoregressive transformer version was not very different than the GRU. It was more or less the same. And in terms of comparison to previous work, it was considerably better, but let's show it more qualitatively. So the previous work is the one on the left, action to motion. It generates only skeletons. It's quite jittery, it's frame by frame. It's using a GRU. And ours didn't have any of the problems. Another example. Yeah, and it's not cherry picked, in case you were wondering. Impressive. Okay, of course, there were parameters that matter. And actually it was in some funny ways we found out, like Matisse is running on the cluster with a large byte size, and then the cluster is down one day, and then he runs it on his own machine with a smaller byte size because there's a smaller GPU, and it turns out the byte size is important. So there are lots of ablations in the paper, and if you want to reproduce, the code is online. So another interesting experiment, because the advantage of using transformers this way was to be able to generate variable duration. So at test time, you can ask the model, I want this many seconds of this motion. But if it has never seen that long of a motion, it's a problem. So what we do is we train with variable duration at training, and then at test time, there's a maximum it can also expect. But the thing on the right, the variable duration, didn't work out of the box either. So what we found out that we should first train and warm up the layers with a fixed duration, for example, 60 frames, and then move to randomly between 60 and 100. That made the model more robust to generations of variable durations at test time. All right, so for example, if we want for the same action, for the same latent space, 40 frames to 100 frames. So if it's too little, it will just cut the action. And then if it's longer, it will make it slower. It will find its way. A few use cases we found out as a side product actually was really nice to see that even if you get the motion from HMMR, which looks like this on the left, it's very jittery. You just encode and decode through our motion embedding, and it just gets denoised. So another example. Arm circling. The danger is that the model has no notion of whether this is really noise or is it a little subtle motion. So we can over smooth things sometimes. And then we thought, why not use this for action recognition? It was a bit disappointing. The same experiment of synthetic plus real, which is the green one, didn't really improve over the orange one, real only one, that much when we were on the 100% of the real data regime. It improved when we were reducing the number of real data. It's partly because the test set is jittery and the real training set is also jittery, and we're adding things from a different domain. So there's still, even if it's 3D, there's always this domain gap. But if we also denoise the test set, then we got an improvement. But I think if we take this render synthetic data, then we will see the benefit then. All right. Some interesting examples of interpolation. So you can also generate new samples by interpolating between existing ones. Some failure case again about using such automatic HMMR-based method is what I think here is wipe, but both of them, you don't have the exact 3D distance to the camera because again, we don't know if it's a child or an adult problem. And so because at training time, we have this wrong translation, it also happens at test time sometimes. And we don't have loss to prevent collision, so there are penetrations. And as I said, so it's not clear if this is a noise or a fine grain movement, so turning the neck. Okay, in summary, the key takeaway was that using the sequence level non-autoregressive VAE provides really good results, and then denoising was a side product. But there are certain limitations. One of them is that we don't have these details. For example, the hands are not even articulated, but we do the punching motion. But more importantly, at least for me, was that we are limited to these 40 actions maximum, and we have to have them a lot of data for each of them. So then we thought, okay, let's release this symbolic action category constraint and move on to free-form text. So that's the second part. Also by Matisse and Michael in collaboration. And the goal here is given text, so a human walking in a circle clockwise, to generate motions, so multiple of them, not just one. And here in this case, showing a skeleton, but we can also use a simple body model. And there it's a similar architecture, except here we are using text. So there's a bit of a pre-trained language model on top of the text before it goes to a text encoder. And then it's another kind of a VAE with two branches. I'm not going to go into detail. You can check the paper. But the decoder part is pretty similar to actor, only single embedding. And it's also non-autoregressive. And unlike the previous work, which I'm listing below, it can generate multiple motions instead of a single, because the previous works are considering only, given the single text, only a single motion in a deterministic way. But we know that there are ambiguities in text, which can result in multiple motions that can correspond to the same. So we do it in a probabilistic way. And a few comparisons to existing works. Oh, they're all playing at the same time. Let me see. Again, the same time. Okay, just a summary, ground truth is perfect. Lin et al. Is, oops. Doesn't correspond always to the text. Language to pose is okay, doesn't correspond always, and it's a bit too smooth. Ghosh et al., they have this food contact loss, which creates exaggerations. So let me play this one. So it's not super realistic, but it has food contacts. And ours turned out quite well, of course. It's better than others. And in terms of quantitative as well. And again, here we also rely on human study to evaluate. Of course, you cannot do this many times. But for our best model, we show them the previous work versus ours and ask them which one is better, which one corresponds better to the text. A person walks in a circle, so they're supposed to click right. And in terms of results, asking about 100 sequences to 100 Turkers, they preferred Temos, ours, 70% of the time compared to the others, and 90% of the time compared to the first work. And we also compared against the ground truth. Of course, they prefer the ground truth, but we're still preferred a bit more compared to the previous work. And in terms of, we asked the same question, which motion is more realistic? So this one, the one I showed you with the exaggerated legs, it turned out unrealistic compared to ours 92% of the time, which corresponds to what we observed ourselves. And here, the nice thing is that we're getting close to 50%, so our motions are realistic compared to the ground truth. And just to show different samples for the same text, a person performs a squat. Here, for example, there are not too many ways you can do a squat, so there's less diversity. So depending on what you type, and the more you type, the more details, it will be less diverse. And then you can interpolate between things. So it's a funny one with walking forwards and a circle. It's the trajectory, which is something in between. All right. So for these both works, there are of course a lot of limitations, a lot of work to do. One is we never care about the interaction with the world, with the floor, with the objects, with other people. So we can condition on the scene and other things as well. And the vocabulary is another question. Even in the second work, the data set is quite limited. It's a lot of walking and not diverse enough to generalize to all kinds of texts. But we still don't know how to transition to in the wild. There is no clip for motions. But then there's also this problem that we can only generate a single thing at a time, but people do multiple things at the same time. We're really good at multitasking, and we don't do only a single thing, we don't stop, and then we just continue doing other things. So we wanted to look at temporal compositionality. So this is fresh from the oven for you. Just a glimpse of some recent results led by Nikos Matis, where we said we want to type multiple texts and it's as a sequence. Sit down, turn left, sit. Another example, kicking with right foot, eat, sit down. It's not perfect, but it gets the gist. And it's relatively smooth between transitioning between actions. And the data comes from Babel dataset, AMAS labeled with language descriptions. It's a quite challenging dataset to train on. And the way it works is almost like Temos, the previous one, except that it's conditioned also in the past every time it generates the future. But yeah, oops. Okay, what is next? As I was saying that there's no clip. Why there's no clip? There's no data set. The Babel, the largest one is, I don't know, 30,000 sequences, so nothing compared to 400 million. And even if you get them automatically from some videos of people, how do you make sure that the text corresponds to motion? Or because the captions and videos, they would describe scene and not just the human motion. So these are questions we're asking ourselves a lot, and I'll be happy to hear any feedback or questions. With that, I'd like to conclude.
there any physical consideration in the method? I mean, if you generate the motion of ticking, then the center of the mass.
Yeah, this if you put it in simulation, it will fall. There's no physics.
Do you have any
Yeah, well, not a concrete plan. It would be great if more people work on it. Yeah.
very nice one. I have two questions. One is for the second talk, you want to check what is it generative text. So do you need like a different data that you wanted to you went and like labeled it or like
That's called KIT motion language dataset. It has about 3,000 sequences that are manually labeled.
okay.
So there's nothing automatic for that.
Okay. So the second question was, why was like some of the pieces are like 3D code, some of them are like simple? The second shot.
Yeah, the second one, because the previous work used just skeleton, we wanted to compare in the same setting. But our method can be plug in, like it can be both for skeletons or simple. But their method was only skeleton.
Maybe open in this question. Like, so I think the last way to borrow composition, I guess, right?
Yep.
So there's also, I think, so I suppose multiple access to the same point of time.
So this is temporal compositionality, what we call like a sequence of actions. There's a spatial compositionality, which is at the same time simultaneously. We haven't looked at that, but that's the next step.
So something that we've seen now is that when you predict motion and for this, sometimes you have any forces and angles that are not biomechanically feasible when you have an angle loss. Do you have any mechanisms to make sure that you don't end up with motion that's not biomechanically for you?
I think because it has trained on, like, I think it learns not to do these unrealistic things once it's trained. So we haven't done anything explicit. Yeah.
You mentioned that it was hard to train on a fixed data set.
Yep.
As the world will have greater impact than the more language models of the regions where this will impact, it be harder for training on English models.
Can you say the last sentence again?
Will it be harder if training on English language models?
English language model.
Non-English.
Non-English.
Yeah.
Um, I don't think it's more like the pre-trained language model, which is the issue. It's more like the data set for training this, the motion text pairs is very long-tailed. It's a lot of walking and then a lot of running and then like other things that are also vague. Like there's a yoga action, but there are so many different poses in yoga and we attach a single word to it. So it's just the granularity of hierarchy of actions, like waving hands versus like raising the hand. That can be described in the same ways, and in the data set they are chosen in an arbitrary way. I think it's just a data issue rather than the language modeling.
So in creating the data, because then most of the data that exists for many languages is scraped and not created from scratch.
Yeah, this is manually annotated data from label data set.
So
the one on the bottom.
To look at creating data sets for those sorts of marginalized languages, we need to look at the quality of what we want to create so that it sort of improves it. Okay.
Yeah, definitely. Any other questions?
I think it was a great talk. So I think one of the key takeaways from our lecture is no autoregressive transformer works the best, I think. But like, do you have any thoughts why this happens? Like, for example, no autoregressive transformer doesn't suffer from balancing gradient or something like that?
Well, there was one issue with the autoregressive one is that, so this is a VAE, right? So you need to encode and decode the same thing and put a reconstruction loss. And when we had it, the frame by frame version, we would encode someone who would wave with the left hand and decode someone who would raise the right hand, because you start from the same position and then somehow it doesn't even reconstruct the ground truth in the teacher forcing version. So we had issues already during training. But at the same time, if it has the entire information about the sequence at a single vector, it's never going to drift. Like it will be smooth. There are all other advantages. The disadvantage is that you cannot make a super long sequence. So that's what we were trying to do with the recursive TEMOS in the last work. Right. You want to set up maybe in the meantime? I'll take. Yep. Yes, I'll take the offline. No, this is yours, right? This is mine. I think it's 4:30.
Sorry?
What time was the panel?
4:30, yes.
I'll come back.
Okay, thanks a lot.
See you.
Really, thank you. Really fantastic. Really hope to see you in Modena if you want, if you have the time to
I
come.
always love
Look, my daughter spent 1 year in Paris
Really?
until yesterday.
How old is she?
She's 22.
Okay.
Okay. Whenever you want, I can come to Paris, but really I'd like to have you to have
Both
a
ways.
talk in Modena.
Both ways.
Thank you very much. Fantastic.
I met your student as well.
Student, a man student, or
I think he left now. He graduated.
Huh?
He graduated maybe. He was in Ellis.
In Alice, it was one of my PhD students.
But then he graduated.
Lorenzo Barato.
Maybe I saw him in Amsterdam. I don't know.
Yeah, Federico Lambi. No, he's in Amsterdam, or two of them. And also Daniele Davide Bati.
No, actually, it was David.
Okay.
Yeah, they're both in Amsterdam.
Yeah, they're both, one in Stockholm and the other one, I think, moving a lot or something.
This group works on problems at the juncture of
Okay, thank you. Thanks. So one of the main problems facing synthetic data field is domain gap. Domain gap is when synthetic data, like models trained on synthetic data, do not often perform well when they are deployed in real world. And while domain gap does happen with different versions of real data as well, but with synthetic, we have the control on how we create synthetic data. So in some researchers argue domain gap can be divided into two components. One is appearance. The second is content. Content gap is the discrepancy or distribution gap between synthetic and real data in terms of number of objects, pose, position, count, geometry, etc. And appearance gap is essentially how the two domains differ in appearance, which includes color, texture of objects, sensor noise, and global illumination. So For the purpose of my talk, I'll mostly be focused on content gap. So even if we look past appearance gap, we see that synthetic and real data, they differ greatly in terms of content. The content shift is huge. The synthetic data is often very clean. Real world is much more diverse, it's much more messy, and it's more clutter. There's more clutter. So what should we do about it? What should we do about this big content shift? Another problem is that artists, when they create synthetic data, they often spend way too much time in creating more realistic simulations. So for instance, they would spend, addressing photorealism and appearance as like a rabbit hole. An artist really spend a lot of time, manually creating all this content. And the content itself, can be expensive. For instance, GTA 5, took 3 years, thousands of developers and millions of dollars to create. If we were to spend those much resources in creating synthetic data, this lessens the appeal of synthetic data because we want synthetic data to be cheap. So what should we do about it? So the purpose of my talk will be to address this content shift in synthetic data and to focus on techniques that can be used to create synthetic data, in a cheap manner, and how do we scale this problem. So one of the known techniques is domain randomization. Domain randomization is a technique to create large amount of synthetic data. You randomize all the parameters of the scene. For instance, in this example, you randomize the light, the texture of the objects, you randomize the position, pose, layouts of the objects, you add real world clutter as distractors to improve the recognition system. So this has been shown to work well, and a lot of industries have adapted domain randomization technique as a cheap alternative to content creation and achieve similar performance. There are still problems with domain randomization. The problems being that a lot of randomization needs realistic bounds on creation, and many of this experimentation is expensive, and determining these realistic bounds is subjective to experimentation. So it's still not as cheap as you would like. Another paradigm to address diversity and to create content at scale is procedural generation, PG. So using tools like Houdini, artists, technical artists, graphics engineers, they create large diverse content. So creating an additional generator for each object can be expensive. However, once we create those generator, we can really truly scale to hundreds and hundreds of assets, not having to model each and every object each time. So procedural generation is a great way to achieve diversity and true massive scale that we would require when we use synthetic data in the industry. One thing to note is that procedural generation also requires some kind of rule-based system for altering content. So artists do specify some set of handwritten rules. Procedural generation can further be used to create large amount of clutter or distractors in synthetic scenes. So remember, one of the earlier motivations we had was that there's a huge content gap, and synthetic data is often very clean. So this clutter, this large amount of variation, the clutter which procedural generation creates, can be used to as distractor to make synthetic worlds also as messy, as cluttered as real world. This also enables developer to control the amount of distractors and occluders parametrically at generation time. Another way procedural generation can also be used is to generate human trajectories. So ultimately, we are interested in full simulations, but can we, again, if we were to manually create it, it's an expensive process. So can we use procedural generation to automate the trajectory creation? So that can be done as well. So far on PG, it's a little bit expensive, but it truly scales and you can create massive content. However, it still requires handwritten rules from artists, and that's prone to bias, human bias. So what should we do about it? Another great paradigm, it has happened in the last couple of years, is using neural network models to learn the parameters of the scene. So for instance, there are two works like Sim2SG, MetaSim, and there are several work to address this problem. That can you learn the parameters of scene generation and work in conjunction with some of these traditional generators? Because just now we spoke about these hard-coded rules. Can we throw away those hard-coded rules and learn that directly? So MetaSim addresses that by comparing synthetic and real data and using backpropagation mechanism to learn the parameters of the scene graph. It does require a bunch of handful of labels to get a signal on how well it's performing on downstream tasks. Sim2SG and other techniques, they rely more on self-supervised techniques to learn learn real-world pseudo labels and then use those labels to create synthetic content. So these techniques tend to learn the distribution of real world as given by qualitative and some quantitative comparisons. However, we still haven't bridged the content gap. There's still a gap. There's still a reality gap that remains to be bridged. Another interesting work which came out recently. So there's a flurry of work on autoregressive modeling for indoor scene synthesis. So there are lots of work in this space using different neural network models to do it. And these techniques work from scratch. Like you don't require traditional generators like MetaSim and Sim2SG. You can actually learn the entire representation, relationships, scene completion from scratch. ATISS, the work that I'm displaying here, does it by modeling this as an autoregressive problem. You set generation, encode it in a more permutation invariant fashion. So this work learns the distribution of existing scenes and from scratch, works great. So this is a very promising direction. The problem is that the generated content is relatively simple. So in industry, we do care about complex scenes, complex behaviors, and this kind of model is still very early on to help us address that problem. Then there's another exciting line of work where you can use GAN. So recently, in the last couple of years, there's style GAN, there's big GAN, there's so many GAN works that can create very high fidelity images. Now, can we use these high fidelity images for training your networks, right? And this is what excites me the most among some of the recent work. So SSOD, self-supervised object detection via generative image synthesis, addresses that problem. It uses a 3D aware GAN, and input parameters are fed. It's a controllable GAN, so you feed some of these input parameters, and using those input parameters, you can actually extract bounding boxes, and GAN is able to generate synthesized images. So once you have bounding boxes and synthesized images directly from a GAN, you can use a downstream task like object detection. This works very well. In fact, this performed like twice as better as any self-supervised or weakly supervised techniques. So this is a very exciting direction with GANs generating synthetic data and circumventing all the issues that traditional pipelines have. Limitations being obviously, this work is focused more on object detection. There needs to be more work around more complex tasks, and general GAN limitations around requiring massive amount of real data. And this particular work also does not work beyond some simple objects being generated. So you want to generate full scenes. This doesn't work on that. Another great direction is dataset GAN, which uses a style GAN generator and trains an MLP on top of the latent features of style GAN to create synthesize images and synthesize part segmentation label corresponding to it. So you guys can check out the work. It does require very small amount of hand annotation in the StyleGAN feature space, but it's very small, and the performance they're getting is very good compared to the labeling that they require. So they've outperformed any semi-supervised techniques. So this is also in line with the previous work where you want to use GAN to synthesize images and part segmentation labels. So you get both the labels and images out from GANs. So with this, I want to summarize my work because Ido will be talking about different aspects of synthetic data. So with summary, I covered the problems with content creation, large domain gap. Manual content creation is very, very slow. We want to scale synthetic data creation. We cover domain randomization, procedural content generation, and then we also looked into neural network-based techniques, which learns the distribution of real data, and some GAN-based techniques to create synthetic data directly. Thank you, and Ido.
Thanks, Ayush, for the introduction. So I see we are running a bit short of time, so try to keep it brief and mainly focus on what we are doing in Meta with synthetic data and how do we use it. So first of all, I want to a little bit zoom out from the rendering engine and view it as a pipeline, as a black box, or as you wish to call it, where we have input parameters which controls this pipeline and then outputs the synthetic data. And the input parameters can be everything that includes in the rendering pipeline, which can be the layout of the environment, the objects, the appearance. It can be the trajectory of a player that moves around in the environment, the motion, his hands, etc. And the output will be the imagery, the renders, all the buffers, all the normals, depth, dense depth maps of the images, as well as other simulated sensors that we can simulate, and the pose of the human, the location of the camera, etc. And we will still need to mine the domain gap, even if we try to use some domain gap minimization techniques in the rendering pipeline. So first application, which I think is pretty obvious for most of us here, is to learn from synthetic data. And in order to do that, we can use synthetic data, and we do render it, and we get this all rich annotation, accurate ground truth for each pixel. And we can use that in order to train our algorithms to do things beyond things that we can do only with human annotations. But if we want to generalize better into the real world, we may need to add real data in the mixture while training. So first way to do that would be to use supervised learning, where we can think of cases where we have labeled data, both for synthetic data, of course, but both for real data with the same kind of labels. It can be from human annotations, which are not scalable, but it can be from other sources as well. And the other paradigm will be the semi-supervised learning, where we don't have the labels for the real data, but we still want to leverage this real data collection in order to train the model and to have a model that will generalize good to real data. So there's been some work that was done that using only synthetic data, and some that mixed synthetic data with real data. So let's overview just the high level thinking here. So one way to do that will be to control the rendering engine. We talked about it in the first part of the talk. And in supervised learning, we want to mix the real data and the synthetic data that we have labeled. So the question will be how we obtain those labels. So one way to do that will be to do photorealism enhancement. In such paradigm, we have the synthetic data, which is the synthetic image, which goes through a model, and then we do some image-to-image translation, and we get some appearance change in the image, but we still get the same content, which has high fidelity to the ground truth, and then we can use those images in order to train the model. Another way would be to have this controllable GANs line of work, where we have
generated data that actually the GAN learned the distribution of real data, and then we can control that. We can provide these controls as annotations, as ground truths for the rendered images, and use that for training. And in semi-supervised learning, it will be a bit different. So we don't really have annotations for the real data, but we do have a lot of real data. So we did the supervised learning because we trained those GANs and we trained those photorealism enhancement models. But on the other hand, we want to still add this data into the mixture. So one line of work that really stands out will be pseudo labeling, in which works we do take the unlabeled data. We have a model that performs fairly good enough on the real data. It was trained only on synthetic data. So we infer the labels on the real data, and we call that pseudo labels because this is a learned model and we don't have the ground truth for that actually. And then we feed those pseudo labels into a training process again, where we train a student. It can be the same kind of model or a smaller model, where we train both with the synthetic data and the pseudo labels from the real data. Now that would affect also will have a very significant effect in models where we have batch normalization layers, where in the same batch we can add both the synthetic data and the real data. So it changes the statistics of the batch normalization, and we get statistics that account for the real data while running on synthetic data where we have the ground truth. So if we deep dive into this semi-supervised learning a little bit further, it would look like that. We have the synthetic data, we train the teacher, we infer the pseudo labels on the real data, and then we would like to have some sort of mechanism in order to really detect the failure cases where the pseudo labels aren't actually correct for the real data. It can be used by just taking the confidence of which is the output of the network, but it can also be done by using some prior knowledge on the domain that we apply this model on. For example, if we want to detect a surface and we can look at some reconstruction error of a surface where we have these predictions, we have this error of reconstructing the surface, and then we can say, all right, if this error is large enough, we can know that, all right, it's not a good enough label in order to train the model. So we do filter out all these bad labels when we proceed into training a student model, and we can iterate this process again and again in order to improve the performance and to enlarge our labeled data. So meta pseudo labels is another work that really gives us the insight that we can also have a feedback loop from the student to the teacher about the performance of the student on the pseudo labels. And that way the teacher can adjust his pseudo labeling process, the labels that he produces for the student, in order to improve the student performance even further. So that's one application for using synthetic data. I want to concentrate on the other side of things, which will be evaluating on synthetic data rather than real data. So the overall idea is that when we have synthetic data, we can have a scalable, large amount of data that we can replay a lot of hours of algorithms that are tested on the synthetic data. And now, instead of having this real-time inference and collecting data issue, we have this compute bottleneck that really we can scale up the evaluation process. Now, we do have these performance metrics. We learn about the distribution of the error, and we have a feedback loop where we can improve both the synthetic data itself and the evaluated unit, for example, SLAM algorithm. And we need to keep in mind that we want to really test our algorithms on real data as well. So we can have feedback and see if really the synthetic data is representing the cases that we wanted to represent in real world. And once we've done that, we can really scale up the data and maybe introduce novel cases and novel scenarios where we want the algorithm to perform well, but we still don't have data for. So for mixed reality and virtual reality, this is extremely useful Especially we're talking about mixed reality and virtual reality devices where we have a lot of sensors. For example, if any of you played the Beat Saber, so we have the Oculus camera, Oculus device where we have multiple cameras. We also have IMU, we have the controllers that we control the lightsabers. And we want to evaluate this, this device on novel scenarios and to really see in which cases we can handle, and we can build a guardian and we can really operate on. So to evaluate in this case would be to have the device in the physical world, also to have the simulated device, exact device where we have the rig of cameras, we have the simulated sensors, and we have the simulated environments. In the synthetic data, we generate the synthetic data simulation where we have this player walking around like he was walking with the device. In real world, it's a bit more complicated where we can't really measure everything. So we take some telemetry. We don't take the imagery itself. So we know when we lost tracking, we know how much jitter we have, etc. So we run those both real data and the simulated data on the algorithmic pipeline for SLAM. We get the metrics, we get the insights, and now we know in which failure cases approximately we fail in real data, and we can even further deep dive and understand, get a better understanding what caused those failure cases, what scenarios can repeat, what more scenarios can cause more failure cases when we simulate those and we don't have actually any knowledge of how it appears in real data. So to sum it up, we talked about accurate ground truths, which are ground truths that is present in the synthetic data, but not always in real data. The modeling issues, number of assets, scaling it up with procedural generation, and enhancing the photorealism. Domain adaptation, we talked about supervised learning using generative models and image-to-image translation, and semi-supervised learning using pseudo-labeling. And our applications are vast. When we have multi-sensoring, you can imagine that we can even simulate sensors that not exist just yet. We can use it for training, we can use it for validation, and we use it for really gaining understanding of the scenes in the real world and the semantics in the real world as well. Thank you, everyone.
Yeah, I have a question. I also asked that question before to other speakers, but I didn't have an answer. When you train, when you do the domain adaptation, so you have your network training on synthetic data, and you want that network to generalize on your world. And then you do some, as you said, domain adaptation or self-supervised learning to bridge the gap. When you do this, you still evaluate on the synthetic data, or you forget completely the performance of the synthetic data and train and evaluate only on the test set, which is the real world? And do you think it is something that should be taken care, or you can completely forget about synthetic data?
Yeah, sure. Actually, that's a great question. So it's basically depends on who does that and the application. In my perspective, both are important. So you do want to eventually want to operate on real data. So you would keep a test set or regression set where you measure your performance on real data, but you don't need to actually forget about the synthetic data, because the synthetic data gives you insights about what failure cases there are present if you can't really deep dive into the real data. And even if you could, you can maybe try to generate more cases like that and to have a larger test set and to see really what caused these failure cases, in what regions you operate well, and in what regions you can maybe improve your model and add it to the training data and really generate more synthetic data in order to prove the model, which is separated from keeping them both, deep dive, see the course of the failure.
Because otherwise you overfit to the domain. I mean, when doing domain adaptation, I expecting that the model improves on both domains. I mean, yeah, ideally it should generalize more.
Yeah, ideally,
But yeah, maybe
you want to take with this one?
Yeah, ideally you want to generalize more. So a lot depends on your test set. If it's like narrow, like for example, if you're evaluating simply on KT, that's not going to cut it for self-driving application. So you want to evaluate across a plethora of real tasks. And synthetic evaluation is another interesting aspect, as Ido mentioned, because a lot of times, for us, the hardware isn't even available, right? Or some situations aren't even available. So suppose it's a rare scenario. Suppose it's some other kind of scenario for which real data doesn't even exist. So you still want to test it, right? And synthetic testing is zillion times faster because the limitation is simply compute at that point. So definitely you want to evaluate on synthetic on dangerous and rare situations. You want to evaluate on synthetic on unknown situations. Yeah.
By training GANs, the GAN itself is trained on a lot of real data, and then we are using the data from the GAN for the training. So is it fair to call that synthetic data?
So that's a good question, right? I mean, ultimately, even synthetic data is also created by users, right? It's not like it just comes from zero or scratch. So there's always some amount of effort, some amount of expense that goes into it. The question is more about like how much expense, right? If it's easy to collect real, so those data are still weakly supervised, like sort of what exists in that real data. For example, when you're training for car models, that all of them are cars. So there's still some expense to it. And with that expense, good part is that, the realism part is handled better with GAN versus, synthetic. Because synthetic, you want to use domain adaptation, photorealistic enhancement, that's expensive and doesn't really close the gap. But with GANs, they're better. But you're right. If it's not purely synthetic, real data is used to do it. But so is domain adaptation. You do take real data to actually improve domain adaptation results. You do pseudo labels and other things in this regard, and their real data is important. So really, when you create synthetic data, you don't want to leave it to anybody's imagination. If it's done by machine learning models, they have to look at real data. Or if it's done by humans, then they have to use their guesswork.
Maybe a quick follow-up on that. So we said that like photorealism enhancement is hard. Like intuitively, I would expect that enhancing a synthetic image would be easier than generating an image from scratch. Like, but you kind of said that the basic.
So it depends on whether it's a network doing it, whether it's human doing it. So if you look at artists, when they actually improve the photorealism, it is very expensive. Because for artists to buy some model of, and bring it into a traditional pipeline, or for them to create a bunch of vertices with some color and all can be a little bit quick. But going from that part where it's just like a 90s graphics all the way to like a 2022 kind of graphics, it's a lot of work actually. It's a lot of looking at it. Like if, for example, an artist quoted me this, like you guys all must have seen the UE5 meta-humans, the realism on the faces. It took, I think, 3 months for one artist to create one human face with that kind of realism. So it is very expensive, actually. So, any further questions? Thank you.
The speaker here.
Thank you.
Okay. Coffee break. And then we'll have some more talk. Just a second, let me take this. So for me, is this not what you see in the? Yours is
I
not.
think if you're just gonna like select it, right, that must be the same thing, no?
Yeah, but basically you wanna know how to put some email
But
and.
because I think it didn't understand like the whole link, right? I think you see the link is only show here. That's oh, but this is now it says invalid address. Oh, because it copied address. I'm an idiot. And now, no, that's the same station. Doesn't sign. Maybe like a second link, different than chance, but I don't think it's different, to be honest.
Yes.
Oops, I copied it wrong. No, I copied it wrong.
Okay,
Oh,
maybe.
because it has some WBR. So I think if I just remove this, yes, ask me sign in any case.
Yeah, but signing in, this is normal. This is
okay
where you have to use the. So at the bottom.
Yeah, the password and the email is this one.
Exactly.
Yeah, so I was.
Okay, so let's start. So yeah, now we're having a talk from Professor Kate Saenko. So Kate Saenko is an associate professor at the Department of Computer Science at Boston University, and the director of the Computer Vision and Learning Group, and member of the IVC group. She received her PhD from MIT. Previously, she was an assistant professor at the Department of Computer Science of University of Massachusetts Lowell, and a postdoctoral researcher at the International Computer Science Institute, a visiting scholar at UC Berkeley, and a visiting postdoctoral fellow in the School of Engineering and Applied Science at Harvard University. Her research interests are in the broad area of artificial intelligence with a focus on adaptive machine learning, learning provision, and language understanding and deep learning. Okay, Saenko, thank you.
Right, thanks a lot for the introduction and for inviting me. Are there people on Zoom and can they hear me? Should we do a check? If the people on Zoom cannot hear me, there's no video also. Should we start video?
The video would be for yourself, but you're already sharing screen.
Okay, so the Zoom people can see my video.
Yes, audio works.
Audio works.
Yeah, I mean, yeah, we can also turn on the video. Yeah.
Okay, awesome. Okay, welcome to hybrid workshop formats. Thanks for sticking around as well this far into the day. I know it's overwhelming, our first time back in 3 years. I'm super tired already. I've been here since yesterday. Yeah, I want to talk about generalizable and adaptable representations. So my work has been for a long time now in working on generalization to out of distribution data. So we have this problem all the time in computer vision. There's a data set that you're training on, and then you get some new data and it looks different from your training data. So you have this problem of data set bias. We call it data set bias or domain shift. And the problem is, of course, you know, your input distribution is different from what your model was trained on. So it's going to fail. It's going to miss people in this case. So we've been working on this for a while, still haven't solved the problem. When does it happen? It happens actually lots of different situations. Happens when, as I said, you train on one city, you test on another, maybe you train on web data and then you test on robot data, or more relevant to this workshop, if you train on simulated data and you then test on real data. But it can also happen when the demographics are different from training to test time, when the culture, even how an event is represented in one culture versus another changes. So lots of ways that data set bias can happen. And what's the issue? Well, it's going to reduce your accuracy, right? So this is from our paper from over 10 years ago. Things aren't that much better these days with deep learning models, where we still can lose 11, 14%, very, very large loss in accuracy. Even when we simply collect a new ImageNet test set the same way that the original was collected, we still see the model doesn't generalize. And why does this data set bias or these kinds of data set bias issues affect the models this way? So in the case of deep learning, of course, the models are learning some feature representation, right? So if you train it on a bunch of data sets of people, let's say adult faces. It will learn representation that includes features like eyes, nose, mouth, certain shapes, parts. Now, if you now want to take this model and transfer it to faces, but now it's children's faces. If the model was only trained on adult faces, it's not going to learn the kinds of parts that children's faces have, right? Children have bigger eyes, they have, slightly different features of their face. So it's this bias in the representation that the model learns, the features the model learns often that causes poor domain generalization to out of distribution data. Okay, so what can we do about this? Of course, we can always try to collect and label more data that is more representative of our target data set. But this can be expensive. So what else can we do? Can we get away with not collecting, not spending lots of money? Basically what I'm going to talk about mostly in this talk is two kinds of machine learning solutions that don't use a lot of data. So the first one is called domain adaptation. This is where we have labeled data from one distribution and then unlabeled data from our target distribution that's somehow cheap to get, right? So let's say we just collected from a car, it's unlabeled, so it's cheap to get this data. So that's domain adaptation. Another approach or another setting is domain generalization. So here we have multiple domains in the training data that are labeled. And then we want to generalize to a novel domain or novel distribution that wasn't there in training. So this is called domain generalization. And here, unlike in domain adaptation, where we get to see the target data, even though it's unlabeled, but we get to see it and we get to train on it without labels. In generalization, we don't get to see the target distribution. We get something, we don't know ahead of time what it is, and we just have to generalize. Okay, so those are the two sort of major settings that people have looked at in this literature. So how do we test these kinds of models that try to do adaptation or generalization? So we have to test on out-of-domain data, right? And in general, I would argue that any model that we come up with, even if it's not a domain adaptation model or domain generalization model, we should still not test it on IID test data, right? When did we decide that taking a single data set, sampling a training and test set IID, training the model on the training set, testing it on the IID test set, and we can declare victory? Like, when did we decide that in our field? It seems really limiting, right? It's always going to really overestimate your generalization performance of the model because it's the same IID distribution. This is really a reason, I think, to have more data sets that have varying distributions between the training and the test time. And so we've collected several of these data sets over the years. They vary in the amount of shift from kind of smallish to larger to very large. So the VISDA data set has synthetic data as the source domain and real data as the target domain. And then the domain data set has all these web domains. So there's clip art, there's drawings, there's sketches, there's real images. So these data sets allow you to evaluate models on fairly significant domain shifts. All right, so in terms of the domain adaptation methods, there's been a pretty, I would say, major focus on this method of aligning the domains, right? So we can align either in the feature space or in the pixel space. And in both cases, we have some encoder. Let's say it's a CNN, could be a transformer. We have the source data with labels. We have the target unlabeled data. So we're talking about adaptation here. And The feature distributions, because of this shift, because again, the encoder learned the features on the source data, the feature distributions that you see here are going to be mismatched. So we can either train a domain discriminator to align the feature distributions, or we can train a GAN to align in pixel space directly, basically translate the images from the source to the target domain to make them look the same. But I'm not going to talk about these kinds of approaches here. What I want to talk about is, what about the pre-training for this encoder, right? The vast majority of cases, when we have a source data set or some labeled data set, we're not going to train it from scratch. We're going to use some pre-trained model that say pre-train on ImageNet or pre-trained on something. So I want to talk about the role of pre-training for generalization. So I'm going to talk about essentially three things. The first one is 2 papers and then 2 more papers. And I'll go fairly quickly, but feel free to stop me or ask me questions at the end. So we want to know, how can we use pre-training to create more generalizable representations? And the first one is going to be about, it's going to talk about unsupervised or self-supervised pre-training. So one issue with domain alignment is, what if we had different categories in the source and the target? And more generally, if we have multiple domains that have different categories in them. So some categories overlap, some categories don't overlap, but we know that these domains are different. So what we can do is we can actually do self-supervised learning. The normal way is we would, learn from similar pairs in a single domain. That's the standard in-domain self-supervised learning. But what we're proposing in this paper is that we also do cross-domain self-supervision. So we find the nearest points in the other domain and we try to align them together. So this is cross-domain self-supervision, cross-domain contrastive learning, cross-domain instance discrimination, whatever your favorite self-supervised learning method is. In this paper, we used instance discrimination. Okay, so the idea is that this is going to try to align similar categories together and keep non-overlapping categories embedded in separate parts of the feature space so that they're not aligned together and confused in the representation. And then this is the pre-training stage. We can follow this with some downstream tasks, fine-tuning, domain adaptation, generalization, anything really that we want. All right, and the second paper along these lines is actually a paper at this, sorry, I'm gonna move this CVPR. It's in the Wednesday oral session. And what we are looking at here, this is a collaboration with the IBM, MIT, and Tel Aviv. So what we're looking at here is, okay, so if we're doing this pre-training, suppose we have multiple domains. So here you see painting, images, real images, sketches, and clip art. These are the different domains. And we're doing unsupervised pre-training in this case, right? So it's great because it's cheap. We don't need labels. What happens is when you look at nearest neighbors for this kind of pre-training, or you do augmentation for contrastive learning, the model will probably learn similarities within domain first. So it will learn that a giraffe, a painting giraffe, is closer to another painting of a non-giraffe than it is to a sketch of a giraffe because of the large gap between the domains, right? So it's probably going to focus on things like these texture patterns, and it's not going to focus on kind of the giraffeness of the giraffe, right? What is the semantic? What are the parts and the features of the giraffe that are unique to that category? So what we are proposing is learning another domain that we call a bridge domain. So this bridge domain is essentially mapping each image to a new visual domain. So it's an image-to-image model, translation model. But in this new domain, this bridge domain, categories are represented as sort of these outlines. So there's no texture or color in this domain. And this domain is only used to align similar objects together, right? So in this domain, hopefully we know that all of the giraffes, the painting giraffe and the sketch giraffe and the clip art giraffe, they're all the same category because they look a lot more similar to each other in this bridge domain than they do in the original domains. And so if you look at, you compare this representation we're learning, so that's the last column here, to, let's say, just edge detection, or HED is a learned edge detector or contour detector. You see that in our case, we are, the model is learning to keep discriminative parts like eyes of the dog and ears of the dog, whereas the HED model is not using them. It's not discarding, it's discarding them. And the edge detector just in general over, estimates, it depends on your setting, but it can detect too many edges that are not semantic. And similarly with the giraffe, you see that in our bridge domain, the giraffe has spots, whereas in this HED domain, it does not. Okay, so this will be a talk at CPR, so I'm just quickly previewing it. And if you're interested in more detail, please attend that session. Another thing that we wanted to look at is sort of, okay, what if we try using some more modern pre-trained backbones? A lot of the domain adaptation literature uses ResNet or version of ResNet pre-trained on ImageNet 1K. And we've actually been running domain adaptation challenges for many years. And the last one we had, the winner had used one of these very recent at the time transformer models, BEIT, and they didn't use any domain adaptation and they won the whole challenge, right? So, and as you can see, if you can see the numbers, they won by quite a bit, almost 10%. So this made us think about, okay, what is the role of these large scale pre-trained models? Are getting bigger and bigger, they're trained on more and more data. Can we really ignore them? I mean, it seems that we shouldn't ignore them. So this is what we looked at in this paper, which we call a broad study of pre-training for domain generalization and adaptation. Okay, so we did a whole bunch of tests. This one is showing if you take state-of-the-art domain adaptation models, where the blue bars are single source and the green bars are multi-source. They're all trained on some source data and then adapted to the same target domain and tested on that target domain. So that's the accuracy you get. And then if we just take a state-of-the-art pre-trained backbone, train it on the source, and don't do any adaptation, we just directly test it on that target domain, this is what we get. Right, so pretty major improvement, certainly over the single source models and also the multi-source ones. So, okay, this is interesting, right? So you might say, well, it's not fair to compare these models because they're all using ResNet 101 and you're using ConvNext, which is also a CNN, but it's more modern. But, I would argue that, well, wait a minute, but it works better. Should we just not use it because it's not proper comparison? So that's kind of what we try to do in this paper is we try to compare various ways of pre-training the model and the effect that has on the adaptation and generalization to new domains. So what we do is we look at comparing the existing pre-training paradigm where pre-training is done on ImageNet 1K with a ResNet architecture versus more modern pre-training where we're using larger data sets like ImageNet 22K or image caption data sets like CLIP uses, if you've heard of CLIP, and a stronger backbone like a transformer or ConvNext. And then we evaluate them on this domain shift scenario, right? So we have a training source domain and some new target domain that has a domain shift with respect to the source. Okay, so I'm just going to preview a few results. There's tons of results and this is a huge table, but just at a high level, when we compare state-of-the-art domain adaptation methods using the traditional pre-training ResNets with ImageNet 1K. The best we can get is 72.8 on this data set, this Office Home. It's a pretty standard domain adaptation data set. Whereas with more modern pre-training, the best we can get is 83.5%. This is with just training on the source data, no adaptation at all. Right, pretty huge improvement. So we looked at many different things here. One of them is architecture. So if you use the same data set for pre-training and similar numbers of parameters, but you change the architecture, CNN versus transformer, what happens? Well, we see that it's interesting that actually sometimes for some data sets, like for DomainNet, the CNN generalizes better to new domains. But for CUB, it's the transformer that generalizes better, specifically this DEIT model. So it could be that CNNs and transformers are robust to different kinds of domain shift. So we should really investigate this further. What about the data set? What should you pre-train on? Okay, so the top is the effect of pre-training on ImageNet 22K, which is larger than ImageNet 1K. And in general, this gives you better results across the board. The same thing for JFT 300 million. You will notice though that there's this wildcam data set where the improvement is smaller. And this is camera trap images. So we think it's kind of an interesting data set to look at because it's very much unlike these ImageNet data sets. So it's interesting that we're not seeing much of a gain there. Now, the bottom right is looking at the effect of pre-training on caption images. So like CLIP, for example, I think this is either CLIP or Albef, one of those two models. And you see that here, actually, it hurts performance on CUB, improves performance on DomainNet and Office Home, a little bit on Wild. So it depends, again, on what kind of data set you have, what kind of task you have. So it might be better to pre-train with image captions, may not be. How about model size? So here we're increasing the number of parameters on the x-axis. And in general, bigger is better. Better generalization from larger models, especially for VIT. You see quite a bit of an improvement with size. And how about domain adaptation methods? So do we still need that? Do we still need to do domain adaptation with these more modern backbones? So the answer so far looks like yes, domain adaptation still helps. But interestingly enough, it's the older method, CDAN from now, I think 4 or 5 years ago, that beat everything else. So when we use one of these more modern backbones, pre-trained on larger data sets. So the conclusion I take from this is that, it's great to have direct comparison with the same backbone. We should always do that. But it seems like as a community, we've been overfitting our domain adaptation methods to the older backbones and the older, smaller pre-training data sets to the point where they don't generalize to the more modern, larger pre-training. So we should be careful that we don't do that going forward, that we should always, try to get the biggest, best, largest backbone out there and test our model on that. All right. Great. So, so far I talked about unsupervised pre-training with real data. What I want to talk about next is, I think, the closest to the topic of this workshop, which is simulated data. Okay. So one of the maybe unsatisfying things about pre-training is you don't usually have much control over your pre-training data. And what we wanted to think about here is, can our pre-training data be customized to our downstream task, right? So for example, if your downstream task is chest ray images, X-ray images, then you might want one type of pre-training data. But if your downstream task is satellite data, you might want a different kind of pre-training data set, right? So the visual characteristics you may want them to be different. So how can we do that? So our solution is going to be to generate custom pre-training data using simulation. Okay, so this is also a paper at this conference. It's going to be poster 122B on Wednesday at 2:30. And it's called Task to Sim Towards Effective Pre-Training and Transfer from Synthetic Data. Also collaboration with IBM and several other colleagues. So here, what we want to do is pre-train completely on synthetic data. And the synthetic data is kind of like ImageNet in the sense that we're taking 3D object models of various categories. Like, we have anything from vases, tables, potted plants, so on. And we are synthesizing images that are kind of like ImageNet images, that there's one object on some background. Okay, and then we take the model pre-trained on the synthetic data and transfer it to downstream tasks, and we evaluate performance. And so what we saw is that depending on how you vary the pre-training data parameter, the synthetic data generation parameters, so do you vary pose, do you vary lighting, do you add blur, how you vary materials, the textures on the objects, and also the background, how much you vary the background. These parameters have a different effect on downstream accuracy, right? So the set of parameters you use to simulate data for Eurosat is not the same, the best ones are not the same as the ones you would use for street house view, street view house numbers, the SVHN dataset. So this motivated us just to say, wait a minute, maybe we should kind of learn to predict what are the best simulation parameters for pre-training based on the downstream task. Right, so if we have our downstream task data, we have some label data from that task, maybe we can use that label data to predict the best simulation parameters for generating our pre-training data. Okay, so that's the idea here. The overall model architecture is here. I'll go over it kind of quickly, but again, we'll have a poster on this on Wednesday. So we have our tasks over on the left. And so we want some notion of how tasks are similar to each other or different from each other. And for that, we use an existing work called task to vec, which takes a data set and embeds it into a vector. And then our task to vec, or task to sim rather, model it's a neural network that takes the task embedding vector and predicts the simulation parameters. Okay. So the idea is that for any downstream task, we can just embed it into a vector, feed that into our task to sim model, and it will tell us what simulation parameters to use to then generate the synthetic data. And we're using the TDW generator or simulator for the synthetic data. Okay, and then once we have generated the data, we pre-train the model on this data, and then we can evaluate it on a downstream task. Now, in order to learn the right parameters, we have a reward that is fed back into the task to sim model so that it gets some training information about which parameters worked out well or did not work out well, depending on what that input task embedding was. So this way it can learn to better map task embeddings to simulation parameters. Okay, here's a quick visualization of the 8 binary parameters that we use in this paper. And they're binary because we either vary each one or we don't. So they are scale, texture of the object, the background, this one is blurring, and so on. All right. Okay, so the data sets that we use for the downstream tasks are here. There are a bunch of them. They're basically 20 downstream tasks from 6 categories. And I won't go through this table because I probably don't have time in detail, but the takeaway here is that our task to sim model seems to actually give us pretty good performance for pre-training compared to either domain randomization, where you just randomize all of your parameters to generate the simulated pre-training data, or compared to ImageNet pre-training where we pre-train on ImageNet with the caveat that we equalize the number of classes here because, we had to constrain our experiments somewhat because it's still, the simulation is still not very efficient and the simulator we used was not very quick, was not fast. So, so for that reason, we either use 100 classes or 237 classes. And so in those regimes, we're actually doing better than ImageNet pre-training, especially in the case of, or at least as good or close to ImageNet. So here on fine tuning, we're very close to ImageNet pre-training, but we're a little bit better than ImageNet pre-training on novel tasks. So at the bottom we have unseen tasks, at the top we have seen tasks. All right, so I think I'm going to wrap up here because I think I'm probably out of time. These are the papers I talked about today, probably too quickly, but feel free to ask me questions. I'm just going to end my talk. I'll put the slide up. We have a new adaptation challenge and it also has simulated data. So for many of you in the room who are interested in simulation, this might be a fun challenge to participate in. And it's also recycling, so it's good for the environment. So there's that. All right, thank you very much. Yeah, so the question is, do we learn to simulate with a closed loop? And yes, we do. So we try, so it's a reinforcement learning framework. You try some parameters, you see how well that data generalizes to a downstream task. And that's that accuracy is the reward signal. And one of the things that we had to do is to compute that quickly. We just actually have KNN classifier, which is much faster.
Next question is, do you know how does branches change the train? Is it okay or the model goes like up to something with branches?
Yeah, we did look at the parameters. I think there are some insights, but you would want it to learn is, for example, if your downstream task has no color or something like that, it shouldn't, vary color. Or if you should be invariant to certain things, then it should vary those things across models, right? But I don't think we saw any very clear patterns, but there's certainly different kinds of parameters that it predicts for different tasks. So it is selective across different tasks, but we need to look at that more to see if there's any clear trend. Sure. Yeah.
That's the question. It seems like in some ways the philosophy of the story is different between the middle work and the last work. The middle work, it seems that the evidence seems to say that you should really be trying to train on larger and larger data sets. Like bigger models is the solution. And in the last work, you said, no, what we really want is customized data sets that just have the sort of variations in traits. Is that a fair interpretation?
Yeah, very, very good. It doesn't really line up very well. Yeah, so the question is, should we just go with bigger and bigger data, or should we go with more custom data? I think that depends on the application and the downstream task. One thing what we saw and what I was pointing out with the wildcam data set is that sometimes going bigger doesn't help you, because I think that there's a limit to what you can learn from web data. All of these large scale data sets, they're scraped from the web, right? So for certain downstream tasks, I think there's a limit to what we can transfer from the web. And so for those kinds of domains, maybe like satellite, maybe medical, maybe fine-grained categories like, everything in the ocean or something like that, maybe we need something more specialized. And maybe for people, so we didn't cover people here, but it seems like from this workshop so far, simulated data for anything people related is pretty effective, and also it's more private. You don't have such issues with privacy or consent to get the training data. So yeah, good question. Yep.
Is there any inclusion of the live second parameter?
Yeah, so we did some initial kind of, these are oracle tests where we tried every combination, and then we saw that some of them work better. So for example, adding blur improves performance on satellite data. And you can see here it doesn't improve performance on this GTD, which is a texture data set. So probably, that data set has less blur. So it helps less on it. Okay. Yep. Yeah, so the question is, what did we use to generate the synthetic data? We used the 3D world simulator from MIT. It has physics in it. I think it can generate sound as well. It's a pretty cool simulator. We're trying to speed it up though. It's not super fast. Yeah, so we evaluate we try to compare the same amount between these different pre-training approaches. So here we have 40K, and then on the right we have 100K, which is still quite small, right? But here we're limited by compute, essentially. We just need more time to scale these experiments. All right. I think we're good.
Yeah, exactly. Okay.
Sure.
Yeah. Okay. So next we have a talk by Professor Deva Ramanan. Deva Ramanan is a professor in the Robotics Institute at Carnegie Mellon University and the director of the CMU Argo AI Center for Autonomous Vehicle Research. His research interests are computer vision and machine learning with a focus on visual recognition. He has received numerous awards, including the Long-Getting Prize in 2018 for fundamental contributions in computer vision, as well as Best Paper Awards at CPR 2019, CE 2020, and ICC 2021. So thanks for coming. It is yours.
Thanks.
I don't know what this thing is.
Oh, it's captioning. Okay. That's pretty cool. I'm just gonna close this. Hopefully that's okay. Wow, okay. I guess it'll be captioned. Okay, so I'll give a little bit of a different flavor of a talk. I know that this tracking benchmark workshop is really focused on the use of synthetic data. And I'll talk a little bit about that, but I'll try to be a bit more provocative and ask the question about what is the role of tracking? And I'll try to answer that question from the perspective of autonomous navigation, which is a space that I've been in for the past few years. So let me motivate this by thinking of sort of well-known challenges and failures in the self-driving space. So one of the remarkable things about working in a place like this is there's enormous federal oversight. So every sort of accident that you hear about, there's actually a transportation board that reviews this, and they talk in detail about what went wrong. And this is in particular is a well-known accident that happened in 2018, and there was a fatality involved, so incredibly tragic. And the document talks about lots of failures that happen at different levels of safety protocols, but it also talks about failures that happen in computer vision. So I think it's pretty remarkable to look at it, to sort of see vision literally matter in a life or death setting. And this is the wording in this document that talks about the failure of the perception system. The automatic driving system changed the pedestrian's classification several times, alternating between vehicle, bicycle, and other. Because the system never classified the pedestrian as such, the system's design excluded tracking history for non-persisting objects, those which change classifications. It was unable to correctly predict the pedestrian's path. So what I'm showing here is a table that's from this document that actually gave the classification of the vision system of what there was a person walking across with a bicycle that appeared from behind an occluder. And because there was a flicker and there wasn't a stable interpretation of what the system was saying, it sort of determined, oh, this must be noise or something that I'm looking at. So let me not sort of slam on the brakes, perform an evasive maneuver. So you can look at this and say, this is an enormously compelling reason for why we need better trackers. We need stable interpretations of the world over time. And what this also suggests to me is that it's still quite challenging to do this. And I would say that it's challenging to build stable interpretations of a dynamic world. And one aspect of this I like to emphasize is that although we generally think about flicker as a bad thing, I think there's another perspective that suggests that it might be a good thing, because maybe it reflects the ability of perception system to fix a previous error, or maybe it reflects the ability of your perception system to realize there's actually been a dramatic change to the environment. This happens all the time with occlusions, because someone appears from behind an occluder. So that very first frame that they appear, do you interpret that as a flicker that you should ignore, or do you interpret that as a change of the world that it's so imperative that you must react to it? And so what I claim is that we actually, surprisingly enough, in this kind of online setting, we might not have sort of the right tools for sort of thinking about this. And one argument I'd like to make is that the way that we even evaluate computer vision, we tend to, I would argue that we actually evaluate it in what I would call the offline setting. So what we tend to see is things that look like the left video, where we take a video stream from one of these settings, we run a state-of-the-art model, this is NASCAR CNN, and the results look really good. But one thing that's kind of striking, I find, is that if you actually get a chance to sit in a self-driving car at some point, I think it's sort of a cool experience to do that, and you look at what's happening live, what you actually see is something on the right-hand side. You see a disconnect between what it predicts and the sort of visual screen that shows sort of behind the predictions. And for a long time, I thought this was sort of just like a mismatch or a bug in the visualization. But I think what we sort of eventually realize is that this is actually reflecting a fundamental property of, I think, embodied perception, which is by the time an algorithm finishes, the world has changed. I think that's undeniable. Essentially, we did some work in ECCV a couple of years ago on trying to sort of emphasize this as another way of benchmarking. And what happens is that you can actually define, or how do I say this? You can actually define metrics that take classic tasks of visual understanding, such as object detection or semantic segmentation, and evaluate them in a streaming setting. You can try to now optimize for streaming AP accuracy or real-time accuracy. And just to give you a flavor of the kinds of things that emerge when you optimize for that, is you can imagine that there's this fundamental tension behind if I'm running an object detector in the tracking by detection framework, should I run a really cheap detector that, let's say, finishes before the next frame arrives? But when I do that, that might be not that very accurate. But one thing that, let's say, one way to think about this is that what we should really do is we should have detectors that report the state of the world when they finish processing the sensor frame. So if you have a really shallow detector, in some sense, it has an easier job. It doesn't have to forecast that much into the future, maybe only 100 milliseconds. Or alternatively, you can run a really deep network with a beefy backbone, but because it takes so long to finish, it actually has a harder job as to figure out what's happening half a second into the future. And what's nice is you can actually let these networks duke it out. There's a well-defined loss here. And you can almost do you can almost do an architecture search and saying, is it better to go lighter weight and sort of more reactive, or heavy duty where you have to do a harder task? The other perspective that this suggests to me is that a lot of vision work, another way to sort of do this idea of kind of like forecasting what happens in the world while you're still computing your last sensor measurement. One way to kind of deal with that is essentially say that for that kind of forecast, it's always essentially like a physics problem. You can, if your eyes are closed and you're still computing from the last time you opened them about what the state of the world is, if you could estimate how the world was changing, like the speed of things, you could say that, okay, they're still moving at the same rate that I saw them before. But what this requires now are models that don't just tell us where things are, but tells us like the velocity of them. And I claim that we haven't done a good job of community of this is not a flagship task, but I think this should be. Like, how good are we at estimating the velocity of things and the accelerations of things? Because if we can do that, then we can at least do first order physics, ballistic motion. So then we understand how things are behaving for the next 100 milliseconds or 200 milliseconds. So I'll talk a little bit about work that we have in CVPR that tries to do this. But then what's kind of neat is that if you embrace this online perspective, what ends up emerging is that even if you're trying to solve like a single frame detection problem, where, just to emphasize what that is what you're trying to say is you're trying to optimize the accuracy of the thing on the right-hand side. And it's really optimizing a single frame accuracy, like MAP or semantic segmentation overlap. What's cool is if you've set it up in this way, what ends up emerging is that it's useful to understand how the world is changing, either directly by using a detector that can spit out velocities, or by linking and tracking things so you can estimate how things are moving in space. So what ends up happening is that even for these streaming single frame metrics, tracking emerges as a thing that you can do to help you solve the single frame metric. But what's kind of super crucial though is that from this perspective of efficiency, this tracking only makes sense if it's incredibly lightweight, because otherwise you end up spending so much time trying to associate and track things that you should have just ran a detector. And my claim is this is how we should actually build reactive systems. You think about this case again, where a person appears from behind an occluder. That first time they appear, you have to make a decision. You sort of want to get as much juice from the signal as you can. Okay. Some other sort of interesting things that happen when you embrace this online perspective is that normally, a frame comes in, you sort of process it, and then you have to figure out, once you're done processing, then you grab the next frame that you have lying around and you start processing that. But what happens though is that sometimes if you just waited a little bit, you would start processing a new frame would arrive and you could process a fresh sensor measurement instead of back here where you'd be processing something that's still, I don't know, 30 milliseconds old. So there's this unintuitive result where if you're really trying to be super reactive, like react to someone that appears behind an occluder, sometimes you might want to hit the pause button and wait for a fresh sensor frame to arrive. So what you actually end up with is almost networks that try to asynchronously schedule themselves. When should they run? Because sometimes you do want to wait. You don't just want to grab the most recent thing you have available. I should say that one more thing about this view of this world is that when you measure accuracy on the right-hand side, one annoying thing about the thing that I'm advocating for is that now when we talk about streaming accuracy, it depends, your streaming IP, that 6%, that number will go up if you have a better GPU. Because if you have a better GPU, you won't have as much delay. So what's really annoying now is that now when we talk about accuracies, you have to tell me what was your hardware setup, which right now we don't have to say that when we talk about AP. But I argue from an embodied perspective, it should depend on your hardware setup. That's what it means to be embodied. You know, the ability to perceive and act depends on the body that you have. So we tried to advocate for this kind of like alternate way of sort of online processing, where, you know, it's almost hardware in the loop evaluation. It was kind of interesting. We held a benchmark competition last year, and by I guess the standard metrics, I would call it a success. So we had a slew of entries, and the winning entry actually doubled the performance of the baseline, which is usually a good sign that like some innovation was done. So just in the here, tracking is not really an explicit requirement, but it's rather emergent from setting up the task in this way. So I find that to be sort of an interesting way to think about tracking, and I'll push this philosophy for the rest of this talk. Another application for if you really embrace this online perspective, I would also argue that the online perspective suggests a different way of thinking about occlusions. So normally when we have long-term occlusions, like let's say we're trying to understand where this person is going and they get occluded behind a car, the way that we typically think about this in the offline setting is once we see them again, then maybe we'll be able to run another tracklet algorithm and find them. And then we apply some sort of meta stitching algorithm to stitch the tracklets together. And so this has spawned the field of re-ID, re-identification. So you didn't see something for a little bit, but then you see it, so you try to link it together. My claim is this is not the right way to think of tracking in an online setting, because what that allows you to do is after they reappear, you can say, oh yeah, this person must have been behind this car the whole time. But in an online setting, if you don't see them, you still have to decide if you want to slow down while they're fully occluded. So another perspective is that in order to deal with long-term occlusions, what you really got to do is forecast. I'm showing like a visualization here that you guys might not have seen. But in a lot of these sort of AV data sets, there's this task of, given track directories that you see for some amount of time, estimate where they'll go in the future. And so this suggests that this should be much more of I'm guessing most folks working in tracking might not sort of work in the field of forecasting, but I want to sort of advertise. I think that's a different flavor of the problem. That's actually pretty intriguing. So it deals with, behavioral analysis, but really predicting in the future. And one kind of cool thing is that there's a lot of AV data sets that people have started producing and releasing to the community from different cities that actually, and from my understanding, I think there's some of the most largest scale behavioral data sets in existence. So you can see how people behave. Do they jaywalk? What do they do at different intersections? Another kind of cool thing working with this kind of data, if any of you work with, I'm sure a lot of you do, if you work with vision and video, it's backbreaking to touch all the pixels. What's kind of nice about this data is you just work with points, XY tracks. So you can actually do sort of large scale stuff. So I encourage you guys to sort of look at this space. It's like a lot of sort of tracking sort of machinery can be reapplied there. So we have our own sort of work on trying to estimate the position of people when they're occluded by forecasting. And one of the magic tricks we use is if we can reason in 3D, we can start saying, oh, the reason why I can't see someone is they're behind something else, like behind an occluder. It turns out there's lots of now monocular depth estimation methods that are pretty robust. It's like this video amazes me. Now this is just this is not a video that this network is trained on. We just sort of downloaded this and ran this, and the fact that it works this well is kind of remarkable. And you can imagine now this gives you a way when you're trying to forecast to kind of do it in 3D. We can sort of say the reason why I can't see someone is because they're moving behind another occluder. So this is a version of the argument that Jitendra gave, that basically if you're trying to analyze how things are, if you're trying to track, sort of doing it in 3D allows you to reason about when you can't see something, why can't you see something? Well, because it's occluded. As you mentioned, Pavel, I think you'll talk about work like this as well. So you'll hear more about this philosophy in just a second. And finally, this argument about sort of reaction times and the fact that we have to forecast. One perspective is this is all sort of engineering details that need to get right for if you really want to build a self-driving system. But my argument is that humans do this. So humans very famously have a reaction time of around 200 milliseconds. The time it takes for you to see a percept in your retina before you can like move your motor neurons. So that means if you're going to do high skilled maneuvers like hit a baseball that's moving 100 miles an hour, you must be forecasting and reasoning about velocities, because the actual signal that you use to move your hand is very stale. The ball's over here, but you're moving over here because you expect it to be here. So this seems to be an important part of even how humans kind of perceive and act in an embodied setting. Okay, so first, this idea of sort of streaming perception, I think, suggests that maybe there's other ways to think about tracking where it emerges. And I want to sort of push on this idea a little bit, this idea of what is the role of tracking in embodied systems. And so again, I'm guessing most folks here don't necessarily work with 3D data, but this is a rich space that I invite you guys to think about. I think there's lots of cool versions of the tracking problem here. And typically what happens in these sorts of autonomy stacks is that you have, you start with a bunch of 3D sensing data, you run a detector, and then you stitch detections together by associating them, the classic track by detection paradigm. And then once you stitch detections together, you get these XY points and you project where they're going to be in the future, forecasting. And then you use that, you give it to a planner that makes sure that it can move the car in such a way where it's not going to hit something in the future. And so something that we've been quite excited about is maybe we could simplify this and instead sort of do this directly. So given a LiDAR sequence, can you just directly run a detector that spits out boxes with forecasts of where they will be in the near future? And usually when I mention this to people at some level, this is kind of like there's no tracking in here at all. So it seems really strange. But one sort of striking thing that I want to point out is that virtually every 3D detector, if you go download a LiDAR detector, it already does this. So there's something kind of remarkable in the space that if you download a LiDAR detector, it not only spits out boxes about where things are, it spits out little arrows about velocity that gives velocity estimates of where they'll be in the next frame. And so I think this is one huge evidence of like something that's very different about 3D data versus 2D data. Like right now, if a student came to me and said, I want to detect a car in a video sequence, I'd say start by running MaskRCNN or Swin Transformer or some single frame detector. That just processes a single frame. So that always breaks my heart a little bit that we can't do better with videos. We can't actually use some multi-frame thing rather than just stitching the detections after the fact. But in 3D data, that's not true. If you want to find a car in 3D data, the state of the art already makes use of multi-frame detectors. And I think one reason why is because it's much easier to align ego motion. You can factor out the movement of the camera because you know how that's moving. So you get these sort of aligned sequences. So to me, I'll even sort of show you like a visual of what this thing sort of looks like. Is yeah, it takes a second, but essentially, this is just the output of a multi-frame detector. So what the detector takes as input is multiple frames, and it spits out forecasts of where it expects things to be, except now we just train it to spit out more forecasts. Spit out the next 10 frames or 20 frames. And my claim is this is actually what's digested downstream. So downstream, it doesn't actually look at the tracks. And in some ways, this thing, maybe it's okay if this flickers, because what this represents is, this statement that, oh, the perception system didn't realize there was a thing there before, but now it does. And so that's okay for it to change. And so the claim, though, is that if we really want to do this, we can train detectors for doing this. And essentially, it's just reusing the existing machinery that you already use for detection. But now the claim is if we train detectors to not just to spit out attributes about where things will be in the next few frames, the hypothesis is that internally, the detector must be doing some kind of tracking. So the claim here is it's not that tracking is not important, but rather the tracking is emergent. That if you set the criteria as the actual output that's going to be used downstream, and you optimize for that criteria, hopefully internally the network will try to, in order for it to really understand, to produce good predictions about where things will be, it seems like it really has to understand how things are moving. But what's nice though is that oftentimes sort of tracking losses in metrics are kind of hairy. You have to deal with track births and track deaths, and here none of that, you don't have to deal with it. It's much more sort of simple and straightforward. So And in fact, the way that we do this is surprisingly simple. Even the first thing that we tried is, instead of actually modifying detectors to spit out, lots of arrows about where things will be in the next 10 or 20 frames, we do something even simpler. We just modify the detector. We just give it a bounding box for a car 20 frames in the future. So we almost tell that from the detector's point of view, this is another category. It's a future car as opposed to a current car. What's nice about defining it this way is that now it learns features that are good for spitting out the location of future cars. And so if we do this, we can actually train a detector to spit out both current cars and future cars. And then finally, we have to do something where we sort of stitch things together if we want to get sort of coherent tracks. Okay, so it turns out that this actually works pretty well. And if you evaluate this on sort of end-to-end metrics, let's see, there's this whole other kind of difficulty of, now if we're going to kind of unify perception in some ways, to say we're going to detect and forecast at the same time, we need to come up with metrics that evaluate detection and forecasting at the same time. So the way forecasting is typically evaluated is you assume you're given ground truth tracks. So, but there's always a disconnect between this and what actually happens in the real world, because in the real world, maybe sometimes I don't even see a car that's there. And so, of course, I'm not going to get a good forecast for it. Or maybe I have a false positive detection, and so I hallucinate the location of a car. You sort of have to deal with like false positives and misdetections while you deal with bad forecasts. So there's this other difficulty of how do you come up with a metric that combines the two? And it turns out that previous attempts at trying to do this, so we were by no means the first ones to try to unify these different modules. But it turns out that if you try to come up with metrics to combine the two, they're gameable. And one intuition is that you could try to only predict cars that are stationary, and those are really easy to forecast because they're not moving. And so if you do that, you can kind of artificially do well on some of these end-to-end metrics. But what it's saying is that's not really the right way of measuring this accuracy. So we have other ways of kind of doing that. But maybe the take-home message here is that basically the forecasting community has spent a lot of effort of saying, well, the problem with trying to understand future behaviors is that most of the time things are really boring. Like most of the time things might not even be moving. So you really have to be careful about finding interesting behaviors at the very first token. Just focus on things that are moving. And then secondly, focus on things that are moving in interesting ways, not just sort of with linear velocity. And if you kind of bucket things based on stationary versus linear velocity versus nonlinear velocity, you can now show that this kind of future detection works quite well, and is actually much better than this. Trajectron++ is one of these classic pipelines that just actually tries to explicitly track and then do forecasting off of that. So this to me is kind of super sort of provocative about what is really the role of tracking in this online setting. And once again, the way I would say that it's not that tracking is unimportant, it's that maybe that it's emergent. You just set up your losses in one way and then the network learns to do it. The other perspective on this is that in order to train this thing, you still need tracks, because that's how you get all this training data of where cars will be 5 seconds in the future or 10 seconds in the future. So it could be that the role of tracking here is really more of an offline labeling exercise. It's a way for you to kind of understand how things are moving. And once you understand that, you basically repurpose a tracking data set for this joint detection and forecasting. Okay, so I wanted to sort of leave that as perhaps a provocative idea. Oh, and another way to think about this is that oftentimes the way that a lot of these methods work for detection, you kind of start with like a bird's eye view image of LiDAR points, you process that, and you spit out detection bounding boxes, you stitch them together, and then you try to estimate trajectories about how they'll behave in the future. But then sometimes in the way in which you forecast is you actually take all of these trajectories, and instead of working with them in some sort of XY space, you actually render them onto an image, and you actually work with sort of 2D tracks that are rendered onto some 2D grid. And all of this just seems clunky, and instead you can just go directly from this continuous representation to this discrete set of objects plus little curves that spit out of it. Okay, So that's sort of an argument that maybe for a sort of online settings, we could think about tracking in different ways. And then finally, I wanted to kind of conclude with a little bit of work on kind of open world perception. So something that I've always kind of wrestled with is, if you think about being able to track in an embodied setting, how do animals do it? Because it doesn't seem like they have, you know, detectors for cars and trucks. It doesn't seem like they follow the sort of pipelines that we build. And of course, there's lots of sort of well-known evidence from the sort of biological vision community that suggests that motion plays a really crucial role. So we've looked at approaches that really make motion and flow a first-class citizen in understanding how things are moving over time. And one thing I wanted to stress here, okay, this is the little foray into synthetic data, is that hopefully folks in this room know, but I feel like this is insufficiently known. And I feel like there's been sort of a quiet resolution or a quiet revolution in motion estimation using neural networks. And I think it's been facilitated from the use of synthetic training data. So you can train on flying cars or flying things 3D, use that to get annotations of how things are moving, and then train networks to spit that out. And it seems, you folks can correct me if I'm wrong, but it seems like one place where like the sim to real gap seems like that's already been addressed. Because right now you can get pretty remarkable motion estimates from these things trained on synthetic data. And so we're going to sort of use this as sort of a first-class citizen for understanding how to detect and track things, even things we might not have pre-built detectors for. So here's sort of like a shameless advertisement. So I know that we've been talking a lot about synthetic data, and even using synthetic data to train maybe not just optical flow estimators, but SFM modules that return back how the camera is moving as well as how points in the world are moving. Something that we've been looking at is repurposing tools like NERF for large-scale scene synthesis, and this just works remarkably well. So this is actually data that we collected from a drone over like a square-mile region. Okay, and you have to do some fancy stuff about how to train at scale, but it turns out you can do this, and you get back like really high-quality, photorealistic, virtual fly-throughs. So the claim is that we have geometry for, we have camera poses for, and you have rendered pixels for that looks pretty realistic. You can almost use this as a data set for learning from motion. Of course, this is still static scenes. But there's a poster on this, so I encourage you guys to talk to Hytham, who's the lead student author on this. Okay, so getting back to this notion of we can learn from whatever kind of synthetic data, pretty good motion estimates. Let's see here. Now, do we know, can you remind me how much time we have left? Okay, sure, no problem. Well, let me skip this for the moment, and say something that we've been pursuing a lot is this idea of differentiable rendering. So much like the incredible progress due to NERF and differentiable volumetric rendering, we've been trying to look at it in the context of, well, what happens if you have dynamic scenes, things where the world changes, things can appear from behind an occluder. And so essentially, we've been pursuing the same approach of, just start with some hypothesized shape and differentially render the world until your shape matches the image that you see. And the one wrinkle that we add that for some reason, very few other people seem to add is, instead of just matching pixel data, we also match flow. So we extract flow from these state-of-the-art networks and say our hypothesized interpretation of the dynamic world, we render that and produce rendered pixels and rendered flow. And we just compare that with a measured flow, and that's another signal for learning. So the advantage that can give you is that essentially, this is one way of what I claim is doing like 3D tracking that's not data-driven. So in the same way that classic NERF just optimizes a test time, this is just optimizing a test time. And so although you've arguably seen reconstructions like this before, for things, particularly for things like people. Oftentimes that's really done in a data-driven way. You have like thousands of scans of people that you collect and you build some, PCA model. Here, there is no data. It's just optimizing a sphere so it can deform and better match the pixel data and the motion data that you see. So the advantage is that now, you can match a camel really well because there's two humps. And we're not going to have anytime soon a data set of 10,000 camel scans. So somehow I very much sort of believe this idea of like, if you listen more to the data at hand, the pixels at hand, rather than your sort of prior conceptions of what you've seen, then I think you can get sort of more higher fidelity out. So we have some versions of this. Gangshen will talk about this on Tuesday, but essentially, one way to think about this is it's also like a philosophical agreement with Jitendra about maybe the way that we track is we really make 3D a first-class citizen. But maybe, one difference here is that we're trying to make this much more generic, where you don't have to have scans of people ahead of time. You just really lean into this notion that of differentiable rendering. I'm just going to hypothesize some interpretation of the scene that matches the pixel data and the motion data that you see. And here again, I guess tracking is almost like a byproduct of the reconstruction. It's almost tracking by reconstruction, if you will. Okay, so maybe I'll sort of end up there. So like hopefully the three take-home messages was, riffing off of this sort of first question of rethinking the role of tracking for embodied perception. So one is if you want to deal with the fact that data comes at a particular rate and we want to react to changes of the scene, maybe we can embrace more kind of streaming loss functions where they suggest tracking is an emergent tool, but not necessarily the only one to solve that. And if you really embrace a more end-to-end perspective, maybe we can just detect and forecast what's going to happen in the future. And it could be that in order to do that, networks have to sort of learn how to track underneath the hood, but I think this might be an easier loss function to work with and optimize. And finally, if we really want to handle sort of open world sort of video processing, the bet that I think we're making is that we can really leverage all this incredible work on like 3D differentiable volumetric rendering and kind of have that be almost like a first-class citizen for how we analyze videos. Okay, maybe I'll end there. Sure.
Talk about the multiple graph truths data that would be necessary for multi-frame models to do these predictions. What would that ground truth would be? And I'm thinking about the synthetic data world. You can actually generate a lot of ground truths. I would like to know what would be the most useful for this kind of.
Yeah. So you could imagine that, let's say for this middle stuff, what's really useful is to have detailed tracks. So in a weird way, tracking is still needed under this sort of story or vision for training, because you need to know where things are, or in particular, where things will be in the future so that you have a target for learning. So you could imagine having that very detailed labels of where things are and how they're deforming in the future as like the targets for future prediction for forecasting.
For example, motion vectors.
Yes.
Single pixel that could be part of the inside of opticals that you already know, and the role position of that object.
Yeah.
Motion vector can make you forecast.
Yeah, exactly. One thing that I would say is that one thing that we're sort of starting to believe in more and more is that we should really be doing this in 3D. So rather than sort of forecast in 2D, I would say if you forecast in 3D, then somehow it's a more sensible thing because then you understand, oh, it's actually moving with constant 3D velocity, even though the image projection could be different. But you pay a price because now you have to sort of reason about 3D stuff. But one claim I'd like to make is I think there's been like incredible advances in this sort of NERF-like reasoning. So I feel like there's a role for that body of work to play in the tracking and video processing community. Yeah.
Great talk about. There is so many
different representations for 3D, right? Like, you talk about nerves with volumetric, you talk about LiDAR versus with also images to 3D from images. Do you see one kind of like unifying way to think about inputs in this many different type of modalities where your conclusions get transferred across this different modalities or maybe the other?
Yeah, good question. I don't know if we have any particular insight there. Yeah, I mean, right now, I kind of like these sort of like voxel-based representations just because, you know, from a vision person that works on images, it's sort of the natural transition to that. But then they tend to be kind of heavy duty and clunky. But I do like even the visualizations that I'm showing here is that the 3D oftentimes is you know, bird's eye view. We're seeing a lot of work in this space. I actually find that kind of intriguing where it's 3D, but if you do bird's eye view, you can still kind of make do with 2D processing. So somehow it's a way to cheat. So that seems like a nice maybe middle ground, but clearly there's places where that fails, where you know you're changing your height above the ground. Go for it.
Hi.
Hey.
Really great talk. I was wondering, because you mentioned product, so I was sort of wondering the role you think in the future of action. I'm driving a car on a stop sign on a slow down so I can learn more information. So there's actually a component where your action affects your perception. So how do you think about that? Where do you think you need to start incorporating action?
Yeah, it's super great questions. So there I think about, okay, just given, you know, we're sort of vision researchers and maybe we sort of live and die too much by data, but that's where I would start. So one thing is that, you know, we've really benefited from having large scale data sets that keeps us honest, make sure we don't just sort of go off in Lulu land. And I think for behaviors in action, that hasn't quite been the case, but I think that's kind of changing. And so that's why I want to sort of advertise, so if I really want to learn a model about how perception and action sort of related, I would start with, okay, give me large scale juicy data of perception and action of behaviors. I think that's kind of hard to build. And all of you know this, because just working with a video is backbreaking. Like I almost feel like there's only, it's not a very democratic sort of AI playing field. You need crazy resources to really play in that space. So that's why I'm kind of intrigued at these kind of like sparse behavior data sets that are like based off of points. Maybe there's a place to start learning because at least we can, you know, do kind of scalable things there without having crazy cluster compute demands. Yep.
So I'm pretty interested in this like learned, you know, forecasting the LiDAR that you showed. But I think there's one major thing missing there, which is like the explainability, right? Like there's something that I think you didn't really touch on, like the classic paradigm of detecting and finding the correspondences, and then, for example, like Kalman filtering all of these tracks to get like an explainable classical model. I was wondering, like, if you had any opinion on, you know, like really.
Yeah, that's a great.
Which one, like, any pros or cons there?
Yeah, it's a great question. That's one of the arguments for these more modular approaches is that, oh, okay, now we can, if we screw up forecasting, maybe we can explain it because, oh, we associated the wrong detection with detections together. So that's why we have a wrong forecasted estimate. So I don't have a great answer, but here's one thought is that, so there's this other claim that we're making that we don't have any proof for, which is tracking is emergent. So as in we think that internally the features that this network must be computing sort of know how things are moving. So one thought is that maybe we could actually add that as another task. So not only do you forecast, you precast. And so one hypothesis that if we add that as a task, actually that's no big deal because the claim is that information is already there in the features. So if we just add this as a task, you know, we don't really need extra layers to do this. But if that's the case, you could say, okay, well, what's the benefit of even doing it? Well, one thought might be it's almost reporting out like an explanation. It's saying, this is how I think things are moving in the past. And hopefully that's one reason why I'm predicting this future thing as is. So it's almost like we're training additional tasks, almost as like explanatory tasks. And the hypothesis is that that should be no big deal because it should be doing that somewhere underneath the hood. Although, you know, in practice, we don't know where. And so it might be tricky to actually wire stuff up correctly.
Right, it's like a scary black box almost, like, you know, that part.
Yeah. Go ahead.
Yeah, I was wondering something similar actually. So however, I didn't hear, I guess, what model you're using or how you're modeling the sequence here. Because you're talking about, end-to-end and from the LiDAR input, you're obtaining forecasts. But then, I mean, the way like it's traditionally done, right, is tracking the modular pipeline, you maintain the tracks over time, so you kind of have this sequential input. Even model at LSTM, but are you taking multiple frames as input here?
Yeah.
That scale, longer sequences.
Yeah, totally fair questions. You could imagine that if you really want to forecast something long, then you probably need to like reason even more about the history to sort of understand longer term how things are moving. So one thing to sort of emphasize that people may not realize if you don't work in the space is that you just download a 3D detector, it's already multi-frame. That to me is kind of shocking because that's not, I've never seen this in the image world. Any image detector you download is not multi-frame. And you can ask yourself, why is it so different? Why is that almost easy to do or the default in that 3D with LiDAR data and it's not in the image data? And I think it's because it's with 3D data, it's much easier to factor out camera ego motion. So I'm not showing this here, but we can align all of this to a global coordinate frame. And so that means we can tell when sort of points are moving, if it's not due to like us moving, it's due to the, something went off. It's due to the like scene dynamics. So, no worries. So the hypothesis is that, so the higher level point that you're making is that, don't you need to really do this over huge amounts of sort of like temporal windows? And if that's the case, don't you want to do some kind of stateful logic like recurrent processing? I totally believe all that. But the way that I would kind of address this is it's almost like a speed up of a multi-frame detector. Like, so in fact, even when you look at multi-frame detection now, it's already doing this. It's already, looking at a scanning window of the past 10 frames, and it's shifting over by one frame and it's running it again, and it's shifting over by one frame, running it again. And you're totally right that I share the same intuition. That seems really wasteful because 9 of those 10 frames I've processed already. So can I reuse something? And I think you can, but the way I would think about that is like there's some way to like reuse sort of features so that you don't have to start from scratch. I don't know if that's making sense, but like you can almost like recurrentize a multi-frame detector.
You could, is that what you're doing?
No.
You're taking multiple frames of input, or you're trying to, I guess, projecting the sweeps into the current ego frame?
Exactly. So right now, if you download a 3D detector, that's exactly what it does. It takes, let's say, 10 frames, it puts them into a globally aligned coordinate frame. So then the points that you see that are moving are just the stuff in the scene that's moving. Yeah. Yeah. Okay, thanks.
Okay, so next we have a talk by Pavel Tokmakov. He's currently a research scientist at the Toyota Research Institute, where he studies object perception in videos. Prior to that, he was a postdoc at CMU, working with Martial Hebert and Deva Ramanan. And together with Deva, he created the Tau benchmark for large-scale vocabulary tracking in an open world. He obtained his PhD at INRIA under the Cordelia Schmidt and Kartik Alahai supervision, studying the role of motion in object recognition. Pavel, take it yours.
Thank you for the great introduction. And one thing which I will have to add to this is that I tend to speak very fast, and I will do my best not to do that, but probably I will fail at some point. So feel free to just tell me, okay? Because I'll just finish it in 10 minutes and you will not get anything. So let's not go there. Yeah. All right, cool. Oops. That's not good though. How do I? Yeah, okay.
Maybe let's stop maybe, and we get the technical guy to fix the audio thing.
Oh, okay. There's a problem with the audio. There's a problem with the audio. You mean?
Can you notice the noise?
Oh yeah.
Yeah.
Is it okay? Yeah, yeah. Oops.
So the audio is plugged in where?
I don't hear maybe. Yeah.
This way, right?
Okay. Okay. Are we good?
Yes.
Okay. All right. So yeah, I think if you're okay, I'm okay. So let's go. Yeah, right. Like you mentioned, I work mainly on object perception and videos, and that's the reason for that is that I believe like the most interesting problems in object perception, they are in videos, not in images. And like David was mentioning it, that he's frustrated that all like kind of the image models don't use videos. I would like detection models don't use videos, right? But I would go even further. I would say like the actual problem of object perception should only be studied in videos. I think almost like studying in images is a mistake in a way, you know. And I would go like into like what do I mean by that? But anyways, as you can see, I'm very excited about objects and videos, and there are a lot of kind of interesting challenges there. And one of them is for me like localizing invisible objects, and which is what I'm going to talk about today. And in particular, I'm going to talk about in the context of multi-object tracking. So of course, like for this audience, there is no need to explain what multi-object tracking is, but I will still give a definition, and because I think it is important, this definition, right? So it's typically defined as localizing and associating all the objects in the video, like in this case, cars and people, and associating them over time. And why I'm saying this definition is important because people actually tend to take it literally. Like they actually first localize and then associate. Like they take these two tasks differently, the two tasks separately. And I mean, yeah, so what, in particular, like most of the approaches in this field, as we already saw today, right, in this challenge, and I mean, as you all know, they operate in the tracking by detection paradigm. And again, like, oh, you all know what it is, but I will still illustrate it like that. In this case, you treat a video as a sequence of independent frames, which are ordered, but they're independent from each other. And the first thing you do, you apply an image level, like a boring image level detector. Oops, I'm sorry about that. Right. So first thing you do is you apply an image level detector to each frame individually. And then you take your detections and you associate them. And for that, you use location information, appearance information typically, right? So boxes which are close to each other and they have similar appearance, those belong to the same track. The interesting part, of course, comes what happens if some detections are missing. Like in this case, the black car is occluded and the other car in the front went out of view. So like now there are no detections, obviously, because you only have that one frame. So what do you do in this case in the tracking by detection paradigm? Well, nothing really, you just keep those detections, right? And you hope that the objects will reappear later. So if they do, like this car getting out of occlusion, so what you do is you reassociate. And so for those objects which were not visible in the previous frame, you use like, again, appearance information, which hopefully didn't change so much. And then you use like motion heuristics, like for instance, people typically use like constant velocity post-processing, right, to propagate the box in the camera frame. And like, I mean, there is nothing fundamentally wrong with this in the sense that it does work really well. Like that's why people use it, right? It's a very simple approach. Like somebody said, it's very interpretable, and there are a lot of domains where it does just great. But then, of course, it has limitations, right? Like this, for instance, if the camera motion is strong, and your constant velocity motion model is going to fail. And then there are work like that work from Dell, for instance, right? Where if you do that in 3D, then you can compensate for that. But still, I mean, heuristics are brittle, right? And another, of course, like if your appearance changes behind occlusion, then the appearance identification will not help you, right? So there are a lot of these practical limitations. But to me, you know, what's the most motivating thing about this is that it's this approach of like first obtaining detections from static images and then associating them as a separate step. It's almost the opposite of how the human perception works. And I want to illustrate this, I think it's best shown by this simple example from Gao and Scholl. So here in this video, you can hopefully all easily detect and track those two cubes which are moving in the field of random noise, right? You don't have a problem with that at all whatsoever. Yet, if you try to apply tracking by detection to this, it will fail miserably because those objects, they only exist in video, right? They don't actually, like, in a static frame, they're just not there at all. And so this, of course, this is an extreme case, and most of the objects we have to detect and track, they do exist in static images, right? But this is just, I think, a strong illustration of how different our visual system is from this tracking by detection paradigm. And as cognitive science claims it is, right? Okay, we have no idea how our brain works, but there are some theories, and some of these theories claim that actually temporal consistency is the primary key used in humans to both localize and associate objects. So an appearance only plays a supporting role in that. And this design is what allows us to handle like crazy amounts of sensory noise, like in this video, for instance. And in addition, something I'm going to talk about more in this talk, it allows us to hallucinate detectors of occluded objects. So what do I mean by that? Let's look closer at that. So in this video from a synthetic Cater dataset, let's look at this golden sphere. It gets covered by several cones and then uncovered, right? And then the camera is also wildly flying around. And yet at least two things are clear to us, right? So that sphere is still there. Like when it's appearing from the view, it didn't disappear from existence, right? So for us, that model of the sphere, it does not directly, it's not directly related to perception, or to sensory inputs. And second of all, it's not only didn't disappear, we actually know where it is. Even if we don't see it for a few seconds, we know pretty well where it is. So how do we do that? Again, nobody really knows, but one theory, which is relatively popular, is the object file theory of Kahneman. So this theory literally suggests that we represent objects as files. So what does it mean? Is like, let's say we see the scene, right? So first thing we do, okay, we use appearance, we use sensor information to instantiate these objects, but then we create objects files in our mind. And those files remain there. So like then at the next time step, when we see the scene changing, what happens is the files attend to the sensory input and they bind and they establish correspondence. And then they get updated for inflation. And then what's important is that next, when the golden sphere completely disappears behind the red cube, we still can localize it because it still remains in our mind, right, as an object file, right? Although there are no sensory inputs anymore, we can still establish correspondence and estimate its approximate location. And this is what is called untethered perception, right? The untethered object representation, saying that our representations of the objects are untethered from sensory input. They are using it, but they are not directly married to it like they are, like in tracking by detection, where they start from the sensory input, right, at every time step. Motivated by these ideas, we try to incorporate something like that into modern tracking by detection approaches. And for that, of course, the first step is to be able to capture like long-term temporal information. Again, something David has discussed, right? That your models have to include as much temporal context as possible to reason about those issues, right? To reason about those cases. And our approach can be applied to any tracking by detection framework, but we chose the elegant center track formalism to illustrate it. And again, the center track, right, it takes, as most of you know, frame pairs as input, and then it this frame pair, it localizes objects with their centers, and then it predicts offset vectors to associate those objects between frame pairs. So yes, it doesn't operate on single frames, but it's still completely local in nature. And those it cannot by itself handle even the simplest forms of occlusion. So a first step for us to address that was to turn this model into a video level model. And to this end, we created this architecture, which we call PermaTrack, which takes now videos as input. And it processes those videos frame by frame, first to extract features, kind of like a document detection model. But what's important is that it then aggregates the representations of the frames with a recurrent module, like in the special temporal recurrent model. And which now kind of, now we get this feature map at the end, which does not just encode this frame or previous frame, it encodes all the previous frames. And it can actually encode, as I will show next, information about previously seen objects. So far what we do is we just go with the center track framework and just localize all the objects in this video with the centers using this recurrent representation. But the difference is now is that we actually localize both visible and invisible objects. So what allows us to do it is, again, I will just go in a little bit more detail here. So although maybe it's simple, but I think it's important to understand is that, again, like with any kind of single frame detection model, right, its appearance, its encoding of the frame is fully determined by the appearance of the corresponding pixels, right? So if you encode this frame here with a CNN, then in your feature map, right, the pixels corresponding to object locations, they encode the appearance of those pixels, right? So then in the next frame, when the person gets occluded by the red SUV, if you again can encode with an SVN, obviously nothing too surprising, those pixels encode the SUV, so you can never localize the person anymore, because the model doesn't know about the person anymore. And the biggest difference here, which recurrent encoders give you, is that now your feature map is kind of like object files in a way, right? It's untethered from the actual frame, right? So now your feature representation does not have to encode the appearance of the frame. It can encode anything else, including, for instance, the appearance of the object which was seen in the past, but now is invisible. Appearance and locations. It's important that it's a special temporal memory model. It knows both space and time. So what it allows us to do now is we can simply train our model to detect and track both visible and invisible objects uniformly, right? So it's otherwise exactly the same as center track. So it's that's like a big advantage. It's conceptually a very simple approach. It allows you to track invisible objects. So yeah, this is a very simple approach, but of course the biggest question actually lies in how you train it. Like, where do you get the data to train it to localize invisible objects? And I mean, you might have guessed that I'm talking at this workshop for a reason. We did find the answer in synthetic data. And I find it quite, this is an example from Flying Chairs also, as Hideo was mentioning, one of the original applications to take data and to computer vision. And so it was used for optical flow estimation. And the reason, again, you see the video is completely unrealistic, but still they were useful, and because although they didn't provide any realism, but they provided unique supervision. Because optical flow estimation is another task which is notoriously hard to get ground truth for, right? So in the real world, it's really hard to label, but in synthetic data, it comes for free for you, right? So this is where we're going here, obviously, right? We also want to do the same with our problem of localizing invisible objects, but of course we want to use more realistic videos than that. And in fact, even like back in 2016, 2017, 15, Edwin actually did this paper, right, where they went way further than Flying Chairs in realism, right? They had this virtual kitty data set where, of course, like it's not as realistic as some of the things are today, but 2016 was a huge step, right? And it, for instance, right, also provides you all the bounding boxes for all the objects, even if they're invisible, because a rendering engine has to track all the objects in the scene, whether they're rendered or not, right? So you kind of get those invisible object labels for free in this data. And fortunately for us, there has been a lot of progress in synthetic data since 2016. And we actually were able to use this synthetic data set from Parallel Domain, which is a private company which focuses on data realism. So you can see here that this video is like a lot more realistic than what we had like 6-7 years ago. And but they also provide us this unique ground truth annotations for invisible objects, again, both for people and for cars and for other agents. So for us, the only thing left for us from here was to slightly pre-process this data, because the only thing we did is we removed all the annotations of the objects before they first become visible. Because it, of course, doesn't make sense to try to train a model to localize invisible objects if the model did not see it before, right? But this simple pre-processing step is the only thing we needed to do. Beyond that is our models as simple to train as center track, using this synthetic data with ground truth labels for invisible objects. So let's see how well it does. So we compare to center track, and first thing we do is we apply the standard constant velocity post-processing in the camera frame space to center track, and it does help. It does improve the performance, but by only a small fraction, largely because in this dataset which we have with street driving scenarios, the ego camera motion is quite strong. So the constant velocity in the camera frame is not really doing that well, right? Our learning-based method, which learns to account for the camera motion in the 3D space, it does like much better and improves significantly here. And qualitatively, as we're going to see here, in this highly dynamic scene, we can see that on the left, the cars which get occluded by the black car, they get correctly localized by our model, even when they are invisible, right? And this is no post-processing, this is just a pure output of the model, right? So it can actually learn to account for both object motion and camera motion at the same time. And moreover, it doesn't only work on cars. In this complex scene with pedestrians and cars, we can see a person-person occlusion here, and then there are another person-person occlusion, and those people are going to occlude the car. And again, our model can localize all of them accurately, right? So the question is now, is that all you need? Is this simple model just solving object perception behind occlusions? Well, are there any serious limitations? And I would say certainly yes. One of the limitations is, again, like it's not probably going to fly too well on this workshop, but I think relying so much on synthetic data is a weakness, it's a limitation, right? Because, I mean, yeah, we can get that data right now easily, but okay, in the street driving scenario, right, we have lots of companies who generate this data for like outdoor driving scenarios because there's a lot of money into it from like the EV companies, right? But anyone who's worked with those companies knows that how they achieve this incredible amount of realism and scalability is that by limiting the environment as much as possible. So they can only generate that data, right? If you ask them to generate, okay, maybe like kitchen videos, right? They'll have to create a new company for that, right? That's like, these virtual worlds are very, very narrow in domain, right? So it's of course like an object prominence is something you want to capture, like it's generic in the world, right? So if for every new domain, you have to create like a new synthetic data company, that's not a very scalable approach, right? But I would say even beyond that, even if we could solve that, if we could have a simulator for everything in the world, our model has a deeper, more serious limitation, which that would still not address. And I will illustrate this by this, again, synthetic video, where we can pay attention to this person walking behind the bus stop. So the person walks behind the bus stop and then he stops, right? And that's easy for us to see because we have the ground truth. But let's say now have the same video without the ground truth. Can you tell exactly where the person is? I would say probably not. And in fact, that's quite natural to us. And when we as humans reason about occluded objects in this kind of highly dynamic scenarios where the objects have agency, we do not exactly estimate their location. Rather, we form a probabilistic belief about where we think they are. And we use a probabilistic belief to then plan our actions, for example. And this is something we wanted to address. So like we want to address kind of both problems I mentioned at the same time, both the reliance of ground truth data for supervision and the kind of the uniform treatment of visible and invisible objects in our framework. So to this end, I'm now going to talk about the self-spread object we propose, which learns to build a probabilistic belief about the invisible object location without any invisible labels, purely from the data. And to this end, we capitalize on the recent and amazing random walk framework of Jabri et al. So what they propose is to model videos as random graphs. And the nodes in these graphs correspond to patches in every frame. And what's going to be very important for our story is that those patches are encoded by CNNs. So that every patch is encoded separately, and you get a feature vector. And that feature vector is the representation for your node. And then the nodes in consecutive frames are fully connected, right? And the edge of each edge has a weight, so it's a random graph, right? So the weight of the edge is the similarity of the patch embeddings in the feature space of the network. So basically, in this case, since the patches are encoded by CNN, it's entirely defined by their appearance. But still, like, it allows tracking, right? So now to track this patch, for instance, all you need to do is you initialize a matrix with of the size of the number of nodes, with 1 at the location corresponding to this node and zeros everywhere else, and then you multiply it by the similarity matrix between the nodes in frame 1 and frame 2. And that now, like, let's say if the similarity between these two patches is 1, right, then you will now have again a 0-1 matrix at the correct location. Of course, in practice, it's not going to be exactly 1, so now you have like a probabilistic belief at this step of where your object is. And you can continue that to track that object for as long as you want. And so this is called a random walk on a graph. And as I have shown, object tracking, like rather point tracking, can be modeled as a random walk on such graphs. And what's very important for us is that now the state of the walker naturally represents the probabilistic belief about the object location, right? So it is not just a binary thing, it's an actual like, a belief state. And another important thing about this framework is that instead of supervising the walker at every time step, which would require temporally dense annotations, they should supervise every k steps. In particular, they use a palindrome training, but you can use like any kind of sparse supervision which you have. So as you might have realized, this framework falls really well into our problem setting, right? We only know exact object locations before and after the occlusion, and we want to learn to form a probabilistic belief about the object location between those points in a self-supervised way. And this is exactly what this framework allows. The only thing we need to do to get there is to apply it not to individual patch encodings, but rather to a spatial memory. So again, consider this example from the stoichiometry dataset. And like here, the golden sphere is occluded by the green cone. And like imagine the edge between those patches in the original center track, right? That edge weight would be defined entirely by the appearance of the patches. And here, the appearance of the patches is completely different, right? So there would be no way to learn this transition. But if you instead encode those frames with spatial temporal current memory, then your walkers, the weights of the edges are no more defined by appearance. Again, they're now untethered from sensory input. And the weight of this red edge here can be trained to be high, even though the appearance of the actual locations is not related. Right, so in detail, like what we do to train this model is for a given sequence, we start a random walk from the center of the object which we want to track in the first frame. And then for the frames where the object is still visible, we directly supervise the transitions, right? So since we have the ground truth here, so we just directly tell the model, okay, that's the edge which you should use, right? But then during occlusions, there exist multiple paths through the graph. And we do not enforce any single hypothesis. We just allow the model to take all the walks and form its belief. And then we only supervise it once the object reappears. And what it does, it shifts the probabilities in the graph towards trajectories which are more likely to result in identifying the object once it reappears. So effectively, the model learns the most likely trajectories the occluded objects can take from the data without any explicit supervision or assumptions about the object dynamics. And what's even better, because it forms probabilistic beliefs, it can now actually, implicitly model different scenarios, different kind of futures, right? So, and form, as I will show later, actually, examples where it can actually model uncertainty about object behavior. So yeah, let's see how this actually works on these two examples from the Cater dataset. So first here we see this golden sphere. It gets excluded by the red cube, and the model in this complex scene, it doesn't give you exact prediction of where the object is, but it rather gives you a probabilistic belief, which is shown in the heat map here. And then as the object reappears, the hypothesis converges to the actual location where it reappears. Even more interestingly, here we see the sphere getting covered by one cone first, and our model can handle this as well. It still understands that the object is there. Even as the camera moves now, it still understands that the sphere remains under the cone. And even as it's occluded by the second cone, we can still handle that, and we can still correctly localize it. And we will later see that this cone is going to lift off, and the model will still correctly understand that the sphere remains under the first cone, not under the second one, right? And in the next video, first we will see again that the sphere is covered by one cone and by another cone, all the same stuff. But later something a bit more interesting will happen. So now these cones will start moving together, and the model will be able to understand that the sphere actually moves with the cones, right? It kind of becomes a part of the cones after it's covered. And again, what I want to emphasize here is this is entirely learned from the data without any explicit supervision or assumptions embedded in this, right? So okay, this looks pretty cool on this toy data. How does it work in the real world? Well, we first compare to our prior work on synthetic data with this realistic driving data set I showed you before. And interestingly, again, we can see here that our self-supervised model actually outperforms the fully supervised model, which is something you don't see all that often, I would say. And again, this is not just an artifact of synthetic data. If we go to the Kitty benchmark, we can see again that in the real world, we also outperform our prior fully supervised work on both like car and person categories. So what is going on here? Like I would say that the reason is that this is again like, reasoning about invisible objects, and that's why I'm saying like that all the interesting object problems there, or like most of them are in the video domain, because reasoning about the invisible objects is an inherently probabilistic problem, right? You have to capture uncertainty here. That's why actually here using direct supervision is suboptimal. And having this self-supervised probabilistic objective actually gives you benefits which even like full supervision cannot give you. And I'm going to illustrate this some examples. First, okay, we just see like this simple example here, right, where a person is occluded by a moving car, and our model can correctly localize the person. But that's like a simple example, which also our prior work fully supervised model will be able to handle. There's nothing too complex going on here. But now in the next example, we see this yellow car which starts to turn right before it gets occluded. And our model doesn't know what it actually does behind occlusion. So it actually forms like two distinct hypotheses about where it is. And that helps it to identify it once it reappears. So this that's why I'm saying that this probabilistic modeling on invisible objects is actually, it actually gives you benefits which a model supervised directly wouldn't be able to have. And finally, yeah, I'm going to also show that this generalizes to real videos in Kitty, and it can also reason about several objects at a time. I was showing one object before just for simplicity, but the model doesn't really care. It can track as many objects as you want at a time. Yeah, so that's mainly it. And I think I have shown, hopefully, that special step representations are essentially following to track for occlusions and generally to properly model objects in videos, I think, and that is objects in the world. And also, like I showed, the synthetic data, once again, can provide some unique information to us, which real data wouldn't be able to do, or it will be extremely expensive to obtain it. But at the same time, it has its limitations. And actually, then I showed that modeling tracking as a random walk along memory results in object permanence emerging from the data. And finally, I would like to maybe make one kind of connection to what Deva was saying about tracking emerging from forecasting. Well, I think we can see what we did here as forecasting emerging from tracking, right? In a way, right? So you supervise tracking, but you don't kind of forecasting the direction of invisible objects. And I would say to me, what it says is that, well, what I've been saying for a long time, I think, is that I think tracking and forecasting is just the same problem. There's no difference. And that's why they emerge from each other, really. So yeah, that's that's basically my talk. And yeah, thank you. By the coordinate model is available online. You can play with it if you want. And yeah, thank you. Yeah, Deva.
So those three bullet points. I'm surprised for the last one you didn't go back to that last slide.
Oh yeah, sorry.
It seems like, if I understood correctly, was also super shocking to me was that last result was self-supervised. There's no supervision given.
For invisible objects, it's given for visible objects, right? Yeah.
I see. Okay. And those numbers that you're showing, that's on all objects, or that's on invisible objects?
Oh, that's like tracking performance on visible. Like basically, it's a track IP on visible parts of it. Like we never evaluate on invisible objects, right? Yeah, we only evaluate like, but we use track IP, which is, you know, like it captures, it's very sensitive to fragmentation. So it shows like how well can you track over long periods of time for a lot of occlusions kind of. It's like a proxy for occlusion reasoning. Right.
Okay, so you still see this as like you still need lots of supervision for the stuff.
Yeah, yeah, exactly. I mean, although I have tried like just using like every like time frame of visible correct, and still works pretty well, right? But you still need some supervision, yeah. Anyone else? Archie? Yeah.
Yes, you mentioned this thing about like for simulated data, you are stuck with certain domains.
Yeah.
And even like theory. But then there's some parts of tracking that seem generic across the idea of
yeah.
I don't know if you have thoughts on whether that part of the model is generalized to other domains or if that already happens.
Yeah, I think it's a great question. And it totally depends on your object representations. And I think if your object representations are abstract enough that they are I think now our object representations are still highly related to sensory input, right? And if you can make them truly untethered from sensory input, where for your model, an object is an object, and then the appearance of an object is some additional property, but actually it's not nature, it's not essential for the object, right? Then these behaviors can totally generalize from all the objects, right? But I think developing such representations is an extremely interesting problem. Yeah. All right, then I guess we're good. Thank you.
That's it. Maybe not in front of the sun. I don't know. Yeah. Could be.
Wanna lower this, maybe?
You guys want to come in?
Yeah, that was. I feel like we should have a round table.
Thank you.
Go ahead.
Yeah. Okay, perfect.
Yeah, are we good to start? Is everything fine in Zoom?
I think this should be fine, yeah. Yeah.
Okay, then let's do some multi-view. All right, so then first I would like to thank our speakers for all the fantastic talks that you heard here today. And I would also like to thank you for staying here as panelists. We are really excited to kick off this discussion. Yeah, so we have talked about that we can quite successfully use synthetic datasets to train the pedestrian detectors and object trackers, and also for various other different kinds of applications. If you're really curious, what challenges are people facing when transferring models that were trained using synthetic data out there to the real world? So we have here also quite some people from the industry, and maybe you could start talking about this in the context of autonomous driving. So, for example, Paul, you were talking earlier about using synthetic data to train multi-object trackers. We also have Adrian here. That was pioneering the usage of virtual worlds for object detection and tracking. So maybe we could start with you two.
Yeah, I don't have actually that much experience, right? Especially in terms of like actual autonomous vehicles, right? But we did like transfer our model to the real like kitty videos, for instance, and we took a very simple approach, which was just to train, jointly train on like small amount of real data with ground labels and large amount of data with ground labels, right? And that was kind of enough to minimize the domain gap in our case. But one interesting thing we noticed is that this was enough because the data we used was already highly realistic. So the company we work with is Spiral Domain, right? They have a really high quality renderings, like all like lighting effects, textures, and whatnot, right? When we try to do the same with like Carla data, we need like one-off experiment with Carla, like that it does work well. Like if you just train jointly, you still like lose a lot of performance, right? So I think, yeah, that's kind of the only lesson I can give, that like, if your data is realistic enough, then the transfer becomes not that much of a problem, but it has to be quite realistic.
Right. So I've worked on this for like almost more than 6 years now. And one of the things that I think some people say, but not enough people say, is that people are too hung up on photorealism. I think we're getting there. It's important in practice and it's there. So I'm not diminishing the importance of it. But you mentioned the failure modes, right? And so the main failure modes will be like, you can have the most beautiful assets, like, I don't know, like millions, tens of millions of polygons of the most beautiful Ferrari, awesome. But if it's in a blank, like, environment or a highway, and you have 50,000 of it, and that's your simulation environment, that's your data set, doesn't matter how photorealistic your lighting is, it's gonna suck. So content realism is more important, much more important than photorealism, because photorealism is gonna get there. Content realism is a huge bottleneck, right? A lot of the talks you'll see, there's this kind of like hidden secret that's not so hidden, which is, where do these models come from? Where do these great, all these great simulation environments that you see from a lot of people today at many different workshops? And it's huge, huge amounts of human hours, of human labor. So I think that, you know, these simulation environments have gotten to a point where they're already useful, and it's great. But to go beyond, they need to be complemented by real-to-sim. They need to be complemented by all these other things that you see around neural rendering, etc. So I like this concept of mixed reality, where you have like real data and virtual data, sometimes mixed at the scale of a batch during training, but sometimes mixed a bit more deeply at the scale of even an individual data sample, where you have like some assets in some real world scenes, or some real assets in some virtual seats. So I think overall, the problem in autonomous driving in particular is so complex that you need every tool thrown at it, right? You need game engines, you need neural rendering, you need sim and real data working together. And even with that, you know, it's still a really, really hard problem.
Yeah, so we don't do too much autonomous driving things, but I did want to connect to one of the points mentioned. At a high level, it's very hard to specifically place items in spaces in a realistic way that also has a lot of variance. There's a trade-off there. How much variance can I actually create while maintaining realism? And so one of the things that we've seen, and this is in different domains that have to do with robotics and humans and people in offices on Zoom calls, for example, or in other things, right? The idea really that we have is it's important to be able to place objects with semantic coherence, but also we think that adding objects that are dropped with physics, so things that are non-deterministic, that have real randomization in them, adding that also drives performance. And so instead of trying to model through simulation everything in a kind of perfect way, put the tree exactly where it needs to be, put like everything in the simulation, it could be for driving or for other domains. One powerful approach that we've seen to this challenge is really adding physics and dropping items in physics and creating this mess that you see in the real world, really.
Several good points being discussed, especially around this content gap or this content diversity. It's definitely very important for us, and this is what we found as well. That content diversity and content realism is very important. So, you know, there is a known technique. There's lots of known techniques in this area, and we discussed some of this in our presentation. Domain randomization is, you know, like you know, more like structured domain randomization is more like, you know, simpler technique and effective technique to create large amount of diversity. But you know, and that works well. But you know, as was mentioned, that you know, you want to throw as many things as you can out there. So there's also several domain adaptation techniques to further augment these things. There's also another line of work, you know, where you want to learn the distribution of real data automatically and try to do some kind of automatic scene generation. Because now you're trying to learn some of the, you know, distribution that your target is, as opposed to focus more on, you know, creating content, and which can be very expensive, and really, you know, trying to model everything by yourself, which is also expensive. There's a question from the audience.
How important do you think is to stick to a semantically correct asset displacement in the scene? So, for example, sometimes we're restricted for cars on roads instead of cars on sidewalks, for example. And that reduces the amount of variability that we have in scenes. So, how important do you really think that we have to be fixed to that semantically correct scenes?
I think it's general. I think it's, the question is general. It's not just self-driving. I think it applies to humans.
Yeah, so I think that's a fair question. Like presumably domain randomization suggests that you don't need to have a really aligned target. You just place things anywhere and kind of be aggressive about it. Yeah, so I don't think that that's really well understood yet. But I do think one thing that's interesting is trying to build more maybe sort of generative models of scene placement and even behaviors, like the work that you were showing, because we don't really have too many of those. I think that's sort of an exciting place to maybe think about where, okay, yeah, so for synthetic data generation, we need huge asset libraries, which we don't have yet. And we also need to know like how to populate them in a reasonable way. But your question is totally valid. Like how sort of reasonable do we need to be? Can we just be loosey-goosey about it? I think that's a fair question. Maybe I'll throw out one more perspective too on synthetic data that I find intriguing, which is, okay, so one angle is definitely all the way to synthetic data. But I actually think you can view that as a spectrum, where the other end of the spectrum I don't know if folks will buy this or not, but I think of data augmentation as a form of synthetic data. It's not the real data, you're augmenting it, but we're doing like pretty sort of tame stuff to it. And I think right now we live in a world where we do like 2D augmentations. We crop, we mirror flip. But I think we're almost at the point where we could do like 3D augmentations. You know, we could synthesize what it would look like from a different camera viewpoint. And to me, that's moving along the spectrum all the way to, it's almost like a data-driven simulator, if you will. So I think that's intriguing. I'm guessing we'll see stuff like, you know, using view synthesis for nerve style stuff for augmentation.
Hopefully at DCC.
Yes. I'm sure so.
Maybe I can offer a view on this particular question where you mentioned that in some cases you may simulate something that is not really realistic per se, but it may help an algorithm or a downstream task to perform better. Now, even if we don't see it as a domain randomization problem or a domain randomization solution to a problem, we may see it as something that we may really occur in real life that we didn't even see it. So it can be a novel case where you can imagine the thing could happen but didn't happen, and you don't really want to be biased towards the distribution that you have on the real data, but you really want to explore options where you synthesize scenes and synthesize cases that you will want to operate that you can't operate on yet. So having that, like, if you have, for your example, if you have all the cars really aligned along the sidewalk and really perfectly distance one from each other, it may create those biases when you learn the task. So having these imperfections can be really useful for the downstream task. This, in my point of view, and also for really imagining these novel cases that we can't see them on the real data because things don't happen that frequently, or we don't collect the data that frequently.
Yeah, I think that there are a lot of really good points here. To add an additional perspective, I see that, you know, synthetic data is a really good way to insert human knowledge into neural networks. So the human knowledge that you're inserting by creating a simulation where the cars are not on the sidewalk, for instance, is that cars are not on sidewalks. Now, we really need to be mindful of what human prior knowledge we want to insert and what we don't want to insert. And there might be, you know, architectures that we want to insert prior knowledge into parts of a broader scheme or a broader architecture, and other parts where we don't want to insert it. For example, if you have a separate detection network, you might not want to insert that prior knowledge of sidewalks. And if you have a more broad general planning system, then you might want to insert it. So I think that it's really a balance there. I will say that for the high-level task, it is important to be robust to, like, humans are robust to this, of course. And so I think that it might be surprising for us, that there's a car that's driving on the sidewalk, but it's something that we would understand and be able to perceive. Especially as we're moving to more of an end-to-end approach, like was presented before. I think it becomes more of an important question. Like just perception, I would say it's probably less critical, but as we're moving to a more end-to-end approach, this is a very important and open question, I think.
Just to change the topic, I mean, still synthetic data, of course. In my opinion, creating a data set is just a matter of creating the more complex and more challenging data as possible. So this is why doing this, you're avoiding your network to overfit. So your network is not cannot pay attention to the small details, but has to understand the whole problem to solve it. And this is what I understood from my small experience. So when the data set is very complex,
very challenging. It contains a lot of variations. Your net will generalize. Otherwise, even if the data is very photorealistic, it will overfit. What do you think?
Isn't that also relevant, like with domain randomization? Let's just say we just create like a crazy randomizer set that's going to generalize better. I think, yeah, like there is definitely truth to that. Right? That's like why we'll do domain randomization, but at the same time, like I think realism is also important. Like if again, if you're just going to have like colored blocks representing cars and people, you know, that's and like completely randomized, it's going to be super diverse, but like it's still probably not generalized at all, right? So I think the answer is kind of both are kind of important. Yeah.
I think photorealism is overrated.
Yeah.
Maybe it depends on the task, of course, because we have this hand close estimation, so we're engineering the best and synthetic data sets to find the hand close estimation. The best thing was just project ImageNet images on the hand model, project ImageNet on the background. So from a human, it was impossible to tell. So it was a very challenging task, and it worked much better. Yeah. So like.
But so do you think this would work like for like more complex street driving scenes with many
Exactly.
agents?
So this I don't know. It depends on the task. Yeah.
I actually have a way to make us all friends. Sorry, try to spice it up, but I think everybody is right. So the reason is that I think what's going on is in the framework of causal representation learning. So I think that's the proper way to phrase it. The reason I'm explaining this is that we are lacking proper causal representations. And so some of the things we know our model should be invariant to or equivariant to or should generalize. So these are just different properties. And so when you do domain randomization, the way I interpret it is that you're randomizing confounders in the unknown causal graph that you have. So you said, like, for instance, in this case, we know that components have a texture bias, but we really want to care more about the shape. So I'm just going to randomize the texture. That was actually this paper that was exceptional for that, right? I think that's a great idea. That's because you know that texture is actually going to be a confounder for your test. So you have an underlying causal model that you don't know explicitly how to represent because you don't know how all the variables, you don't know what are all the causal factors. By the way, even if you do, we don't know how to solve it. If you talk to people in causal causality, 5 variables is high dimensionality for that. I don't think we, as computer vision people, like 5 dimensions doesn't even register as like small dimensions, like 1, 0. So I think that the whole problem is we don't know all the variables in the underlying causal graph. So what we have to do is we have to inject partial knowledge. The world is partially observed all the time. So you have to inject some prior knowledge in this form. It's a confounder, randomize it. It's not a confounder, it's actually a causal variable. You want to model that relationship and you want it to emerge as a pattern in your data so that your model learns the statistical version of it because it doesn't do causal inference. It just does correlation, right? And they say, correlation is not causation. But there's no causation without correlation, and one just did not capture spurious correlation and be causally confused. So I think the proper way to unify all this is to think about causality, but not assuming we'll have the full causal graph, like either parallel or like this type of people, but thinking that we need to leverage parts of it, like the partial observability of that causal graph. That's very high level, sorry.
So I'm in the camp where I would say photorealism is indeed overrated, but I can understand your point about how you're explaining in terms of causality. I have a more simplistic view of this, where we let the task network or a more like a task specific representation figure this out. So we have had cases even in self-driving scenarios where we had an Oracle task network guiding some of the translations, some of the how it should appear, and we have seen, like, we had concrete evidence that images started to look very crappy, very unrealistic, but the improvements was through the roof. And because we had access to the Oracle network, so we could do that, but that was just an observation and point to make that there is probably a better representation for networks that actually can give much better results than actually trying to, because it's expensive to do all this photorealistic improvements, very expensive for artists. One example we gave was MetaHumans in Unreal 5. It took one artist like 3 months to just create that amazing, realistic looking human. That's great, but I mean, how's that helping synthetic data cost? Because we don't want to spend that much time. This is the appeal.
Yeah, probably it depends from the task also, I guess.
Yeah.
So people detection is something, and detection is something, but more complex tasks, maybe require more graphic.
Yeah, so to spin things a bit and add a little bit more spice, I can provide an additional kind of perspective. I mean, we have like a lot of good points and a lot of different sides, and I think it also comes from the tasks that we see people using the data for. So for instance, at DataGen, we have folks from the cosmetics industry that are using 4K, super high quality images of people's faces, and then they do skin analysis with the data. And so the quality there is actually quite important because they're interested in the fine details. If you're interested in human tracking, it might be less important. Another interesting topic around kind of the augmentation and randomization that was discussed on the hands, for example. So like I can also maybe speak to that a little bit because we've done various work in that domain as well in the past. And what we've seen is really that augmentation is telling the network what not to look at, right? So by creating this super heavy augmentation on the skin or on the background, we're telling the network, don't look at this, look only, let's say, at the contours of the hand to analyze it. And so that's great, but you will reach a performance kind of performance ceiling, meaning you're not leveraging specific parts of the image in order for the network to infer what's happening in the image. So if you want to do like full 3D hand pose estimation or full 3D hand mesh estimation, there the question is, okay, do you really not want to look at the signal that you get from the skin of the person at all? Because that's what you would be training the network with. And I'm not sure that that's the case. I would say that for the most part, you have a nice kind of difference between the hand and the background. But if you have multiple hands in the scene, for example, then you might want to leverage more of this kind of color information, for example, in order to differentiate between the different hands and get multiple hand meshes. So I think it's very much dependent on the scenario and again, what kind of human prior knowledge we want to insert into the network, as well as what we want the network not to look at, what we want it to not be dependent on.
Yeah, but again, we're talking about variety, not about quality of the graphics, right? If you want different skin colors, this is variety, not quality. So I still think that, yeah, data set should be photorealistic, but I think variety is much important. I would say 80-20 or 70-30. I don't know.
It's hard to put a number on it.
Yeah.
Okay, maybe I can speak from experience because I made a crappy data set, as Pavel was saying in this presentation, which was 6 years ago, which was virtual PT. And so initially this data set was, if you train on garbage in, garbage out, right? Simple image processing, like information theory, right? It's called the data processing inequality, if you want to know the math behind it, but it's a mathematically known garbage in, garbage out. So to some level, if it's crap, you're gonna get bad stuff out, right? But one of the things where it's interesting, where it's the reverse. In autonomous driving in particular, because of the safety critical nature of what we're doing, it's more like, I think Deva was mentioning it and other people are mentioning it, that simulation tends to be more used for verification validation, right? It's more, that's why we have this workshop. For training, it's a bit more of an open problem, right? There's a sim to real gap and there's a lot of things that you have to work extra, right? We're not at the level where you can just replace any real data set with a synthetic data set, right? But for testing, that was the point of the virtual kitty paper in 2016, was actually, even with crappy data where you need to work really hard to overcome the sim to real gap in terms of domain adaptation, which you can, but you work really hard. A pre-trained model in the real world, which in this case was a tracker, actually was tracking by detection, but two different trackers, two different tracking styles. It generalized in exactly the same way. And this is why I created Virtual Kitty as a virtual clone. It's also what people call digital twins of Kitty, because I trained it on the real training Kitty dataset, this model. And then I tested it on the real Kitty test set and on its digital twin. And I could look track per track if the results were the same or not. and the results, and literally like mod A was equal to the third decimal. And so that was something to me that was like, huh, interesting, because if it's trained in real world data and it generalizes directly to SIM, but if it's trained on SIM, you have to work really, really hard. So the interesting bit is that there's an asymmetry to the SIM to real problem. And so if you are caring more about the real to SIM, there might be an opportunity there where indeed you don't need to push as hard your simulation. But if you are working the SIM to real angle, I think that's more important, like to close the domain gap as far as you can with quality. That matters, again, for the task.
I just want to throw out one more comment, sort of emphasizing the point we're making about like, is it really about realism or more diversity? And I would agree with you that it seems to be more about diversity. So I found Kate's talk, I guess she's not here, incredibly sobering. Like essentially, one of the take-home messages seem to be: don't try to make your networks generalized to a new domain. Just collect more data, and then that will solve. Like get more diverse data. Like turn on these massive data sets. And so it's almost saying that like we're not like a cynical view would be that we're not really building general models. We're just building models that sort of memorize the data. And if you have diverse data, then they work. If you don't have diverse data, then they don't. So it seems like diversity is this really crucial property.
And I want to slightly irritate you and to present a different point of view, because I do support diversity and I do believe that photorealism is slightly overrated. And in some cases, and it really depends on the task. So go get end shape case, which is very, very good example in my opinion. But still, I think that there is some limitation in terms of what we ask the models to do. So we can think about it as a no free lunch term, where we can't really do everything well altogether. So there is some boundaries in terms of how much diversity can the model take. So for one example will be if we got this too much light in a room where everything is reflective, this is some special case of diversing the materials and diversing the lighting conditions, but eventually you won't see anything in the room, and we still ask the model to perform good on that data. So we actually thank the model to do stuff that he can't do, that he won't reasonably do good enough. So we start to try to memorize that and maybe to do that in expense of making good predictions on other cases. So there are some boundaries that we can think of and we need to take into account when we diverse the data. We can't do everything all together. So diversity is important, but we need to really think what we are trying to do and not ask the model to do everything all together. So maybe disentangling the task, or maybe deep dive into the cases where we want to first predict the hand shape, and then we really want to deep dive and see the textures after we know which part of the hand is in view and we know which part of the mesh is in the camera field of view, and then we want to choose what task we want to do next instead of doing it all together. So that's my 2 cents on that.
Augment Aido's point further, there is a structure to diversity. Like domain randomization by itself, you randomize everything, is not going to give you the best performance. That's been shown in the work out there. So there is a structure to it, right? If you throw in context, if you throw in scene graphs and randomize the parameters of the scene graph, that tends to work. That kind of randomization tend to work better, right? But that's not the end of it, right? Like there's if you looked at Kate's presentation today and some of the work that has happened previously, there's a certain distribution that's optimal for your downstream task and for your data, your data set that you're evaluating on. So there's a certain distribution even in randomization that you want to look for. And that's best learned as a signal through task network, because let the task guide you. Like what sort of randomization is better for it, because just plainly randomizing it is limiting.
about distribution. How do you find balance between over-representing the edge cases and not messing up a realistic distribution?
That's a great question. One thing that when we say edge cases, the challenge is that those edge cases many times don't show up a lot in the test data set, right? Or in the validation set. And so one thing that we promote a lot is doing unit tests, similar to software engineering, where you have unit tests for the different functions, the different pieces of your code. There's not one giant test. We promote the same direction with computer vision. And when you have access to high quality synthetic data, like through code, you can then think of the data itself as code. And you can think of creating test sets that validate these different edge cases separately from the main test set. And so when you change your model, when you upgrade it, when you retrain it, you want to validate that it's working well in the general sense, but also working well on each of these edge cases that you thought of. And also, taking a step back, you don't want one test set or a set of fixed test sets, but you want to be constantly growing this. It's kind of like the robustness of what you're developing is dependent on the robustness of your testing suite. So, yeah, that's how we think about it, at least.
Do you have any estimates on about percentages, maybe?
So it's really dependent on the task and what you're trying to do and everything. But we've seen a lot of things with respect to humans and understanding people. And then you really want to create unit tests both for bias analysis to validate that there isn't imbalances between different ages, genders, ethnicities in various different downstream tasks. And also you want different edge cases. And so there are various kind of extreme poses of the head, extreme expressions. There are many, many different edge cases. Could be lighting edge cases as well, where you have extremely brightly lit scenes, for example, and you want to perform well in all of those different scenarios. And so it's, again, very dependent on the target domain and on what you're trying to solve. But the concept is very much the same. Just really, as the field is progressing, moving to more of a software engineering mindset and not as much of a research and research paper where we have like that one number that we're trying to hit. We need to move to more of a mindset of a software suite and test suite.
All right, that number is 42%. It's a good question, and actually it's a testament. I will also say it's a sobering question to use those, because I've had the same question for the past 6 years, which is, do you need photorealism, right? That's number one question. Everybody asks this question. And then the second question is how much real data versus synthetic data? That's always the question. And the answer has always been it depends, which is a testament to how little progress we've made on this question. So the pragmatic view is yes. But so what it means, the pragmatic view, is that we have no science, we have no strong results to guide us. It's guided by the empirical stuff. So we tried to do, I think there's one thing that changed though recently. And so we had a paper at ICCD last year called Buddha for geometric unsupervised annotation. And so here we try to do a scaling law, because in machine learning now, at the scale where we're at, experiments can run in the tens of millions of dollars. And when in addition, that's with the data you already have. When in addition you have to pay a company to generate data, then it's even like the onus is even higher. And when even more so, it's like, we don't know how much data we're going to have to buy. That's even worse. So I think there needs to be some serious work in the scaling laws for sim to real. And so we did an embryonic version of a scaling law for sim to real back in this ICCD paper, Buddha. And so we found a couple of things there. We found one, quality actually does matter. So I said photorealism is overrated, but in its importance, because we're getting there. It doesn't mean it doesn't yield performance improvements in certain tasks. So we did observe when we compared different qualities of synthetic data, like old school VNT, not that great from like 6 years ago, to the state of the art we can buy now. And quality improves. So that's one axis of the scaling law. The other axis of the scaling law is the quantity of synthetic data and also the influence of the batch. So all these hyperparameters, etc. So it's in the paper. I encourage you to check it out. And by doing the scaling law, what enables you is to say, well, how much money would I need to reach this amount of performance? How much, how do these parameters relate to each other? And you can extrapolate, right? And so one of the things that we found in the process while doing this is that there were some surprises in the scaling law. And one in particular was that geometry-based features actually turn out to generalize really well across the seam to real gap. So the dimensions of the seam to real gap is like the seam to real gap is typically seen as a kind of a 1D thing in accuracy space, but it's not. There's many such buttons you can turn in the simulation and the different scaling laws that happen with how you scale these different buttons. So yes, the pragmatic view is ultimately the view that works today, but hopefully in the future we'll have some better scaling laws that cement our understanding of the seam to real gap. I don't know what was the order, so maybe the back first, yeah.
So yeah, the question about more complex stuff. So we have lots of really interesting topics today with breaking, which is not really the air, but just some tools for leveling. That's actually what we're doing also in real world scenario with, for example, scenarios similar to MOTSynth and MOT, where we want to analyze personal behavior. So what are we doing? Is it someone kicking, someone trying for help, or maybe lying? And what works like MOTSynth is really useful, for example, for estimation in 2D or 3D. But right now we may be using this dataset for standing person and walking. Maybe sitting at most with like one person of the poses, which is sitting. And I'm not quite sure how realistic it is. Not photorealistic, but realistic in the air for behavior realistic. Do you have some thoughts about this? Or could get to this point where we are using sim data to analyze behavior instead of using huge real data sets that are really problematic for the data privacy?
Take that. But yeah, so I basically abandoned synthetic data because of this reason. And switched to human motion synthesis because of that same reason, because the assets are limited for so many tasks. If you care about low-level things like semantic segmentation or pose estimation, optical flow, like pixel-level things, it's great. But whenever you're trying to attach semantics, behaviors and semantics, it's becoming problematic. Then I went back to like how do we generate and attach semantics to motions and go beyond walking and running. So I think there's a bit of work before I could go back to synthetic data with that. And maybe another domain, which I'm also working on sign language. And people always tell me there's not enough data. Why don't you simulate synthetic data? How am I supposed to generate moving hands without having actual motion capture and scale, capturing all the thousands of signs, the diversity of signs and everything? So simulation sounds like something that's for free, but it's like, of course, there's a lot of assets and engineering behind, which is not so trivial for many tasks. So, yeah, that's not an answer, but I don't want to demotivate either.
Yeah, I just want to reinforce my experience is the same as we did the paper on procedural human action generation for videos to train action recognition models, so CPR 17. Yeah, thank you. and it was the same conclusion, exactly the same, because what we did is we started from the CMU mocap dataset and then added some amount of noise, but then also added ragdoll physics and inverse kinematics to be able to just add noise that was like physically okay. And it's actually pretty hard. Like you have a lot of bugs that look like video games from the 90s, you know, like things like, you know, whatever. So yeah, so in the end, I think I agree. It's like, it's actually tremendous amount of engineering. And in the end, you go beyond what you already know. So I think also the generative modeling needs to happen before we can. So I 200% agree with what you said.
I just want to, I want to kind of cite someone very smart who I think kind of summarized this thing very well. It's Vito Ferrari, for both of you don't know, he's a Google Service right now. We were back in 2016, like I was showing like the flying chairs, like everything said back then, there was like a wave of people saying, oh, state data is gonna solve everything, that's the answer. And then like there's someone asked this question to Peter, like, is that do we need like anything else now? And he said that basically, well, in order to, if you want to say data to replace everything, especially for like high level tasks, right, like activity understanding, then you need to be able to model everything in the world. But if you can model everything in the world, what do you want to learn anymore? Like you already have a perfect model of the world. So it's a kind of it's an equally complex problem as learning general AI, I think. So I don't think there's going to be. I think it's going to make more direction probably because we're going to inform each other, but one is not going to solve the other.
So to quickly counter everyone who just spoke, I'm just kidding. But I will give a very different perspective, and we can connect it to the various examples here. One is I definitely agree that you guys, for the most part, should not be trying to create your own synthetic data because it is extremely hard to do, and it requires a lot of engineers working on things that are not computer vision. It requires a lot of infrastructure and a lot of graphics engine capabilities, and like creating good synthetic data is extremely, extremely hard. But if we take, for instance, the cases of, let's say, sign language estimation, which is a great case, or action recognition, like was presented here, using some of the capabilities that we've presented, and I don't want to make this kind of sales pitch, but I will say like a few things. Using the capabilities we've presented or we've created, you guys can create this with relatively low effort. Meaning, for instance, for sign language, if you do have a mocap of sign language, you can use our API and pretty much apply that same sign language to 100,000 different people with different lighting and different directions. You can drop physics items in the scene. You can do a lot of very powerful things that would not be kind of available to you ahead of time. And so using things like this, you are able to progress towards solutions that are codable end-to-end, meaning you don't need to go out to the real world and gather a ton of data to do them. That said, right, it's definitely a challenge and definitely not something that we just stumbled upon. We work really, really hard to make this at good quality. I don't think that simulation and the ability to create a general AI is anything that I have to disagree with that as well. Simulation is very engineering, requires a lot of engineering. General AI requires a lot of advances in AI. I think that they're two separate tasks and they're not equivalent to each other. Really, we're trying to create the data. The AI aspect is really compressing and extracting from that data the relevant information in order to create a transformation function from the visual domain to some kind of structured output, some kind of information. And so, we're trying to create those hundreds of gigabytes of data. You can then extract from that and kind of compress it into a network that weighs 50 megabytes, for example. That's kind of how I think about it. These are new capabilities. We will be coming out with more and more kind of publicly facing benchmarks, and we have a few that have already been out. But and we'd love to collaborate on sign language, really. Yeah, it's a step-by-step process. I will give maybe one example of in-cabin, because we do work with a lot of the big auto manufacturers. For in-cabin, you have like people falling asleep on the wheel. You can either pay people to fall asleep and then come in and then kind of go do as if they're driving. Sorry, there's some kind of.
Yeah, we're just trying to figure out what.
Okay, so you can either pay people to come in and then film themselves driving, capture video of people that are sleepy and that are falling asleep, or you can capture the motion of these people and then apply it to 100,000 different people and create randomization in that motion using various methods as well. And so that's like a more scalable approach from my perspective.
Just to augment your point further, there is also works that we do in terms of proceduralism to actually augment and create more human trajectories and further augment motion captures. But obviously, motion captures are a good starting point, and that's where we start. Just add more diversity to it, more perturbations, more randomizations. And there's also some recent work on looking at videos and trying to get all kinds of poses, not just pose estimation, but trying to get the whole human representation out of it from Jitendra. So that could be another interesting direction to actually address some of these issues.
Yeah, so I think we are way over time already. This was a very fun discussion. So I think that what we need to do is now to conclude the discussion. Thank our speakers and panelists again, and also the audience for all the great questions. And of course, if possible, if some panelists still have time, we can take other questions offline.
Thank you.
So thanks.
Thank you. Thanks.
Thank you, guys.
Thank you. Thank you for the organization. Really great job.
Thanks. Thanks for inviting us.
So great to meet you.
We can drink something after. Maybe
Yes,
this
yes.
week.
Yeah.
For sure.
Should give you my number.
Yeah, give me your number.
So it's
Plus.
yeah, plus 972. 972.
972. Three numbers.
Yeah, yeah. And then 054.
054.
819.
819.
0740.
0740. Gil.
Yeah, let's do it.
Yeah.
Prepare something.
Yeah, just something. Very nice.
Yeah. More than that. It's a pleasure.
Maybe not tonight, but we can. Yeah. Which is unfortunately is but if you some
Thanks again, guys. It was great.
Thank you. Very nice.
Yeah, great job.
Thanks a lot for coming.
No.
Oh, we're done.